right. Welcome all to the Cisco Quantum Summit. Building on the success of the past 5 Quantum Summits, I'm really looking forward to the 6th one. We have started with an annual summit, and of late we've been doing 2 summits per year. So this is very exciting. To kickstart January of 2026, we are super excited to actually bring 2 trendiest topics of 2026 that I'm sure you're all excited about: AI and quantum. And this is the first time we're actually fusing both of these major trends, industry trends, into one conference or one summit. And we have an exciting lineup of some amazing speakers that are going to touch upon these the intersection of these 2 topics. To start with, we have our Cisco keynote, and followed by technology track and infrastructure track. And then finally, the later half of today, it's going to be about ML applications that are going to be powered with the help of quantum data centers. So it's a very interesting combination of AI, ML, and quantum that I think we are doing it for the first time. Really, really excited. And I know people are tuning in from all around the world, so good morning, afternoon, evening to our remote viewers. I've been told that between the in-house set of folks here in San Jose, in Cisco, as well as our remote viewers, we have about 1,000 people tuning in live today. So that's very exciting. This is actually the first time I think we're hitting that large a number. And we are really excited to kickstart this session. And so this first session is actually I'm chairing this first session. The original plan was to introduce our head of Outshift and SVP GM for Outshift, Vijoy Pandey. But unfortunately, as with any large city, we have traffic woes, and he's stuck somewhere in traffic. Hopefully, he should make it soon. So I have been tasked with actually giving the talk myself. So I'm going to be doing my inner Vijoy to actually channel his thoughts and also extend a warm welcome to all of you folks. Okay, so with that, pretend that I'm Vijoy, maybe not as debonair as my boss and SVP GM, but so just a brief introduction to Vijoy. So Vijoy is actually head of Outshift. He's and Outshift is the Cisco's incubation arm, and Outshift actually works on several new products and new directions in the emerging tech world. And off late, the 2 most important trends that Outshift has been focused on are building the Internet of Agents, that is the AI/ML side, and then the quantum internet. And these 2 are the primary pillars for Outshift. And Vijoy also oversees Cisco research and DevNet and open source for Cisco. These are broad Cisco-wide initiatives. With that, let me dive into the keynote that Vijoy has prepared. So I'm just going to be delivering this for him. So life is filled with emerging paradigms, and one such paradigm shift that was predicted by Feynman is that in 1981 is that nature isn't classical. It's actually quantum in nature. And so simulating a lot of nature or problems in nature really becomes hard in classical computing infrastructures. In order to actually simulate nature behavior, you need quantum mechanics. And that has been predicted way back in 1981 by Richard Feynman, and that sort of ushered in the era of quantum computing. And what do this quantum computing, what is the promise for quantum computing? This is really about solving some real hard problems in fields such as weather modeling, logistics, pharma, discovering new materials, logistics optimizations, financial portfolio management, all kinds of these really hard problems. There's a promise that quantum computing can really help with this. For all the promise of actually solving these real hard problems, unfortunately, the reality is that quantum computers are nowhere close to where we want them to, right? it takes about hundreds of thousands of qubits in order for you to be able to solve many of these problems effectively. But the reality is we have about hundreds of qubits, three orders of magnitude away from where we want to be. So one way to actually address this gap is to scale up, which is basically build out a much bigger quantum computer. Another way which we can actually leverage from our classical counterparts is the scale out approach, right? Which is really about taking a large number of these quantum computers and sort of interconnecting them with the help of a quantum network to really build this gigantic quantum data center. So this is really what Cisco and our quantum labs have been working on for the past few years now. We've been really trying to build this quantum network of the future that can interconnect all these quantum computers and make these really hard problems tractable with the help of this kind of a quantum supercomputer, if you will. But it's not just about quantum. The future data center is not just about interconnecting quantum processors. You will need to coexist with GPUs, CPUs, star PUs, essentially, any type of processing units. They all need to come together to actually solve these problems. It's not just about interconnecting quantum processors. And that is where the future lies. And many of the dots here are just basically representing the different colors represent different forms of processing units. So the fundamental building blocks that we have actually already worked on is this entanglement source for building out the quantum network of the future. And we've announced this last May, and this chip can actually generate about 200 million entangled photon pairs per second, and it operates at room temperature, which is pretty amazing. So in addition to announcing this hardware piece, we have actually announced a full stack, holistic quantum network stack that basically, you have the quantum hardware at the bottom, you have various quantum network protocols like entanglement distribution protocols, teleportation, what have you, and then your quantum network aware application, such as your distributed quantum computing compiler and several other classical applications that we have talked about that can leverage the presence of a quantum network. But these hard problems, right? So it's not just for quantum to solve. AI models have also been trying to target many of these applications in the past by throwing more data at it, more compute at it, better training models, this kind of stuff. Okay? Quantum is also facing scaling challenges. So AI and quantum both are actually facing scaling challenges. And this classical quantum networking is actually one of the key foundational technologies that is actually going to help with addressing the scaling challenges that both AI and quantum will face. So really, that's why you shouldn't be thinking about both these in isolation. And in fact, there is a synergy that needs to be exploited between AI and quantum if our real goal is to actually solve these problems at scale. I don't think of this as just a bunch of talks. Really, I think today the agenda is to really come together and do a joint design of how AI and quantum can come together to actually solve these real major technological problems. Identify those gaps and figure out how to address these gaps to get to where we really want to be. The tagline being, let's make hybrid AI quantum computing real. And that's the goal for today. And with that, I end the Vijay part of me, and I transition to introducing the next speaker. I'm super privileged to actually introduce Resza Najabati, who actually leads our Cisco's quantum research efforts, and he's been super phenomenal over the past couple of years to get this whole quantum networking goal and agenda and vision, really shaping that and bringing to light several innovations in the past 1 to 2 years. So with that, further ado, please welcome Resza Najabati.
Thank you. Thanks for the introduction. No, I am sweating. Okay, let's get on with the presentation. Today I am going to present that what is the Cisco vision about building the network infrastructure for a quantum era, for network of quantum era. Ramana alluded to that, but I will add one more thing here, that we know that quantum computing has a scaling problem. We need to build, if you want to really make an impact, both business, commercially, or in the life of people, really need a far larger quantum computing that even being promised by 2030 today. Also, we know that the classical application, in certain areas, they are hitting the boundary of the physics. From the latency, for example, you are bonded with whatever latency of the fiber is with one point to the other point. So these are the problem that basically we believe a quantum network can offer a solution for both of these areas. And that's what in Cisco we are focusing. So I'm going a little bit deep dive into that, what we are building for our quantum networking technology. One is what we call it quantum for quantum, or quantum networks for quantum technology, where we focus, as I said, to build a network that can help to scale out quantum computers to a impactful size. And that's basically first instance, building a network that at data center scale that connects quantum computers together. Why we choose the data center at the first? Because data center is more controlled environment, shorter distances, and that's where our focus is that. Now, once hopefully we achieve this, that gives us a pathway to create a much faster, or create a faster speed to market, or speed to application for 1 million plus qubit that we need to make impactful applications. Now, once we succeed, our plan is that to extend our network to connect the quantum data centers together, basically go toward the quantum internet. And then at the same time, we are looking at the quantum network technology that we developed that connect quantum computers also has application for connecting quantum sensors and build a distributed quantum sensing. So connecting quantum sensors to a quantum network is a must. You can argue that distributed sensing is valid or not. I leave it to the academics to explore that. There is certainly argument for distributed quantum sensing, but nevertheless, there is an advantage to connect. There is a need to connect, not advantage, to connect quantum sensors to quantum computers to take advantage of the quantum effect. So that's also a network that we are looking on that. Now, all of this, we are building the network, but all of it is depending when a robust and useful enough standalone quantum computer, quantum computing chip will be available, so it's ready for networking. So we are working with the quantum computing partners around that, but at the same time, we find out that there are other useful applications in the classical domain that today they can benefit on that. One of them is the security. Security, you can, obviously everybody knows about the QKD, but there are other applications. For example, we can use our quantum network entanglement network that we developed for connecting quantum computers as a sensing probe to see if there is somebody tapping to your classical network. Or you can develop a network that two parties can play quantum games and do the telepathy for decision coordination with application in finance and military. All ultra precise time synchronization and also position verification. These 4 applications are example applications, but applications we found out from our customer domain partners that they are really demanding now for a solution that quantum perhaps can help. So with that vision aside, let's focus on the theme of today's summit. So we are building a quantum data center. So our objective is that to build the best entanglement distribution network. So is that a scalable, very high fidelity, and also is a multi-tenant, multi-user. So we can multiple application or end devices can use it at the same time. Now, we don't want, as you see this slide, there are several modalities of the quantum computing I have shown is connected to this network. The reason behind that is twofold. One is, first of all, it's very difficult for us to bet which quantum computing modality is going to win the race or be a dominant technology. The second, also we believe that a quantum data center would be a mixture of technologies, mixture of a few technologies. Every quantum computing technology can bring different advantages for certain type of circuit or application. That we see that there would be a mixture. Also, there is a possibility would be a mixture of technology. Therefore, we are building our network to be compatible, or as much as we can, to be the view to be compatible with these various quantum computing modalities. Now, connecting quantum computers just with the quantum entanglement network, really, okay, you can see how scalability can achieve, but really doesn't make a quantum data center. Then you have the whole bunch of classical network. I mean, you need to connect it to a, I will highlight the GPU, but you read it as GPU, CPU, or compute, classical compute part, advanced cross compute part. You need to connect them together. There are the twofold reasons. One is that you need to support the classical processing of that from measurement comes from out of a quantum computer. The other thing is that we see quite a lot of application that, especially in machine learning domain, that they propose there is a potential benefits to use the quantum computing as an accelerator for a machine learning or AI computing. So I don't want to claim that's proven or is a valid, but certainly there are very good indicators that shows people that there is a good advantage to this arrangement. Now, I hope that today during the summit we see the argument against or in favor of this this claim, and we can at least get some more information about this and make a decision. Now, let's focus on the first quantum network, then I go to the classical network part of it. On the quantum network part of it, we are building the full stack of the network, quantum networking. On the hardware layer, we are looking at the breadth of technology I put on at the bottom, from entanglement source to switch, to measurements, to synchronization, memory, and interfaces to quantum computers. Things that also Ramona before me alluded to, that we have announced some of our technology earlier in 2025, that the entanglement source, there where we use, basically that's what is a fundamental for us to do connect the quantum computers and based on the try to succeed, at least at this first stage. Then also we have done a partnership with the startups and to basically develop atomic-based quantum entanglement source. And the reason for that is, especially this particular case is a rubidium, and rubidium gives a transition between telecom and neutral atom. So therefore, is a path, one of the way that we are looking to use as a part of our transactional conversion. The other thing is that we have our own internal development on the basically tunable transduction from neutral atoms to the photonics. We are working on various parts of this architecture, as you see on the right, from the nonlinear tunability material based on the Chi2 material and Chi3, and also the cavity part. These are still at the R&D stages. And also the other thing that we noticed, I will go a little bit more detail on that on the classical part, really to make the quantum computing work in distributed way, the synchronization that most people use white rabbit, I guess, is not good enough. And I go a little bit on that why, and then we had to develop our own synchronization mechanism. Obviously, other technology on the bottom, the memory measurement and switch is also the active work for us there. Now, what we want to do, we want to be able to create a network that essentially allows us to connect the quantum computers based on emitter or a scatter protocol or combination of all those protocols. And also we want to make sure that to share the resources as much as possible in our data center, at least for the quantum computer are closer together. So that's why we see that we have a quantum switch, our quantum processors, and then a bunch of Bell state measurements and entanglements. So this particular architecture is designed try to succeed communication between the quantum processors. And we have done essentially we released the detailed analysis of architecture and how does it work in the archive last year. And then every year we update with the new funding and new recommendation how a quantum data center look like. Earlier this month also we released a new version, which you can see the archive there. Now, that's from the hardware point of view. When you go to the software, also we have built, we are looking to build our own compiler, but our compiler has a very unique angle. It's looking for distributed computing, take into account the network that we are building for distributed quantum computing, and how we can do the error correction more effectively when you bring the network into the play, which is by itself is a source of error, and then how we can do the circuit partitioning, and then that's also is a very comprehensive software that supports the network. As far as I know, it's the only distributed quantum computing compiler that has a network element embedded into it. And we released the first version in end of September, beginning of October, publicly available. Can be done via barcode. Very soon, please stay tuned that a much more enhanced features for this is coming. I mean, we are scheduling the release of it, but very soon it will happen. Now, let's go to the classical part. So the way that we see the data center QPU to QPU is dynamic. We don't have a point-to-point connectivity forever stay there between two. So it can't, relationship between the QPUs, two QPU can change at any time in a data center. Depends on your circuit, and that gives you a lot of advantage both in design of algorithm and also circuit partitioning. Then if you do that, then something like a white rabbit just doesn't cut it for you. And the reason for being that white rabbit is very highly accurate, that's great, but as soon as you start changing the dynamics of a network, you have to wait minutes, sometimes a large amount of minutes to basically to achieve your synchronization. So we wanted something to give us accuracy of the right rabbit or better, and also the same time can cope with the dynamic change in the network. The other thing is that the quantum error correction workload. That's another thing that's need a low latency, high bandwidth. So, so for our synchronization, we have developed our own synchronization protocol, which is very light touch and essentially works on the fiber network, in the classical fiber network, and is basically at the moment is FPGA, but eventually can be ASIC with atomic clocks. And basically it has its own network interface card that plug into the measurement part of the QPUs. And that allows us if the relationship between the point-to-point changes is very fast startup time has. So you have a picosecond accuracy on the synchronization and the startup of the microsecond, and we try to reduce that even further, the microsecond side toward the nanosecond. So that's one of the unique work we have done. The other thing on the classical part is that there are studies. Again, we are not building quantum computers per se, but there are studies, well-established studies that okay, how much data you generate out of the quantum computer when you do the measurements. And that we are talking about the terabit per second and the petaflops of compute requirements aggregated for a distributed quantum computing. Now, obviously that depends on what modality of QPU or quantum processor you are using, how you do your measurement, and what type of error correction and control you are using. So this is is changeable. So we wanted to create a network that capability that doesn't bound us for a specific computation, specific architecture. So then we come up with all this high-speed reconfigurable network. Essentially, we have our quantum network for a data center. That's a very abstract version I showed you earlier. Now, what we do, we have our own development of the basically classical network interface card for design for very high bandwidth transport. And also, we are working on a fast optical switching that allows us to allocate the GPU resources at a high bandwidth very fast to our computing resources. These are, again, what I explained here is our R&D prototype and research activity. So what we do, we rely on the optical switching fast version of it, and also let me see, yes. And also in NIC switching. So what we do, the switching technology that we are developing, we believe that comes out of our quantum switching technology development, can be applied for the classical part of the requirements. And also, Cisco always has been good on the transponder side, and we are taking advantage of that to basically build a very tunable transmission using our own FPGA that we develop in the research part to create this capability of the in-NIC switching and high bandwidth transmission. Now, then comes that this is something that we are working. Okay, now you have this capability. What is the ratio between the two? So you want to build your quantum pod, your AI pod. So first of all, that AI pod or compute pod, if I want to make it more generalized, doesn't need, it can be allocated to any task, including the quantum support task. Or a quantum pod needs to be allocated to a standalone task by itself or to support AI tasks. So that's why we build this. And then we are thinking how we can scale this, because we see a view that this is the modular pod that we can build it, and then depends on your need, you can choose any of these pods and connect them together the way that you want. So one way to connect and scale it is the scale it via the switches that we develop. Obviously, that's scaled linearly by the size of your switch. That's a big problem that needs to solve. A scalable switching at a fast speed is not an easy thing to do, but that gives you the advantage of the latency, in fact, and flexibility. That's are the things that we are still working on that. So with this, I stop here and I basically finish my talk here.
Thank you, Resza. It's always impressive to see, practical, outcome of these designs and stuff. I think we went from really high level to really getting into the nitty-gritties pretty soon. So hopefully that woke everybody up and you're all geared up towards the next session, which is actually from industry perspective. Now we are moving to academic perspective. And our next speaker is truly a titan in the field, Professor Mikhail Lukin. He's a Joshua and Beth Friedman University professor at Harvard, and he's also the co-director of the Harvard Quantum Initiative. His research is in the area of quantum optics and quantum information science. He's also the co-founder and chief scientist at Coherent Computing. The number of awards that he has won is just staggering, and I'll probably take an hour to just describe them. So just keep it short. Alfred Sloan Fellowship, David Lucille Packard Fellowship, NSF Career, many, many more. He's also a fellow of pretty much all the prestigious institutions that you've known: American Physical Society, Optical Society of America, AAAS, and most importantly, a member of the National Academy of Sciences. Without further ado, please welcome Professor Mikhail Lukin for his talk on New Frontier of Quantum Computing. Really excited.
Right, so yeah, thank you once again. So it's a great pleasure to be here So my talk will be about building quantum machines. And this is really an exciting time in the field because there are many platforms which are now being used to realize kind of key ingredients for quantum computers and quantum information systems, ranging from atoms, neutral atoms, ions, to superconducting qubits and photons. And what all of this work is now addressing is what I sometimes call the ultimate quantum rivalry. Now, it is kind of these days, it's a loaded term. It can be viewed as a competition between different platforms or maybe even between different countries. It's actually much more fundamental than that. So this is really a competition between two forces of nature. And one of the forces is really a controllability, where we need to isolate and control individual quantum objects one at a time, with high precision, with low errors, such that we can maintain the quantum states. But at the same time, we have this kind of force of scalability, where we need a lot of these things working parallel. And these two forces are in competition in many areas of human activities, probably here in Cisco. If you put a bunch of very smart scientists or engineers in one unit, it will become hard to control. So, but I mean, this here it's really in this area of quantum information. It's really fundamental. So most objects around us are built from quantum particles, from single atoms. But when they put together, they behave completely classically. So basically, what we are trying to do in this field is really kind of confront the nature, and force the nature behave quantum mechanically at large scale. So the current frontier is what we call the era of quantum discovery, where basically there are several systems around the world which can put together hundreds of controlled qubits, and with this one can really push the kind of boundary of what modern classical computers can do. And basically what we use the systems is to start to test and implement first quantum algorithms and explore first applications. But then we also can use them to kind of learn to build bigger and better quantum machines. And the key challenge, which we knew already for many years will emerge, and it's now we have to confront, is that basically as you increase the number of the qubits, and increase in particular circuit depth, the depth of your computation, you have to confront the errors. That's kind of this, and these errors, as I already mentioned. So initially, it was not even clear if there is anything which one can do about that. And for example, whether one can use something like redundancy, classical error correction, because quantum mechanics is special. There is no cloning theorem. You cannot duplicate quantum information. Also, usually if you use redundancy, you have to measure your state of your system to basically compare, to kind of compare the outcomes. And usually if you measure quantum state, you destroy quantum information. So nevertheless, it turns out quantum error correction is possible. And the way how you use it, you basically use entanglement to delocalize quantum information between several physical qubits. And we say that this procedure can be used to encode the so-called logical qubit. And basically, one can then use local measurements to detect local errors using the so-called stabilizer measurement while preserving this globally spread quantum information. And the key idea is that basically by being delocalized, this kind of new logical qubit degree of freedom becomes hard to accidentally manipulate, and you can therefore store and protect quantum state during this evolution. But you already see, even in this simple example, this is quite an intricate procedure. It requires a lot of overhead. It requires a lot of physical qubits to manipulate one logical qubit. And for this reason, up until very recently, basically all experiments in the field were limited to very small number, 1, 2, or 3, maybe small logical qubits. So we want to change this situation. And in order to do that, we use quantum computers built from individual neutral atoms. So this picture here on the screen shows how each of these kind of experiment starts. So this is a cloud of about 10 million nearly motionless atom in something which is called magneto-optical trap. And it's actually 10 million is a lot of atoms. So if you can use each of them as a qubit, you have a lot of qubits, and they're basically identical. They're basically nearly not move. And the challenge is really to kind of learn how to control them. And for that, we use optical techniques. And the kind of fundamental idea is we trap individual atoms in focused beams of light, the so-called optical tweezers, and then move these atoms around to basically assemble them in this kind of registers. So basically, each dot here is literally a picture of one atom, and trapped in this optical tweezer. And basically, once we kind of move these atoms, we start exciting them also with laser pulses to manipulate their internal states and excite them in particular into something which is called Rydberg states to make them interact, to build quantum logic from that, and eventually we read out the state of the atom. That's this projective measurement. And so this kind of simple, seemingly simple approach turns out to be extremely powerful. And in the next, in the last 10 years, really changed the trajectory of the field, and the next 10 years will change it again. So, and basically now there are several hundred of systems like this under construction, and there's at least 15, I think more now, maybe more close to 20 companies already trying to commercialize this approach. So these are some examples of the recent work utilizing the system from our lab. So what one could do is one could use this kind of system as a quantum simulator to kind of probe complex many-body states, both ground states, excited states. One can start use it to explore, some classical algorithm classes. And the system of this kind of analog system, has been for more than 2 years now available on AWS Bracket service. And maybe one reason why I'm mentioning it here is that basically the kind of most fruitful collaborations which we found were really collaboration with a supercomputer kind of centers like NERSC, for example, where there are teams of scientists designing these algorithms and using both this quantum machine and also classical supercomputing systems to really kind of advance and in fact to make discoveries in some cases. So, but what I would like to do today is focus on this kind of digital quantum computing, and in particular this quantum error correction frontier. And so the idea, the key ingredient here is something which we call reconfigurable architecture. So usually if you build a chip, for example, a chip in your cell phone, so this has been, designed many years ago, and then basically optical techniques, not unlike the one which we use here, have been used to basically kind of, create this, transistors. But the connectivity of this chip has been essentially determined at the point of design. So this is different here. So here what we can do is we can encode qubits in these so-called long-lived states, for example, spin states, hyperfine states, such that the atom in the states can be trapped in this tweezer and basically stored for a very long time. And in particular, this tweezer can be moved around while preserving a quantum state. And this gives rise to this so-called reconfigurable architecture, where basically the connectivity of the processor is a living organism. So what we can do, we can encode qubits into the atoms, move atoms around, excite them briefly in Rydberg states, do quantum logic, then kind of move them again, and basically the connectivity will evolve with the computation itself. So there are several unique opportunities here. First off, this connectivity can be clearly non-local, and in particular, this allows us to control atoms in parallel very efficiently from the classical point of view, which actually has really been underestimated. The importance of that has been underestimated previously. So in addition to this kind of new approach, we as a community made a lot of progress in the last 3 years to basically control systems up to about 500 qubits. So first of all, the gate fidelities have been dramatically improving over the last 2 years. In other words, the errors per each physical operation is greatly being reduced to the point that we are close to now to the 3/9 of fidelity. We also learned how to program arbitrary circuits by doing a lot of single qubit rotations in parallel. And we also learned how to read the atomic state, the atomic qubits mid-circuit, while preserving coherence in other qubits. And in our case, the way how it's done is we just take some qubits which we want to read out and move them in a separate zone and then image them with the laser beam while preserving coherence of the rest of the qubits. And so altogether, about 2 years ago, this resulted in what we call first logical quantum processor. So this involves a zoned architecture where we can store logical qubits in one zone, and we have a separate zone where we do gates in parallel by just shining exciting atoms in the Rydberg states, and we have a readout zone. So it's actually this starts now looking like a real computer. So in fact, this architecture is reminiscent to something which is called von Neumann classical CPU architecture. In fact, there is even a version called the Harvard classical CPU architecture. And so it was actually kind of a major jump in the field, in fact, enabled by a group of exceptionally talented students and postdocs. But the key idea here was to really move from controlling over individual physical qubits to controlling individual logical qubits. And the idea basically is the following. So let's consider two logical qubits now separated, and spread over a number of kind of physical qubits, and consider, for example, the task of making a quantum logic operation. So because now quantum information is delocalized, it's actually quite non-trivial to actually enact a logical gate, for example, on these qubits. And typically, this requires, some sophisticated procedures. Actually, even their names sound scary. As one of them is called lattice surgery. You have to really kind of, design. But actually, in our case, there is a very elegant way how you can do this logic operation in one step. And the idea here is essentially the following. So what you can do, you can pick up one of these, qubits and then move them essentially of blocks, and move them on the top of another block. And just with one laser pulse, where you entangle pairwise the qubits which sit on the top of each other, you enact something which is called transversal CNOT operation. And this operation turns out to be extremely powerful. So first of all, it's inherently fault tolerant. The information cannot spread between kind of within the blocks here, and it requires, as a result, much fewer rounds of error correction. One can also imagine longer range interaction, but more importantly, from the control point of view, you can really think about each single block here as a kind of macro atom. And basically, all of these physical qubits within this block will receive the same exactly instruction and will act like one of these big atoms. So you can basically minimize dramatically the number of control knobs and calibration knobs that you need to operate these kind of qubits. And so basically, in this work about 2 years ago, we have done this kind of quite advanced circuit in which we entangled 48 logical qubits. And this kind of case, you see this kind of hierarchical entanglement. So each of this dot is one atom, and each of this kind of circle is one gate operation. So here we ran out of space in our entangling zone. We had to kind of store the qubits temporarily, and we do operation. And what you see at the end, we will entangle them all together. And actually, this realizes a so-called scrambling circuit. It's actually a very similar process to what happens in a black hole. And actually, this work already showed that even this early version of this logical kind of processor can be useful for probing physics of entangled complex systems. And this work, in a way, started kind of quite, remarkable developments. In 2024, there has been several quite advanced quantum error correction experiments, for example, in Quantinuum with trapped ions, also with Google, most of you have heard about. And actually, this work, these initial experiments, resulted in new theoretical development. For example, it turns out that by properly structuring the circuits and using the so-called transversal gates, you can actually outsource a lot of the quantum error correction from the classical device to the from a quantum device to the classical coprocessor. But also, one can use this ingredients to start doing some quite advanced quantum error correction demonstrations. So, for example, at Quera, we have realized the first magic state distillation, which is actually a very important ingredient of the scalable quantum computer. So this magic state distillation has been done on this Gemini class Quera's machine. And that kind of shows a little bit of evolution. So this is our kind of legendary Atomary lab at Harvard. And this actually is a Gemini system, which actually has been delivered to ICE. It's a Japanese NIST in the spring last year. And actually, we really use it. So it is situated in a data center, which we've kind of NVIDIA, next to NVIDIA GPUs, and we actually use it as a really development platform. So we collaborate with a number of companies to really sort of use it as a prototype of both kind of physical but also logical quantum processor. So fast forward, 2025 was also a very special year. And so what we have done is basically we took all of these ingredients and started putting them together into the first complete architectures, which can do this kind of deep circuit fault-tolerant algorithms and start kind of exploring the applications. So to do that, actually, you have to satisfy a number of requirements. So first off, you have to be below threshold to suppress error. You have to operate efficiently on logical qubits. I already showed you that we can do it. Most importantly, you have to do things, such that you can enable universal computation. This is non-trivial because logical qubits basically are digital, and normally quantum evolution is analog. So it's actually building the analog evolution with digital precision is one of the most remarkable things that quantum error correction can do. And even more importantly, what you have to do, you have to build the systems which can remove the entropy during the computation. That's maybe the most important element of the quantum error correction. And so basically, in this work, we for the first time really put all of these elements together. So it's actually quite advanced, and I don't really have time to talk about it, but for example, we demonstrated operation factor of 2 below quantum error correction threshold, which already used quite advanced decoding using machine learning. We have operated efficient quantum logic and first universal operation, and in particular, we implemented this kind of deep circuit algorithm. So I will illustrate it here. So basically, what we are doing here is essentially building a circuit by encoding information into these logical qubits, entangling them, and then measuring some of them, and basically through quantum teleportation, moving the information to the qubits which are in a storage zone. And after this measurement, what we are doing, we are basically resetting the qubit. We correct the errors, we detect errors, correct them, and we reset the qubits, recool the atoms. So this is, by many measures, the most advanced quantum circuit which has ever been implemented. So it actually realizes the cluster state from 96 logical qubits. Is using this quite, what's called high-rate code, where in one block you can encode, many logical qubits. And basically, what you see here, these blinking dots, is where we measure the atoms. Where we kind of detect, the errors. We detect if atom was lost, and then reset these atoms, while the upper block here is stored. And then basically, what we are doing now, we are starting to again re-entangle atoms. First, create this correcting code, then entangle in one-dimensional cluster state, and then basically bring the other one, entangle in two-dimensional cluster state, and then this procedure operates for many cycles. And basically, what we can do here is we really can maintain logical error rate to be very, very low, up to like over 30 cycles. And in fact, the fidelity with various kind of tricks can be actually very, very high. So if you kind of follow this talk, you will realize now that, in some interesting way, what quantum computer is actually like a big refrigerator. So on the surface of this refrigerator, there is this very pristine, very nice unitary evolution of the quantum states. But beneath it, there are all of these machinery to detect errors, correct them, kind of remove entropy. And basically, this demonstration includes all elements with one exception. One exception is that, basically, as we do this circuit, the atoms get lost. So we actually refill them from the reservoir. But the depth of the circuit is limited by the size of reservoir. At some point, we run out of atoms. And that's where the computation here has to stop. So this refilling reservoir is something we addressed in a separate system in which we have demonstrated that we can basically continuously operate atomic processor with over 3,000 qubits. So the idea here is we basically separated atom preparation, cooling, and the kind of processor zone. We just bring fresh atoms, all the time, and constantly refilling this kind of these lost atoms. And basically, this way one can really sort of proceed. The computation can proceed, indefinitely. So I hope to convince you that I convinced you that large-scale quantum computers can be built. The bigger question now that the field will has to confront is what we can use them for and how can quantum computers really change the world. So we as a community have a lot of ideas. So one candidate problems will be difficult problems which can be solved currently, but solved inefficiently. And then there are some kind of impossible problems which people really don't know how to solve classically. And but I mean there is really kind of still a big question. So how we can what will be the most impactful application. So I would like to give two examples, kind of related to the theme of this Quantum Summit. The first one will be the application of these quantum machines to do quantum simulations. So one example which I would like to feature here is the quantum simulation of something which is called Kitaev model, which is basically a model where you have highly anisotropic interactions between spins in this kind of honeycomb lattices. So this is a model which was proposed over 20 years ago, and in fact resulted in a field which is called Kitaev materials. But in fact, this model and basically the physics of this model has never been up to now probed experimentally. So the way how we realize this model is very simply just taking one sublattice of atoms and moving it around and basically in between switching kind of the basis, and that way we can realize this highly anisotropic interaction, and with that we can create, for example, some very exotic states like non-abelian spin liquid. We can, probe excitations, which actually fermions here. You can study, for example, fermion dynamics and verify, Fermi statistics. And one can also simulate digitally this famous Fermi-Hubbard model. So this movie shows you how this is actually done. So we first prepare this kind of entangled canvas state by using ancillars to basically, make, kind of stabilizer measurements. And then afterwards, what we do, we start this evolution, and basically, in this way, we create this non-abelian spin liquid. So it turns out that this kind of procedure can be generalized to realize, for example, non-local fermionic circuit. And what's really exciting is that one can really use it to study strongly interacting dynamics on this kind of digital quantum computer. So there are opportunities for simulating complex materials, chemistry, lattice gauge theories. But I think perhaps the most exciting component is that these kind of quantum simulators can be integrated with the advanced quantum classical algorithms like DFT, various machine learning algorithms. I think Matias will talk about it, but we actually, in terms of building the systems, will really come to the point where these things will become useful. shifting gears and having in mind that Cisco is interested in quantum networking, I would like to actually mention one exciting quantum networking application. And this is an application to non-local quantum sensing. So suppose what you would like to do is, for example, image a far distant star, and the kind of conventional method is to have a telescope or maybe telescope array, which consists of several receivers, and separating these receivers is good because this improves essentially the resolution of these telescopes. However, imaging, in particular in the optical domain, with distributed receivers has some challenges. And kind of essentially the challenge is the following. So to get the optimal sensitivity, you have to essentially interfere the photons which arrive from the stars directly. So you have to basically bring together these two paths, and eventually interfere them. So this is challenging for large distances because, for example, on the ground, there are losses kind of in the fiber. So there are, of course, other techniques you can use, which are so-called local detection techniques, where you can, for example, use local oscillator. But in the limit when you have very few numbers, so this mu here describes the kind of a photon number. So if mu is very small, these kind of local techniques actually have provably worse signal-to-noise scaling. And so the idea, which was suggested, more than a decade ago, is if you start with kind of entangled nodes, or if you use entanglement to basically teleport the quantum state from one node to another, you can actually effectively recreate this, kind of non-local sensing situation, without being circumvented by things like losses. So basically, what this non-local entanglement essentially enables is, in practice, enables something which is called non-local heralding. So you can basically detect that the photon arrived, without knowing in which of these nodes it arrived, and it actually erases kind of which path information. So to realize it in practice, it's actually important that you need to have entanglement which was created prior to the photon arrival. So you need to have some memory, you need to have some networking capability. And in a very recent experiment, we actually, for the first time, demonstrated this type of operation. So actually, this experiment uses atom-like system, silicon vacancy centers, but it's actually not so important here. And in fact, what we see is by using entanglement, we can increase the visibility of this kind of non-local interference. And in fact, these stations can be separated now by kilometers of fiber. So what's very exciting is that if you can take this kind of basic demonstration and combine them with these quantum processing units of the type that I described, is actually in this case you can use quantum algorithms to actually quite dramatically enhance the sensitivity of, for example, like receiver array in a weak field regime. And in fact, one can really apply it to practical imaging tasks, for example, detecting, small, faint objects on the top of the kind of big star. The key idea here is you really have a memory advantage. So you can basically, you do not need very many photons to basically, for example, separate the point spread function of these two objects. So this really motivates, developing, networking techniques and integrating them with the quantum processing units. And in fact, this is a work which, in the case of atom array, which is already underway in our labs. And the idea here is to use essentially atom transport to start to move atoms from this quantum processing zone to the zone where you have this kind of efficient interfacing. And in fact, we have some very early results where we can actually integrate atoms with very good optical cavities. And we also have some exciting new developments showing that we can scale this technique at least to thousands of channels where we can do this kind of operations in parallel. So I hope I kind of convinced you that we are now living in a very exciting time. So I must say, as someone who has been in the field for a couple of decades, for us, this is a very, very special time. So this kind of dream of really building a utility-scale quantum computer for the first time, I would say, is really in direct sight. And so one could envision now paths to systems with hundreds of logical qubits, part per million error rate, but already there are new ideas. There are these new error-correcting codes, called QLDPC codes, which really would kind of very rapidly, move the systems to thousands of logical qubits and, quite low error rates. So to kind of give you a sense that we are really entering new era, this is almost now a legendary drawing that the students, it's actually is a diagram of first logical GEG state realization. So each line here is a logical qubit, not a physical qubit. And I think this really marks a transition to something very special. So the field now is in a very special point and a very special time. So we are still in the age of this quantum discovery and using machines for scientific applications, but we are entering a new era of the scalable, fault-tolerant devices where new applications and eventually new products can be foreseen. So with that, I would like to thank all people whose blood and sweat resulted in this work. This is my research group and also Team Quera. And I would like to thank you for your attention, and I'm happy to take any questions.
I guess I know we are running slightly behind, but maybe one question from the audience, please.
What is your biggest concern?
Just 1 second. Let him get the microphone, please.
What is your biggest concern about seeing success in this area?
So I maybe will mention two. So one, I believe at the component level, we have really demonstrated all components which should allow us to scale to large system. But kind of integrating the system, basically a system level integration, this is something that, at least at this complexity, no one has ever done, And that's, I would say, is the key challenge, at least, in our case, So that's concern number one. And the second concern I alluded already at the end of my talk is what are we going to use these things for, right? And I think there are a couple of maybe examples of high impact, but quite specialized applications. And this application challenge, I think now is emerging as a challenge number one. And in light of that, thinking about quantum computers, not just as computers, look, these are just new types of instruments, Of course, they can be applied to computational tasks, but thinking of them in a kind of broader sense, for example, integrating with networks, integrating with sensing. So this thing which I presented at the end is a real use case where, if you have quantum-limited, weak field sensors starved for signal, quantum computers can help. And I think these kind of things will be very well nourished as a very, very special application.
Right. Let's thank Professor Lukin for this amazing, insightful talk to kickstart the session. So we are transitioning into the second session. So this concludes basically the opening session and opening remarks and keynote. Now we'll be transitioning into the infrastructure and technology session. We have 3 talks with a break in between from Microsoft, IBM, and NVIDIA. So amazing lineup. Our first speaker, true veteran of the field, whose work actually spans the gap between complex many-body physics and industrial systems architecture, Matias Troyer. So he's a technical fellow and CVP at Microsoft, and he was a former professor at ETH Zurich and a recipient of the Raman Prize for his pioneering work in numerical simulations in many intractable areas of quantum many-body physics. He's also won the Hamburg Prize for Theoretical Physics, and he now leads Microsoft's efforts in building quantum systems for real-world utility-scale quantum computing. And please welcome Matias for his talk on quantum system architecture for utility scale.
Thank you. So this is supposed to show the next slides here. Okay, it's coming. Yeah. Thank you. So you heard from Nemish in a great talk kind of where quantum is making progress. We're getting to the bigger machines, better one, logical qubits, and so on. There's real progress. And what we want to do is we want to build the utility scale, the quantum computer that can solve important problems that we can't solve classically. And so the great news is that while computing has improved over the last 5,000 years, the fastest GPU we have today works on the same principle as the abacus. The way we compute has not changed until now. With quantum computing, that is changing for the first time. And with that, there's lots of hype around. Quantum will change everything from your cell phones to the stock market and more. But we now are getting clarity. There's clarity on what will be the applications where quantum can help the most, and clarity what is needed to get there. And with that, our focus is on utility scale. And utility scale, I used to define as I want to solve an interesting science problem with quantum hardware that I cannot solve classically. So that would be my goal, a great paper where I solve a certain problem that I can't solve classically. But working for a company, I need more than that. And what DARPA then pushed us to is said, look, actually, if you build that in a big machine like CERN, something big, we're building for billions, and we write the paper, get the Nobel Prize. Okay, that's all fine, but that will not make it a real commercial success. So DARPA defines utility scale as being able to solve a problem where the value of the solution exceeds the cost. So if the machine costs $1 billion, then nobody might buy it. If it's cheaper, then yes. And so my chemistry colleague said if the calculation of some problem costs a few $1,000s per molecule, yeah, they'll use it all the time. If it costs $1 million, no way they want to use it. So cost is also important for utility scale. But then let's start. First of all, quantum computers need quantum speedup, meaning that the scaling with problem size for an algorithm has to be more lenient and better than classically. That means when the problem gets large, the quantum computer will win. But when the problem is small, the classical one will win, simply because the classical computer has a faster clock speed, is cheap and easier to build. So there's a crossover here. And we need that crossover scale to be small enough. If the calculation takes 1 million years, nobody will use it. If it takes a few hours or days or maybe weeks, then yeah, then we're in business. And with that, we looked at problems years back and found that some have a crossover time of 1 million years, 1 billion years, and others had one of ours. And then we thought, kind of, what could be the principles that let us decide where the promising applications are. And for that, you need more than the scaling, because all quantum algorithms with quantum speedup will beat the classical computer asymptotically. But we need to beat it for a small enough problem in a short enough time that it becomes interesting. For that, you need more than scaling laws. For that, you also need constants. And so we need to make assumptions. And the assumption we make here is, on the quantum side, a really optimistic view. We're getting 10,000 logical qubits with a logical cycle time of 10 microseconds. That's many, many more than we have now, but that's something where I think if we can get there, I think that would be exciting. So that's kind of what we can build maybe in 5 years, in 10 years on the quantum side. On the classical side, I'm taking a pessimistic view because I'm the quantum optimist. I want to be good for quantum, so I'm saying I take a single H200 GPU. And compare that. What can it do on that one GPU today, not on the thousands in the data center, but a single GPU compared to a future quantum processor? The first thing you see at the bottom is the I/O bandwidth. The I/O bandwidth, what it can load into the quantum computer, is at most a gigabit a second, because it can do at most 1 billion operations per second. So I'm limited to about gigabit a second for the I/O bandwidth on the quantum computer, while the classical one, the GPU, although it's limited by I/O, can load about 40,000 times more. So quantum computers will not be good for big data problems, despite one hearing that sometimes. They will be good for big compute problems. But for the compute even, the GPU these days can do about 2 petaflop of compute. If you wanted to do the same operations on a quantum computer, the same 16-bit floating point operations, I could code about 10 kiloflop. So the quantum computer is about 10 to the 11 orders of magnitude slower per operation, but it does few operations. Why is it slower? Simply because it's much more complex, as Misha showed. You have the laser tweezers, you move around, or the control pulses, you do the error correction, and the machine is slower. So just fault-tolerant quantum operation is 10, 11, 12 orders of magnitudes more costly than a classical operation, but I'm doing fewer. And so now that can be the basis of deciding which applications will win. Because you need an application that has a quantum speed up, a scaling advantage that overcomes the 10 orders of magnitude difference. And that means we're looking for problems with an exponential quantum speed up. These are problems in cryptanalysis. Shor's algorithm breaking code, okay, that's not what one wants to run, but that means we have to harden our crypto. We have to replace our networking hardware by one is supporting the post-quantum crypto. The applications that we see clearly with the exponentially speed up is in simulating quantum systems, as Misha also said. So these are simulations in chemistry, three new molecules, reactions, getting the catalyst for the carbon fixation, green chemistry. Will be new drugs, new materials. Now, when I mentioned that to my team, one person said, now he's disappointed. He wanted to join the quantum program to change the world, and now I tell him the only thing it will be good for might be chemistry and materials. But that's when I say that 96% of all manufacturers' goods rely on new materials, on the new chemistry. If we can really simulate and design materials in chemistry, that will change everything. But it will do that not alone. It will not be just quantum. It will be quantum computing combined with classical supercomputing and with AI. And we can start now, because what we've seen is we can design new materials in days or weeks. So within 1 week, we scanned 32 million potential candidates for a new electrolyte and found one that worked. Doing that with the HPC would have taken 20 years on the same machines. What we do there is we simulate the models with classical method, the HPC. We use all the results to train an AI model, and then we use that model to predict the properties of new molecules and materials. But that is only ever as accurate as the classical simulation we did are, and that's where classical simulation of your quantum systems are limited. So, and the complexity of the classical calculation grows rapidly when you need more accuracy. If you start on the left and I want just the structure of the material, if I just want how a protein folds, a crystal structure, I can do that just using effective classical force fields between the atoms. So that works well on big systems, protein folding. Basically, it can be done with an HPC. If you want to look at exactly how molecules dock, for example, a bind, then you need a little bit of quantum physics in there. There are semi-empirical methods. Then the scaling becomes quadratic in the problem size. If you want to understand the electron densities, the polarizations, and more about the electronic structure, you can go to density functional theory. That's the mean field, the method that looks at one electron quantum mechanically fully in the average potential of the others. That works well for certain problems. If, however, you want to look at chemical reactions, how photons interact with matter, how chemical bonds break and form, how things react, then the electrons become entangled. You break a bond, you form a bond. Then you have to accurately simulate the many-body quantum problem, and that ultimately scales exponentially with the problem size. So here we're getting a problem for chemical reactions that are exponentially hard, classically. And that's where quantum computer comes in and helps us, because in a quantum computer, the same thing can be done with about cubic scaling. Those are problems where with quantum computers you can simulate with much higher accuracy than you can do classically. And that's especially important for chemical reactions, synthesis or metabolism in the body of drugs and so on. So that's where we need quantum. Now, people have asked me in the past, can I accelerate protein folding with quantum computing? And my answer was, no, it can do it well enough classically, but I can accelerate it with AI. What was shown with AlphaFold. We can actually fold it better with AI. So with AI, we make things faster. With quantum computing, we make the calculations more accurate. And what happens if we combine it? If we combine it, we make it faster and more accurate. Because it can now take the models that I've trained on the classical data before. They worked so well, for example, for the batteries. And they can now refine it for those molecules, for those configurations that become important during the chemical reaction, where those models break down. That's why I'm adding in extra simulations based on quantum computing data. And I'm using the results of the quantum simulations to refine the model. I have a foundation model trained on the classical data. I refine it, make it more accurate with a small set of quantum data. And then I get a new model, a quantum trained model, trained on quantum data, that will be accurate and predictive. The key thing is, no model can ever be better than the training data. And if I cannot solve quantum systems accurately on a classical computer, then I can't train AI. So one colleague once told me, hey, Matias, I think what you're trying to say is we'll build a quantum computer to teach quantum physics to an AGI. So yeah, that's it, ultimately. So if you need new materials for the networks, quantum will help you. Now, what we need there, we need more than the noisy qubits we have now. We need to get to problems with, or to machines with hundreds and thousands of reliable logical qubits. And that's a journey. And the step we're now, Misha showed this, we're in the phase now what we call level 2. We're building the first logical qubit. We've left the age of the physical qubit bits, the NISQ machines. We need to go towards scale with logical qubits. And we have the first ones now. So Misha showed some data there that we've shown 4 logical qubits on the ion traps from the Continuum 2 years ago. Then showed 12 logical qubits when they upgraded the hardware. Then November of 24, we showed 24 logical qubits. And with our partner Atom, we're building a machine now with 50 logical qubits that we've sold to Denmark, and that we will deliver later this year. So we're clearly in the phase of logical qubits. What we want to aim for is scale. And for scale, the problem, as Misha mentioned also, is the integration. How do we actually control the qubits? We have the qubits now. The problem is, how do we scale it up? How do we integrate it? How do we control it? And how do we build a system around it? And while quantum computing is fundamentally new at the level of the qubits, for building computer systems, we can learn from decades of classical architecture. Quantum computers will be another class of accelerators. So I can build the quantum data center in the same way I build my classical data center. I have the same stack of the architecture. On top, the hyperscale workloads, the developer tools, I have my cloud services, the fabric of the data center, and then the hardware. So the workloads, these will be problems in chemistry and other problems, working with the AI, with the Copilot, based on libraries and models, using developer tools like Git, the GitHub and Copilot, and so on, running in the cloud. And what we'll do is we have many different SKUs already now in the data center. We just add one more. We add a quantum accelerator in addition to the standard SKUs we have, the HPC SKUs, GPU ones, the large memory ones. We'll add the quantum SKU. And then how do we build this quantum accelerator? There again, when you look closely, and we thought through that for years, you see a clear similarity between how you build the quantum computer and the classical one. On the top, in the high-level language, we write the applications. We compile it down to an instruction set architecture. And then the translation of that from the logical qubits to physical qubits to control pulses is very similar to the microarchitecture of a classical CPU. And so we can learn a lot of all the challenges we have just by looking at what is the classical architecture that was solved for classical problems and using that for quantum computers. And so, Misha, we are not building a von Neumann machine, we are building a Harvard architecture machine. And the difference is the Harvard architecture stores the instruction in different memory than the data. And I'll not store my quantum program in qubits. I store it in classical memory. So I think it's Harvard, the architecture, like where you're from. So, but then what we build here is, again, we build the operating system that handles all the scheduling of the code, that runs the classical execution. And then, like we have the micro architecture, Okay, so we have on top the quantum OS and the drivers. In the drivers, there's a different driver for every piece of quantum hardware. It can be the same OS, like Windows that you have, that runs on ARM CPUs and Intel and others. And it works with many printers and other things. So there will be many drivers for different type of quantum hardware with it. Then we'll have in it a classical CPU for the classical code. And we'll have the quantum processing unit that has first a quantum engine that does the quantum error correction. We call it the qubit virtualization system. It does the bring up, the control, the readout, everything. That's the microarchitecture of the classical CPU. And then underneath it, there are the qubits. And so you asked before, what is really the most challenging aspect? And the most challenging aspect is really doing that control and readout at scale. Because if we have 1 million physical qubits, and we operate it at a megahertz frequency, we're doing 10 to the 12 or a tera operation per second. I'm getting a terabyte in measurement data back per second. Okay, that doesn't scare networking people, but you know it's challenging to build. So we have to do the same with data coming from qubits and controlling it at the same scale. And that's where we like the topological qubits ultimately. And the reason for that is the topological qubits are ones that allow to do all the important operations be done by voltage control, by simple digital voltage pulses. That means I can control it with a transistor. And if I have to do 10 to the 12 operations per second, 1 trillion operations per second, and I want to do it in a cryostat where I have a watt of power, then switching a transistor is about a petajoule. And processing 10 to the 12 bits of data, you know those switches draw power. So here, because it's just a few transistors need to switch to control the topological qubits, that's where I think that's something that I can build at scale with cryogenic CMOS at low power. So that's why we like the topological qubit. But the biggest challenge that I see is really, I think, the same challenge that Cisco faces in networking. If you have a 100 terabit a second network, you have to actually do all of the signal processing of the data that comes out. It comes in analog with light. It goes through a photodetector, ADC, signal processing, error correction in a small package. We'll have to basically do the same thing for the qubits. So, and building that, I think, will be the big challenge for engineering. The rest of the system, I think, we have under control. So what will it then allow us? It allows us to solve utility scale problems. So let me just end with a quick outlook. What I can do if I have an AI model for chemistry materials that has been trained on quantum data. It lets me design a molecule, a material with specific properties, and what comes out of the model, I type into my Copilot or ChatGPT, design a material with these properties that I need for my product, and boom, it comes out with something that works because the model is accurate and quantum trained. But having a molecule or material is not enough because you need to find a way to synthesize it. That can take years to find how can I make it. But then because I can simulate reactions, I'll ask the AI, please also tell me how to make it. And then when you have it, there's the life cycle analysis. How does it interact with the environment, with water, with air? How does it degrade over time? Will it become toxic? Will it burn or whatever? There's also what we can predict there. So just having that vision of AI combined with quantum can let you really do those things before you go to the lab, that can really change manufacturing and the industry. Thank you.
Thank you, Matias, for this very insightful talk. I'm super glad that you actually sort of also touched upon the synergies between AI and this is sort of coexistence. So we have time for maybe one question from the audience. Any questions from the audience? Yeah. Can you, 1 second. Can you please pass on the microphone?
What is your prediction for the time frame to actually see some success?
So I think within the next 3 years, we can build machines that will be really interesting, that can start solving interesting problems that I can't do classically. We can start combining that with AI, so that's where it will start. And then it's a question of scale, and that's where I say let's move fast to post-quantum crypto, because the threat might come faster than we thought.
One more question.
Thank you very much for your talk. So I have a question. When you mentioned about, you combine AI and quantum,
Yeah.
and your belief, because with chemistry, if the agent of AI trained with quantum data.
Yeah.
But my worry is because, quantum computing is still slow, as your talk, right? So even generating this data, and because AI needs a lot of data, and how we can generate such an amount of data, and also how to store it, because we don't have quantum memory.
Great point. Okay, so what I need here, so the problem is quantum simulations will be slow. A molecule might take about a day for us to simulate, and if that's a big machine that fills a data center and they get out 1 data point per day, that will be hard and expensive, right? So we need machines that are compact, hence I like the topological qubits. And I think one can also do atoms slightly more compact and build it that way. But I need something that is small enough that in a data center, and don't just build one big machine, this network, but I build many machines, a big cluster of them. That way I can generate enough training data fast enough. But then the key thing there is, so I still want to combine it with AI, because brute forcing it will always be slower than AI models. Now, how can I make the AI models? If I were to train it all from ground up with 100 million data points that come from quantum computers, then there's no way, as you said. But what we can do is we can start with a model that has been pre-trained on classical data. That has been pre-trained on DFT calculations, like we do now, and that can already do a lot. There are certain things where it's not good enough, and that's where we've shown that just with a few thousand highly accurate data points, you can really make the model better. We've seen in many cases in AI, when you take a pre-trained model, fine-tuning with a small data set makes it much better. And we've shown the same can be done here. With about 1,000 or 10,000 data points, we'll get a model that is much, much better. So that's the key. You use the quantum data to just refine the pre-trained model. And the data we need is typically just energies for chemical reactions. That's a classical number. So I do it. The output of the quantum computation is the energy of a certain configuration. That's classical data. And that's what I use to train the AI model. From that I get the structure, forces, and other properties.
I think we should probably, in the interest of time, move forward. But this is a line that we will probably touch in the panel as well. So please reserve some of the questions for the panel, because this is a fascinating topic. I have a bunch of questions myself.
Thank you.
Thank you, Matias, once again, for the wonderful talk. So now we are moving on from system architecture to the specific hardware challenges of scaling, and for that we have Dr. Jason Orcett from IBM Quantum. As a principal research scientist, Jason is the architect behind IBM's efforts to connect quantum modules using superconducting cables, which are also known as L couplers, I believe. He's currently leading the department focused on the gate and readout performance that will define the next generation of IBM quantum systems. Jason, the stage is yours.
Thank you for the opportunity to be here and talk to you today. It's my pleasure to represent the team at IBM. And I'll be talking, I guess, the third non-Cisco speaker and the third qubit modality, which is rather reflective of the field today. And I'll be talking about our vision towards large-scale fault-tolerant quantum computers. So this isn't a journey that's starting now. It's actually 10 years that we've been actually having public-facing quantum systems on the cloud. Some of those were very early systems that were very early technological maturity. But in the past few years, we've had over 25 of these systems be more than 100 qubit systems that can run more than 5,000 2-qubit gates. And this has given us a lot of experience to define our path forward. To make this a little bit concrete, the kind of main processor that we have on the cloud today is called Heron. It's basically fixed frequency transmon qubits. These are superconducting qubits that are connected in a fixed circuit architecture by tunable couplers. And the kind of ball and stick level diagram of the hardware that I'll be talking about throughout the talk, and I'll try to make it light on the hardware details, is shown at the example at the bottom. Qubits are represented by coherence times and lifetimes. The connections between the qubits for 2-qubit gates are characterized by randomized benchmarking experiments. And we would attribute all of the error in the error per Clifford to the 2-qubit gate. This is an example of one of the best 2-qubit gates that we have from the Heron systems, which is around 4.7 times 10 to the minus 4 in fidelity in these 2-qubit gates. The exact details of our systems, daily calibration, you don't need any account, you don't need any relationship to IBM. You can go online to our cloud website and see exactly what that is and what the performance is today. The performance needs to not just be the hero qubit pair on the device. So we have a metric that we call error per layered gate, or EPLG. And in this case, at 100 qubit scale, when we see the kind of decrease of the error over time for these systems approaching the low times 10 to the minus 3 infidelities. And notably on these recent systems, if you look at the 2-qubit gate pairs, 57 out of 176 of a recent device, the 2-qubit gates have an error per gate of below 10 to the minus 3. Now, the quality of that 2-qubit gate fidelity is just one axis. We also care about the speed. We need to typically run a lot of circuit instances to get a valuable result. And that speed comes not just from the fundamental hardware, but the software stack supporting it. So we have a metric that we call circuit layer operations per second that we track, or CLOPS. And this is an example of improving the software stack for a given set of physical hardware, of increasing the circuit layer operations per second, depending on how you measure it, over a factor of 110 to a few 100,000 of these of CLOPS in our recent systems. But the hardware is not staying static. We're introducing increased qubit connectivity. So the first kind of processor that I showed you, called the Heron systems, it's a heavy hex. It's a relatively sparsely connected system between 2 and 3 degrees of connectivity per qubit. Nighthawk is on the cloud now. This is a square lattice where all the qubits in the core have 4 nearest neighbors. And we're able to make that change while actually improving the coherence times of the qubits that make up the processor, while still keeping 2-qubit operations in the low times 10 to the minus 3 for this first device that we've made available to clients. But the journey's not going to end there. I think as we've heard, the trend and the needs of the systems are going to keep on growing, and that need is going towards fault tolerance. So our 2 data points that we build towards is Starling in 2029 and Blue Jay in 2033, where we're looking at going from the kind of 5,000-ish and more 2-qubit gates in our circuits to 100 million and a billion, and having the logical qubit count go from 200 to 2,000 with an internal benchmark of, say, a factor of 50 larger physical qubit counts. So I'll talk a little bit about the realization of this new fault-tolerant architecture. I'll talk about scaling the system, and I'll end with some discussion of achieving useful computational results in these systems. So to start with the code, we have to go from a code to a system. And there's a lot of criteria that you need to look at for a code to be useful for building a quantum computer. So first of all, this has to be fault tolerant, that you have some degree of logical errors being suppressed. You still need the qubits to be addressable, and you still need to have the connections and the operations between those qubits to achieve a universal gate set. Additionally, you want this to be an adaptive system that can run in real time, ideally modular and efficient, such that we can build it at a practical cost, because the cost at which we have to build these systems is obviously a very practical constraint. So in the past couple of years, there's been really amazing work from the theory team that I take absolutely no credit for. I stand back and watch these guys produce incredibly impressive results of going from the idea of a code to an architecture to utilize that code for computation, and all the way to a real-time decoder to be able to back out what the logical errors may be in the operation of that quantum system. The way I view this at a sketch is kind of in this cartoon here, where you would be having an array of modules. The array is just a simplicity of representation. There's a number of reasons why you don't want this to just be a simple linear array, in which each module is either going to have a magic state factory or is going to be comprised of a quantum memory and a logical processing unit. And generally, we talk about connecting these within a set of quantum interconnects, ideally within a contiguous cryogenic system. And together, this is going to represent a universal poly-based computation architecture. What has made us very excited and optimistic of the future is that this comes along with an order of magnitude reduction in resource constraints compared to when we were thinking about building these systems with a surface code. The system is modular with very well-defined connections, but there's always a catch. And the catch is that really significant new hardware capabilities are needed. And I'll talk just a little bit about what that means to be able to implement this. So our packaging by which we build our quantum processors today is already incredibly sophisticated. It looks like a CMOS chip that has been optimized for quantum device performance, where there's a qubit chip, Rito planes, wiring planes, through silicon vias, multi-level wiring. And what is the limitation that we need to move beyond is that in our traditional processors that we have on the cloud today, all of the interactions between qubits are adjacent operations in a single plane. What we've had to do is we've had to add yet more complexity into the stack, where we can have low-loss connections between the qubits to create high-fidelity quantum operations between non-neighboring qubits. We've pulled this together along with the gates that we need for long-range, high-degree, non-nearest neighbor connectivity. What I'm showing is basically some research device plaquettes that went into the device that we built this year, cooled down at the end of the year, called Loon. This is shown in a wafer on the right that was built using a 300 millimeter fabrication line at Albany Nanotech, where we benefit from 24/7 fabrication for cycles of learning. And in this facility, we've already kind of run 11,000 wafers. It's a large-scale effort. There's also a large-scale effort on being able to lay out these chips with non-trivial connectivity. So we have automated quantum EDA to be able to lay out such a complex device. And finally, in error correction, the state preparation and state reset is a really critical parameters. There's a new set of hardware capabilities in this device for high fidelity, rapid state reset. So this general blueprint is something that we're trying to scale. And IBM has spent a ton of effort all the way through our stack of building our processors to try to develop scaling technology along the way. So we've had 4 generations of classical control infrastructure. Today, that's moving towards cryo-CMOS. I'm showing a randomized benchmarking sequence using a cryo-CMOS ASIC controller with error per gate of 10 to the minus 3. We have interface in and out of the system. There are a lot of wires. I'm not going to lie to you. You have to control every qubit. This is something that a lot of people don't. One of the things that is obvious, but is kind of a hard switch that people have to think about when they think about a quantum computer, or at least how we're planning on building a quantum computer. Everything's controlled from the outside. You're not looking at like a flip-flop controlling another transistor. It all comes out. So we need high-density signal lines. There's a number of technologies that we have been developing to try to make this more scalable. And then we need to have modular and efficient cryogenics to cool this whole thing. So what I'm showing is the engineering plans for Starling. The energy costs are not trivial, but they're something that we view as achievable, of around 55 watts per qubit. So this is something that would be 2 megawatts of total power with the technology we know how to build today. And within this space, we need to be able to connect the quantum system. And this is something we've spent quite a bit of effort on. 10 years ago, we were really hoping that this would be optics connecting everything, but the physics there is really hard. So the number one current quantum interconnect that we're building towards is remote gates over millikelvin coaxial cables. We call this the L-coupler. So this is basically the combination of a physical attach and interface qubits to create a remote gate operation between modules. We benefit from some nice things. It turns out that Teflon, or low-density PTFE, has really low propagation loss in the single-photon microwave regime. And most solders are superconducting. So that's all things that benefit us quite a bit. We're looking at ways to extend this. There's a concept that we're generalizing, calling a quantum networking unit for our systems, in which we're looking at tunable qubit interfaces to local data qubits to various forms of external interconnect. Briefly, the types of interconnect we're looking at. The L-coupler is our internal front-up that's determining our engineering roadmap right now, which is this millikelvin microwave connection. We're looking at ways to extend this to more of a data center interconnect, peripheral interfaces to connect to things like sensors, and microwave optical transduction that we'd call T-couplers. We have wonderful partners in the space. Under the National Quantum Initiatives, we engage with Fermilab and Argonne, as well as our lovely hosts here at Cisco. So I'll end with talking about achieving useful computational results from these systems, which is the reason why we're building it in the first place. Besides the fact that as an engineer and a scientist working on it, it's just really cool physics and engineering. So if we want to talk about computation, we need to talk about software. So the software that enables our computers to interact with users in a productive way is Qiskit. This is an open source ecosystem for quantum computing. Characterized as having 3 layers: a layer of algorithm research, a layer for high performance computing, I'll expand on a little bit in this context of connecting quantum computers with high performance computing, and then the base layer for quantum information science. And this includes a software design kit for the kind of nuts and bolts of operating quantum circuits, and then the actual connection to the quantum computer, of which IBM Quantum is only one of many. We use a partnership with clients to operate algorithms and conduct research that's relevant to them on our systems. There has been a variety of publications. There's, we'd call it 95 plus, created prototypes with industry clients for their use cases of algorithms running on our hardware for either something that would be useful now or useful in the future. And so useful now is basically gets into a very murky topic of quantitative advantage. And we define this in kind of like two parallel paths. One is basically empirical explorations of, is this useful for a client thinking about a computational problem? And the other is attempting to be a rigorous exchange of the proof of an advantage of a problem for a computation, both classically and quantum. Both, especially the rigorous aspect of proofs of advantage, need to be done in the context of a community. Our attempt in this is to be partnering with external entities in a very transparent way in something that we call the advantage tracker. So there's expected to be a back and forth between, hey, I did this with a quantum computer. Hey, I have a better way of solving that with a classical computer. And this is a dialogue and an exchange that we hope will be productive. I want to end by talking just a little bit about one specific example of the way we view and think about the chemistry aspect of this, as it most directly ties in with the theme of connecting to large classical resources today. So in general, the motivation is in material science and predicting reaction rates. So very small uncertainties in the energies of the system result in very gross mispredictions of the reaction rates that are relevant. So really what we're trying to do, and what is the basis of a lot of computational chemistry, is achieving a higher accuracy prediction of the various relevant energies for chemistry problems. And the current state of quantum computers today require large classical resources to be able to work in concert to try to get to a useful, more accurate result. So the work at IBM Quantum, a lot of this is done in conjunction with Riken. The theme of engaging with HPC and partners in the space is true at IBM as well. And we have been looking at the Fugaku quantum computer in Japan, which is around number 7 on the top 500 list, and operating this in a closed loop fashion with IBM quantum computers. There's also been external partners working in this space for looking at high performance computing applications together with computations done on IBM quantum computers, in which you can look at the number of qubits, the number of 2-qubit gates, and then the classical resources required, to the point where we can look at a 2D scatter plot right now of quantum resources on the y-axis and classical resources on the x-axis, where the classical resources are getting to a day of a top 100, a number 1 on the top 500 list supercomputing performance. So in total, this forms the basis of our vision of quantum-centric supercomputing. I think in general, the trend of how do we have a quantum resource that plays in a non-trivial way with large classical resources for chemistry or AI is a trend that you've already heard today, and you'll probably continue to keep hearing. Again, we partner with those working in the field to try to advance this. So, in summary, I have tried to talk to you about improvements in LDPC error correcting codes and how this has shaped the IBM roadmap for how we're building our hardware. We've had to rethink how we build our hardware. We've built a number of qubit couplers to be able to build these codes. We have built scaling infrastructure alongside this development of our building blocks to be able to scale to the hundreds to thousands of logical qubit level to solve practical problems. And networking, albeit typically within the lens of computation, is the way we focus ourselves and orient ourselves, is necessary to be able to build up that scale of the problem, a scale of the system to be able to solve the problems, and then adapt and integrate in new applications. At the application level today, we're really leveraging the relationship with clients to be able to define what's useful or not useful, and then leveraging large classical computation to be able to organize quantum computing in the context of quantum-centric supercomputing. With that, thank you.
Thanks, Jason. I think we have probably time for maybe one question, and we'll take a quick break afterwards. Go ahead, Doug. Yeah, wait for the microphone, yeah.
Hey, thanks. That was great. So I have a very specific definition of quantum advantage, which is when can I start making money with it? And I guess, obviously it's related to your definition, but where does IBM see, or what is, in your opinion, where we're going to see the first, or I guess, useful, in my definition, applications of quantum computing and quantum technologies, whether it's an industry or a specific application?
Yeah, so just as a level set, also for the panel, I'm a hardware guy, right? So
that's okay. I'm a stats guy. I get it. But I like getting a paycheck, you know?
That's the worldview by which you're going to get an answer, right? I do work for a capitalist for-profit enterprise. People pay us to use our quantum systems, and someone pays me to build the quantum systems. So some of that is in the hope of those quantum systems improving, right? In general, I would say that in the near term, a lot of the back and forth for usefulness, if we're going to be defining that rigorously, such that you can really then turn around for whoever is the computational scientist at our client to be able to turn around to their CIO and say, hey, this is the justification by which we are paying IBM Quantum for access or for a future process, for a future kind of contract. That would have to be done around this back and forth for quantum advantage. I think when we're going to start to see a real differentiation where these arguments become clear, hopefully, are these fault-tolerant systems. And that is really this sort of Starling timescale for us, which would be 2029.
Thank you.
I think please reserve your questions for the panel because Jason and other folks will be in the panel. So with that, I think let's thank Jason once again. We'll take a 10-minute break just to stretch and refresh and maybe get some coffee or water, and we'll reconvene at around 11:10, 11:12. All right, thank you. I think we are starting the final talk in this session. I want to introduce Jin Sang Kim from NVIDIA. So he's a developer relations manager for quantum computing at NVIDIA. And with a PhD from Princeton and a background at IBM Quantum, he now leads the strategic alliances that are driving NVIDIA's accelerated quantum computing roadmap. Please welcome Jin Sang for his talk on accelerated quantum computing. Thank you.
Great, thank you. So my name is Jin Sang Kim. I'm from the quantum computing team at NVIDIA, and I'll be very happy to tell you about the work that we've been doing within the quantum space for the past several years now, and really work that we've been doing with the entire quantum ecosystem. So to start, NVIDIA is not building our own quantum computer. This is probably the first question people ask us when they ask us what we're doing in the quantum space. But very similar to what we're doing in the robotics space and the autonomous vehicle space, where we don't build our own robots and we don't build our own cars, but we work with every company in the AV space and we work with every company in the robotics space. We also work with essentially every company in the quantum computing space. And so our North Star here is this concept of the accelerated quantum supercomputer. This is the integration of quantum systems with modern HPC and AI systems. And the purpose for this is, our perspective, and I think many of the folks in this room's perspective, is that all of useful quantum computing will be hybrid. So we know that quantum computers will be very good at accelerating certain workflows in an HPC workflow. They'll be essential to solving problems that we can't solve today with modern supercomputers. But there are other workflows that still excel on CPUs and GPUs that we still need to offload work onto. And it'll be important for a future quantum workload to be able to do this in a performant and tightly integrated way. So there's a couple of reasons why GPUs and AI are very important for the success of quantum computing. There's many aspects of compilation and calibration and control and enabling fault tolerance where we believe GPUs and modern AI can provide immense amounts of value. And we can also leverage the supercomputer for things like pre-processing, post-processing, circuit compilation, circuit synthesis, many of the steps that a quantum computer cannot do on its own, but can be supported by a modern HPC center. Long term, enabling fault tolerance requires a decent amount of classical compute. So just for decoding a large-scale fault-tolerant quantum circuit for something like Shor's algorithm will likely require on the order of petascale compute. So this is not a trivial amount of compute, but it would be very, very good for us to be able to incorporate the modern compute that we have today and the infrastructure that we have today, and to be able to integrate that with quantum computing in order to make all of our endeavors successful. For us at NVIDIA, the developer ecosystem is critical. This is something that we've been investing into for many, many years. This is the reason why CUDA enabled the AI ecosystem to really flourish. It gave developers a platform to develop applications on the GPU, to leverage the GPU alongside the CPU and at scale, and to ultimately build the modern generative AI ecosystem as we see it today. So there are many benefits to enabling the ecosystem to using resources like Python, C++, and CUDA for things like heterogeneous programming. So there's a couple of reasons why we think AI supercomputing will be very useful for the development of modern and useful quantum computing. On the one hand, they're very powerful resources for doing algorithms and applications research. So by simply doing the applications research on a very powerful simulator, we believe that we can accelerate applications and algorithms research, resource estimation, understanding the effect of noise on our applications and algorithms, developing better error mitigation strategies, things of all sorts like that. In addition, simulation is very powerful for the design of next-generation QPUs, for error correction code development, but also for training AI models for quantum error correction, control, and calibration. In addition, when we actually deploy a quantum processor in an HPC center or next to a classical cluster, there's a couple of things where we think that GPUs will be very important for accelerating the development of quantum deployments. So things like real-time accelerated quantum error correction, doing the real-time compute with low latency and a cycle time that is rapid enough to actually decode the errors as they come out of the quantum processor, real-time AI-assisted calibration, control, and readout in order to correct for things like drift in the calibration of the system, but also for hybrid algorithms and applications where portions of the workflow still need to run on a classical HPC system, but other portions of the workflow will be offloaded to the quantum processor. So at the heart of our platform is CUDA-Q. This is our open source platform for programming a hybrid quantum classical system. If any of you are familiar with the CUDA programming model, this is what enabled the machine learning and generative AI ecosystems to really flourish and enabled the developer ecosystem to develop applications at scale. CUDA-Q is a very similar programming model. It enables the developer to program quantum kernels, very similar to one would program a GPU kernel. And so this is just a packet of information or instructions that gets executed on a quantum resource. This could be any one of the partner QPU builders that we've integrated with today, or it could be executed on a powerful simulator. So you'll notice that we partner with QPU vendors across the entire ecosystem. Our strategy is to enable the entire quantum ecosystem. You'll see QPU builders represented across the entire ecosystem on this slide. So one click down from Q is our set of primitives called QQuantum. So QQuantum are a set of libraries that are useful for accelerating quantum simulation of all sorts. So you'll see probably all of your favorite logos on this slide. All of your favorite frameworks are accelerated by QQuantum. So Cirq, Penny Qiskit, along with many others. So for things like application development and algorithm development and understanding the effect of noise on a system, it's very useful to do an accelerated simulation. And so by just offloading that work to the GPU, you can often get orders of magnitude faster simulation times. And this ultimately just leads to an increase in the throughput of your research, enables researchers to just get more done in the same amount of time. For us, simulation is very, very complementary to the development of quantum processors. The researchers using our simulation tools uses them because it makes their research better. It accelerates how fast they can understand a scientific system. It enables them to explore regimes that they weren't able to before. So very, very complementary. We think it's a very powerful tool for enabling quantum research. Finally, on the kind of opposite ends of the stack here, at the very highest level of our stack, we have a set of libraries called CUDA-QX. This is a set of libraries for quantum research and application development. The first one is called CUDA-QEC. So this is a set of primitives and building blocks for enabling researchers to do error correction development. So within this, we have a couple of pre-baked quantum error correction codes and decoders, all accelerated on GPU. There's a tensor network decoder. There's a couple of very nice tools that enable researchers to accelerate their research in quantum error correction. The second library here is called CUDA-Q-Solvers. This is more for applications development in fields like quantum chemistry and biology. So it's a set of one-liners that make it easy to develop quantum chemistry and biological applications. At the very bottom of the stack, we have a new architecture that we recently announced just a few months ago with the entire ecosystem. This is called NVQLink. This is a reference architecture for the low latency integration with an HPC center and a quantum processor. So this enables a very, very low latency connection between quantum control systems of all sorts, QPU builders of all sorts, and a GPU host that can serve as the real-time host. I'll talk a little bit more about the details of NVQLink in a couple of slides. So we're really proud of this slide here. We really see ourselves as the tide that is lifting all boats within the quantum ecosystem. We want to accelerate everyone's work. We're trying to work with everyone to accelerate their most important problems. We really, NVIDIA only succeeds when our partners succeed. So we're really proud of all the partners that we've developed in a pretty short amount of time in just the past 4 years. From quantum hardware builders, the quantum simulation frameworks, research centers, and quantum software and systems builders. So I'm really proud of this slide. If we're not working with you, we would love to work with you. We want to deepen our relationships with all the partners here. OK. So from our perspective, there's a couple of challenges from getting to the few logical qubits that the folks have demonstrated today to the thousands of logical qubits necessary for doing real useful work on a quantum processor. And the challenges here, just to name a couple, are in developing better quantum algorithms, developing better qubits, so using design tools and automation tools to understand the physics of our qubits better and ultimately design better and higher fidelity qubits. Quantum data generation, so in order to train frontier models for quantum computing, a major bottleneck is the amount of data that's available to train models that can actually give us useful information and do inference for things like error correction decoding. So generating quantum data at scale is a major challenge. Developing hybrid applications and actually implementing them on real systems today. And quantum error correction. We need to be able to scale to the thousands of physical qubits in order to do useful quantum computing on a fault-tolerant quantum processor. And so for all of these, we've designed a platform that can help enable all of these workloads and accelerate them. And so what I'm showing here are just a couple of representative benchmarks for the speedups that we're seeing for a couple of different workflows in each of these categories. And these are typical speedups versus CPU, but the nice thing about running things on a GPU system is that we can scale them out and get very nice scaling results. So oftentimes seeing many orders or several orders of magnitude improvements in performance. So I want to zoom in a little bit on our NVQLink architecture. This is our architecture for enabling the tight integration of various quantum computing systems with the control systems and integrating that into an HPC center. So we announced this a couple of months ago, really in collaboration with a pretty broad ecosystem of supercomputing centers, national labs, QPU builders, quantum control vendors. But really from the perspective of the supercomputing center or the supercomputer, in today's kind of zoo of QPU deployments at supercomputing centers, there's a pretty disparate kind of zoo of physical QPUs that are getting coupled to HPC centers. And these are typically very, very different looking from the supercomputing side. But what we want to do is to be able to encapsulate this into this concept of a logical QPU and really kind of have a unified specification that connects the HPC center to this concept of the logical QPU. So what we've done is built a software architecture and an open specification that gives us this concept of the logical QPU. We have a real-time server that lives on a GPU server, and then we've built a specification over an Ethernet connection, so RDMA over a converged Ethernet. So not an exotic connection by any means to enable us to connect to a wide variety of different QPU vendors and control systems. So just connecting this back to quantum error correction decoding, there's a couple of challenges that we think can be addressed by having a very low latency connection to a powerful classical HPC resource. And so for quantum error correction, some of the challenges here are the throughput, or the rate at which syndrome measurements are processed as they come out of the quantum processor. There's the reaction time. This is how long the QPU is spending as the logical measurement is being processed and decoded. And then there's the accuracy. And some of these can be kind of trade-offs with each other, where the accuracy may be bumped at the expense of the reaction time and vice versa. So at least one of these can be solved by parallelism, which is the natural solution on a GPU. So throughput can oftentimes be solved through parallelism, as shown by this very nice work from Rivalry. But what we can do is decode various layers of our syndromes simultaneously and just increase the throughput. And this motivates kind of why it's useful to have a GPU in the loop in a tight quantum error correction loop with the quantum processor. And so moving towards this, we recently also showed this pretty recent result with Quantinuum. This is Bring's code using Quantinuum's new 98-qubit Helios QPU. This is using an implementation of NVQLink in real time. This is using an off-the-shelf decoder that is in CUDA-Q QEC. This is just our LDPC decoder, our BP plus OSD decoder. And then the average decoding time, the median decoding time is about 67 microseconds with a budget of 2 milliseconds. So we're well within the time budget. And so what we've seen is about a 5x improvement in the logical fidelity with NVQLink and our QLDPC decoder. Okay, so I want to switch gears a little bit and just talk a little bit about some of our new simulation libraries. We now have libraries for polypropagation and stabilizer simulations in addition to our tensor network and state vector simulators. And we also have a library for simulating quantum dynamics. And all of these have really, really fantastic performance over CPU implementations. And really, what this enables for us and the entire ecosystem is a powerful set of tools for accelerating the workloads that you can simulate on for your quantum computing research. Recently, we accelerated 2 new frameworks. So one is QTIP, which of course is a very, very popular framework for simulating the dynamics of open quantum systems. So we're seeing several orders of magnitude speed up. We worked with the QTIP developers directly, as well as researchers at Sherbrooke and Northwestern. And then the second one is SE qubits, which is a very popular framework for the simulation and design of superconducting qubits. The last thing I want to show is this work that we did in partnership with NERSC. Well, really, they did most of the work. They were using the Perlmutter supercomputer just across the bay to do a full wave simulation of a novel quantum chip. So this is spatial EM simulation to simulate the propagation of waves through a novel quantum chip designed by researchers at UC Berkeley. So unfortunately, the animation's not showing, but it's available online. This used the entire Perlmutter system, which is about 7,000 GPUs, to resolve micron-scale simulations. So this is a really fantastic tool for just looking at the things like crosstalk and long-range couplings that occur as you're propagating signals through a chip. So you don't need to use the full supercomputer for this, but this is just really a demonstration of how scalable this problem is. So for other problems, it's perfectly acceptable or appropriate to use a smaller size system like a single GPU or just a small node. But they were able to use the entire supercomputer to do this really, really nice demonstration. Okay, and with that, I'd like to thank you for your time and take any questions.
So I think we have time for maybe one question, and then while Jin Sang is answering the questions, can I ask, can I request all the speakers to, like the panelists, to come and maybe start, just setting up the stage for the panel? Yeah, go ahead, please.
Yes, hi. Do you plan in the near future to provide first-class support for Rust in CUDA-Q?
So CUDA-Q is based on C++ already. If there's a strong need for Rust support, we can consider it. It's not currently in the roadmap.
Okay, thank you.
Yeah, please, Matias, Jason, Misha, and Resza, and Jin Sang, please. All right, I'm super excited about this. This is actually going to be a very interesting panel, hopefully. We've listened to all the great talks so far, and I have a bunch of questions to get started. But audience, please feel free to ask any engaging questions you may want to ask. To set the stage, this is a biased question coming in from Cisco, so I'm gonna start maybe from that side to really ask what you think is the role for quantum networking in scaling quantum computing systems. Maybe start with Jason and then Misha and Matias and so on.
So in the near term, we define a lot of things that look kind of internal to our system as networking, which is maybe not a fair way of doing that. But then connecting other sorts of quantum information to a quantum computer, I think, is one of the more interesting and exciting things that we can start to look for in the near term for what a quantum networking application would be.
I guess where I'm actually asking this question is, this is really in pursuit of the utility scale quantum systems that we care about, like hundreds of thousands of qubits to maybe even 1 million qubits, to where we are today. What is the role of quantum networking to really get to that scale? Is really where I was actually asking the question.
Yeah, so I think that this gets down to a little bit of a prejudice of how we think about building a system. And
Right.
Other people might have a different view of that, which is totally fair. But this sort of Starling or Blue Jay scale, 100 to 1,000 scale logical qubit system, that would be kind of within a overall coherent control architecture. There would need to be networking inside that. We have to be able to connect modules in a non-trivial way. I show it as an array. It's not going to just be an array. We might have more heterogeneity inside of that.
Right.
We will have more heterogeneity inside of that.
Right.
But we look at that as far as within the control system of decoding the quantum computer. That's the way we look at that scaling problem.
Gotcha. Misha?
Yeah, so at the end of the day, all the systems, scalable systems will have to be modular in some way. I think maybe an important question is what should be the size of the model, and the larger is the size, the more powerful in a way it is. So there could be two roles that kind of this quantum networking could play at a high level. So one is in the help of scaling. And so, for example, in our system, we believe that with this atom moving reconfigurable architecture, we should be, able to operate a single model at least at a scale of, 100,000, atomic qubits, or maybe more. So in that way, this kind of networking is not of kind of maybe direct relevance to scaling kind of in the near to medium term. But let's say at a level of millions of atoms, I could imagine that this networking could start playing a role. And at that scale, actually, networking, in particular, if you can do it in parallel, could be very, very powerful. But to me, what maybe the second part where this networking could play a role is really in enabling new functionalities of these machines. So, for example, I mentioned in my talk this kind of like network, quantum computing, enhanced sensing applications. This would have to rely on a network. Probably, okay, then maybe another example that we have worked on, and you might have seen our papers, things like blind quantum computing, where even things like quantum advantage has to be measured in a different way because you have to basically, do things in a secure fashion. So for these types of applications, I would say probably optical kind of networking will be kind of indispensable. So they are more naturally suited for, let's say, atomic and ion qubits, but I think there is some effort to develop transduction for superconducting qubits. So I think there are these two directions for different platforms. This will sort of be relevant different times, but I am very excited about this, like using networks to really extend the scope of applications of quantum computers, which I think could be a sort of maybe if not near-term, medium-term prospect.
Yeah, I think totally right. So, but in terms of actually just the scaling part, right? Based on your answer, looks like at least to scale to like hundreds of thousands of qubits, you don't see quantum networking as an immediate need. Yeah. Is that fair to say?
Yeah. So yes, the short answer is yes. Maybe the longer answer is that basically, I mean, at some point, there could be several paths to scaling.
Right.
And, they will sort of, like to evaluating each path, it depends on details, So I would say the very important kind of component, of what I was kind of talking about is our kind of ability to control, many atomic qubits in parallel with very few control parameters that's related to things like calibration and so on. So we do not need to calibrate individual physical qubits, which actually greatly simplifies tasks.
Yeah.
Even then, it's a super hard calibration problem. Let me just be very clear. But so basically, for atomic qubits, this kind of networking capabilities have been developed, including our group for maybe last two decades. But I would say this parallel networking is a really key kind of component. So if, let's say if someone magically builds a system where we can, now do parallel interfaces for, let's say, thousands of physical qubits, I'm not even asking about 100, but just 1,000 qubits, this will be useful, and potentially it can be useful also for scaling, to accelerate, for example, certain, tasks, maybe speed and things like this, So these are sort of complementary threads. So we do not believe that this is essential for scaling, at least in the medium term, but it can be helpful. That's maybe the way how to think about it.
Matthias, go ahead.
So there are two fundamentally different paths for reaching scale. One is scaling up, the other is scaling out. And we follow both. Now ideally, we'd like to actually have a single system that can go to negative 10 million qubits. And that's what we work on with the Majorana qubit. The other is kind of if you get two systems, terms like with the neutral atoms, 100,000, others 10,000, then you need to network them. But there, the bigger you can make a single module, the more qubits fit in, the less bandwidth you need on the network, the easier the network becomes, just like in a classical HPC. And so we'd like to always kind of make the modules big, because yes, in the end, I want to build a data center with 1,000 quantum modules, but then ideally there should be 1,000 or 100 quantum computers that can do 1,000 or 100 calculations in parallel. And they may only need to be networked than at the classical level.
Makes sense.
So the smaller the module, the fewer qubits I have per module, the more I need the network. The more modules I need, the higher the cost is. And for utility scaling, getting costs down, I want as large modules as possible. If the network is needed, then yes, then we want it. But I want to push the size of one.
I think I'll come to the polar opposite here. I think Resza may share a different opinion, but okay. I want to hear.
Yes. So I'd like to add, though, there's more that wasn't touched on, namely for security. I may want it for QKD, for defense in depth.
Sure. Those are different applications. For sure.
There might be more applications so in applied quantum computing, though there are some challenges there. Do I really want that somebody runs Shor's algorithm on my quantum computer without me knowing it?
Right.
There are challenges there and trade-offs about that. But yeah, there will be interesting applications for networking.
Your take, Resza?
I mean, to some extent, I agree, but also we need, Matias mentioned, I want to take his word on that. We need to learn from classical system. First of all, if we think about just two quantum computers or three quantum computers point-to-point statically connected together, I can kind of agree with what Matias said. But the way quantum computers I see that they are developing, all of them great. Some of them are faster reconfigurable, some of them are better decoherence time, some of them worse decoherence time. So I see that the network plays role in a quantum computing, future quantum computing would be multiple modality, because a circuit, if you want to optimize the algorithm, big algorithm, is gonna take advantage of different type differently. And then also the same way that you see that this modality of quantum computing is better because I can move, let's say, atoms freely everywhere I want. That was Misha mentioning. Or if compared to the other one that, for example, I need to do a neighboring entanglement and then just swapping and then go to do that. So if you have a network, which is a point-to-point, like you have a very static, you need to go one-to-one, one-to-one. But if you have a dynamic relationship between your quantum computer, then you can think about the whole quantum computer as a very reconfigurable circuit or as reconfigurable topology of the qubit connected. Then we come to that point, I agree with Misha that you need a large polarism there, but that gives you a several algorithmic advantage that just simply with a single quantum computer, with a single modality, you may not be able to get. I still jury out, but that's my view.
No, absolutely. I think we may be embarking on a similar journey that classical computing went through with scaling up and then eventually scaling out, because the economics and serviceability and reconfigurability and if you only have 10 modules, one module goes down, you're left with 9 modules, right? If you have 900,000 or like a million modules of smaller capacity, even if you lose like 10 modules, it's not a problem. I mean, the fragmentation, the granularity actually does play into some of these things. But no, thank you for the answer. So the second part I wanted to actually, I purposefully skipped NVIDIA because I know you don't have a quantum computer of your own. But this question is actually probably more, maybe I'll start with you. What's the most important role AI can or is already playing in terms of scaling and accelerating quantum computing? Let's start with NVIDIA and then go.
Yeah, so I can think of a couple of good examples where we're seeing really promising methods for leveraging AI for accelerating the timelines for quantum computing. The first, I think, most promising one is leveraging AI models for doing decoding in real time. So decoding is a pretty compute-intensive process, but one potential that we can leverage using AI is to pre-train a model, front-load the computation, and then just run inference when you need to do the decoding. So this is one, promising way. Of course, there's many challenges still involved in doing inference for decoding, error correction models. There's the scalability of the data required, but there may be ways of doing things like hierarchical methods or pre-decoding to lower those requirements. But we think that in order to actually just get below the threshold for the timing requirements, AI and running inference may be a very, very promising method for actually scaling quantum error correction. The other ones, I think, the DOE and with the Genesis mission are also very important, are using AI methods for algorithm and application discovery. So right now, there's a handful of known, exponential advantage algorithms that I think the entire application space is kind of relying on for providing, a rigorously known quantum advantage in the future. So there's a potential for doing some sort of AI, algorithm and application discovery, and there's kind of early work that's leveraging things like large language models for generating quantum circuits of interest that give you the properties of, say, a molecule. But I think that's also another very promising method. The third, I think, is for doing things like digital twins of quantum hardware itself. So within the classical compute world, of course, AI and CAE tools leverage, or rather CAE tools and EDA tools leverage AI methods for things like generating the next generation GPU design, or for generating the masks that are used for the actual lithography, things like that. I expect, as quantum systems scale out, these tools will become more and more important. The compute required for actually designing and developing next generation quantum hardware will rely on those tools as well.
Matias?
Yes. So the AI helps us broadly accelerate science discovery. This starts from the materials, the battery I showed, but also qubit material, qubit design. Then the big thing is when you have 1 million qubits, how do you tune and calibrate the 1 million qubits? As Misha said, that's a challenge. So to bring them in tuning faster, I think that will be a big thing that is feasible with AI. Then all the software we're writing, the software stack, developers have been using the Copilot and GitHub for years already for writing code.
So are you saying the vibe coding quantum stack?
We have shown last year in April when the agentic mode came out in the GitHub. They told the team, look, I think we can do quantum vibe coding. They told me, no, Matias, it doesn't work for quantum. Then I told them, try it. I said, I'm going to stop my quantum copilot because I think the generic one can do it. Within 1 week that was running, it can now just send quantum jobs to quantum hardware, but just with Copilot it works and the results come back. And since last summer, AI then explains the experiments for you as well without asking and prompting. But then the vibe coding asked them, I think quantum vibe coding should work. My dev team said, of course, no, it doesn't work. That evening, they sent me a video and said, hey, Matias, it works.
Wow.
So when people ask, who will program those quantum computers, the big one, the scale in 5 years, the answer is AI will do it.
Wow, pretty
But then also the application level, as I mentioned, chemistry. I don't want to run every calculation for hours on quantum hardware. I want it just with a quick call to model that is most likely right, and then I check it sometimes selectively. So it's kind of from the hardware, the fab processes, control and bring up, the algorithms as mentioned, development, the coding, the applications everywhere.
Anything else you would like to add, Misha or Jason?
Yeah, I mean, I agree with what everyone has said. So I should say that already kind of at a scale where we are sort of operating now, I mean, it's very clear that for things like compiling, certainly for decoding, so some of our most advanced experiments used AI decoders, and I mean, there are concerns in the community to what extent these things scale, but our initial results are exceptionally promising. Also for codes which are very complex, which they basically outperform the existing kind of things. So I would say it is indeed like we envision the future where this quantum QPU will be essentially a part of the integrated system. Right. Where you will do pre-processing, compiling, optimization of algorithms, in particular with things like reconfigurable architecture. This is extremely important. But also, kind of decoding and keeping the system calibrated. Right. This is sort of, and then eventually utilizing this kind of quantum results. And I was hoping Matias would mention it, and but I mean, for example, accelerating classical methods, with quantum data would emerge as one of the maybe first, most impactful application of these things. And we already see bits and pieces of that, but I think there is much more to come in the next couple of years. So.
Okay, a good segue to see if there's any questions from the audience. Yeah. The front.
So question about the networking side. If you think about networking at a larger scale, more than 10 millimeters, maybe more than kilometers, so to city scale and across the different countries. Classical computing, you have parallelization possible, so you can split the workload. In quantum, it sounds like you have to have for computing, the connection has to be high fidelity. Otherwise, the thing breaks down. So it seems like it's down to sharing resources. For example, the signal processing thing you mentioned for detecting. Would you agree with that, or QKD or things like? Is it really for sharing quantum entanglement resources and not for computing?
For computing, the problem is in classical computing, you can always trade off space and time parallelism. There is a near scheduling theorem. We don't have that for quantum because of entanglement. So you can do space-time trade-offs, you can make something bigger and share it, but it's a bit hard and you have to think through the algorithm for how you use more qubits for that. So it's a bit harder, but yes, you can do some space-time trade-offs as well and build something bigger.
You have another question?
Yeah, that's, yeah.
Or
I can maybe
please go ahead.
Yes,
go ahead.
but I mean, basically, at the end of the day, indeed, like these entangled belt pairs, kind of are universal resource for that. So once you have them, you can basically wire up these things, and of course, at that point, the entanglement rate will matter, and the fidelity will matter. But I mean, of course, you can distill things. But so this is, I mean, there is basically a level where this space-time trade-off emerges. It is not as kind of simple as for classical systems. It's a little bit more simple, but there is absolutely this space-time trade-off, and that's why also I agree with Matias that at the end you would like to utilize this networking, but it is quite likely that at the bandwidth of networking, and not just with transmission of the pairs, but also, for example, at a rate which you can kind of distill them, and kind of an extra resources you need to distill, would actually enter any kind of practical, consideration, And again, I think the rule is the bigger is your system to begin with, the better off you are, because you sort of will need fewer and maybe kind of not as high quality kind of initial resources to actually wire them up,
Resza, you want to add?
I want to add to that. I mean, at the moment, the first version of this connecting quantum computer we think about, or partition circuit, is based on try to succeed. We try and try to succeed. But eventually, when we move on, your network, I think Misha alluded to, if I got it correctly, is going to be you need to add the distillation. When you add the distillation to process, your network become a part of your circuit, become a part of your compute. Essentially, you consider that, and then you can easily basically try to optimize based on the part of circuit which is made of your network and distillation and the compute that is running on your processor. So that's the way it goes. But I think it's possible, I mean, to do the optimization and scale it. I don't know how it's going to look like, because still the network has the way to go to achieve that. Yeah.
Just last year, there has been some exciting theoretical work kind of combining these ideas, for example, with higher rate codes, and there you can have choices. You can either distill at a physical level, or you can actually first code and distill. So I think as the systems, again, these things start to pay off if you don't have just, 10 or 20 qubits. If you have like hundreds or thousands of qubits, maybe hundreds of thousands in your block, then you have some optionality, and I think there are some real possibilities there at this point.
And so 5 years back, we looked at the programming models, and we found that MPI really is good also for quantum, with two small changes. One, you need resource states. You need the bell pairs, but they then bring the quantum depth for collectives down to 0, because it's all classical. So that's constant depth collectives, quantumly, because you can pre-prepare the resource states. But the biggest change, there was one change we had to make to MPI, namely that you cannot clone a quantum state. Right. So when you do a send or receives, then you move the information. So we had to say, look, we need some move semantics for sending and receiving. The rest is the same as classical.
Wow. QMPI. That's
QMPI, yeah, it works. And we thought, the concepts are really well designed, because it was trying to abstract from various classical hardware, and it even includes most of quantum except for the move semantics.
Perfect, perfect. I think there was a question there.
Thank you very much. So I think because like a lot of presentation mentioning about milestone of quantum computing, like for example from IBM, about at the end of BlueJay. How about quantum network? Like how it will be matured to serve the purpose for connecting quantum computers or the work. The second one is maybe quantum network. I'm not sure how mature it is, but I'm very interested. But Mikhail Lukin mentioned about blind quantum computing, because, for example, as a bank, we want to run some algorithms, but we want to make sure it's secure. Is it possible to do that even with classical communication, assuming some cryptographic encryption? We don't need information secure guarantee, for example. Is it something achievable now or near future with near-term quantum computers?
Go ahead, Jason.
Yeah, maybe I could start. So at least just speaking from what goes into a roadmap from our corporate perspective is that we have to have an engineering path for doing a proof of concept of something that we're claiming to do in the future for it to show up on our roadmap. And unfortunately, for working from the field of superconducting qubits with microwave, in the microwave domain, there still isn't qubit remote entanglement scientific demonstrations via an optical photon. And we would love that to be true. It's not a lack of importance. It's not a degradation of that goal. It's a scientific reality that informs the maturity of that. So we would love to be partnering and pushing this forward and making that mature so that it can show up on the roadmap. Your comment on blind quantum computing, when I first started talking to people in quantum computing, I come from optics and quantum optics. blind quantum computing was the first application that we thought of. And there's some really concrete frameworks by which we can define that scientifically and then communicate a value of reducing points of trust between the client and the operator of the quantum computer.
Actually, on that note, right, we don't have actually blind classical computing. Why are we talking about blind quantum computing?
So, I mean, blind classical computing is fully homomorphic encryption.
Yeah, sure.
So it's just computationally impractical. Otherwise, we'd do it.
It is expensive.
It's super expensive.
And if you move that to quantum, it will also be expensive.
I would also add another nuance, which is if you look at the way, again, this is just take it as a perspective from IBM, you need to have IBM calibrating. We talked about calibrations. This is not a set and forget device. IBM is going to be knee deep in making this computer work. And there has to be a fair amount of trust there. And there's a lot of things that we can do to build that up. But establishing trust from physics is a much more direct way of achieving that.
Yeah, so maybe to kind of elaborate a little bit and explain so this homomorphic, basically, classical computer works by encrypting the information, and then you operating on this kind of encrypted bits, right? And there is the overhead is actually, quite significant. That I believe up to now this is not really practical, So in some way, if you, for example, think about, fault-tolerant blind quantum computing, so I mean, you have this kind of this sort of, encryption, in this fault-tolerant, like in error-corrected techniques, is a massive overhead. That's why this is so challenging. But basically, you kind of solve it anyway, right? And then so it's sort of, you could think that there is inherent advantage, essentially, of using, this blind quantum computing because, in both cases has to be encrypted. So in this case, in a quantum, you have to encrypt it to protect from errors. So, but I mean, I must say that this field is really quite underexplored. So for example, thinking about blind error-corrected quantum computing is just in the early stages. So, and for example, the overhead that you have to pay off in terms of communication is actually an open question. Because, I mean, if you have to communicate with fault-tolerant qubits, this can be extremely challenging, and it's probably not going to happen in the next foreseeable future. However, there is some early work that, and in fact, our group has just done theoretical analysis showing that, in fact, once you have a fault-tolerant, computer, potentially, communication can be much lower cost, and that, I do believe that there is, it's not a near-term undertaking, but there is actually a path forward.
So what I really meant was when I said blind classical computing doesn't exist is partly, yeah, techniques exist like secure multi-party computation, privacy-preserving computation, confidential computing. I mean, we hear all these different terms, but it's not really that people are worried about it, that this is an absolute must.
That's
right?
the cost.
It's partly related to cost. My point is quantum computing itself has not become commodity to the point where I think this is sort of a second order or a third order even concern for quantum computing, right? Unless I'm missing something that...
No, but it just can enable, there is a reason why people now want to have, on-prem computing, for security reasons, right? So, if we could really have a, blind quantum computing, this would just eliminate it. Of course, it comes with other things which Matias have mentioned, which one has to somehow, but, but it really, and it really redefines what's called quantum advantage, right? You now do not need to compete with sort of the fastest possible, but you need to compete with fastest, homomorphic, which is completely different scale, right? And in a lot of ways, the infrastructure that you need to build, like for example, this logical, encoding and so on, you have to do anyway. So you sort of pay high upfront cost, but then you can do other things. So in that sense, this, I think it is a kind of unique, opportunity, So.
I know we are slightly running over time, but maybe one last question from the audience. There.
So there's been a lot of talk about remote entanglement. as one of the reasons for networking. But what about just sharing quantum states from one computer to another, right? How much importance would you put on that as a use case?
Anybody to?
You're sharing states. You mean that you want to send a state from one to another because you split the computation over two machines for networking? Yeah. But that will do. You send it by entangling qubits. That's how you the teleporter send the information. So you use the entanglement to be able to move quantum states from one to the other. Yeah, that's spot on. That's what we'll do.
So maybe kind of I can elaborate a little bit. It kind of maybe really is related to the second part of the previous question about importance of networking layer and when do we have a roadmap for quantum networking? So I think the answer to that is really application specific. So quantum networking, if you want, is the oldest part of quantum information, right? Because QKD, point to point, is something that already people did 30 years ago, right? But I mean, within this narrow scope of these one specific applications with all caveats and so on, one could say that it had already worked, But then, the question related, to what you mentioned is what are you going to use these entangled pairs for, right? Well, but I mean, sharing for what, right? So, and I think it's kind of related to this. So the networking is important, can be important for scaling, but it can be important also for enabling things which are completely impossible without network.
Right.
There is a class of applications of quantum computers which are not completely possible. Blind quantum computing is one of them, but for example, this kind of quantum computing enhanced, distributed sensing, this is something which will not be possible unless you have a networking layer. And in fact, this might be another area where sort of early real quantum advantage can emerge. The reason is simply the following. So quantum computers are super powerful in processing information in parallel, but there is this problem of input and output. So input and output is classical. That's why we cannot use quantum computers, at least currently we know, for big data problem. So because the input and output is always classical and it's relatively small data. However, if you make input and output quantum, all of a sudden you can really enable a lot of these kind of possibilities, and that's where this networking could be really, really powerful. So yeah.
This is sorry, you had.
Yeah, just one last kind of point of maybe it's interesting, maybe it's not. We often talk about entangled pairs as the resource in networking because it's quite universal. If you're talking about any specific case, you typically get down to an engineering reality of how do I optimize the fidelity of the quantum operation between the end states of the quantum information. And that's some combination of remote gates, bell pair generation, state transfer, and local operations. And part of the lovely math of this field that we work in enables us to synthesize the operation that we're trying to create by a variety of methods, and we optimize for fidelity.
All right. So one last, this is a rapid fire, less than 30 seconds, question for all of you, right? So maybe start with Resza. What is the single most interesting and important milestone that you're working towards in the next 12 months?
You have a full stack classical quantum network connecting at least 2 quantum computers. That's.
Why at least 2? Why not more?
If we can more, yes.
2 plus.
Well, I got my directive from my boss, so working toward more than 2.
What about you, Jin Sang?
We have a couple, but I'll focus in on the tight coupling of HPC systems and quantum computing systems directly.
Okay.
I have 2. One is shipping the near 50 logical near qubit machine with the atom computing to Denmark, and then to entangle 2 topological qubits.
Oh, wow. All right.
Yeah, so we would like to basically use this continuous, operating machine to really kind of enable kind of deep circuit, potentially useful quantum simulation algorithm. And maybe on the networking side, we would really like to start seeing how we could, extend this kind of, two-party to, node thing to a larger scale and try to implement maybe some of this enhanced sensing algorithms.
That's music to my ears. Jason?
So if it's one, for me, it's turning on and operating these new quantum LDPC code systems. We've put a lot of time and effort into building, and we want to be able to operate that in a fault-tolerant manner and hopefully add some interesting experimental data points alongside other qubit modalities here.
I have one milestone of my own, which is to actually track all of your milestones and hold you accountable. Thank you so much for a wonderful panel, and thank you, audience, for all the questions. And I think we break
for lunch.
Break for lunch now,
yeah.
And we'll meet in an hour, I think.
Yeah.
Thank you.
Thank you.
Hello, everybody. Welcome back to our second part of our summit today. The second session is also focused on infrastructure and technologies. With that, I would like, without further ado, to introduce our next esteemed speaker. We have Pranav Gokhale. He is the CTO of Inflection. Obviously, he has a very long list of achievement and accomplishment. He's a serial entrepreneur. He was the CEO of the Cold Quanta, and also he has done his PhD in quantum in University of Chicago. With that introduction, Pranav, please.
Awesome. Well, first off, thanks so much, Resza and Ramana, for organizing this wonderful Cisco event. It's great to be here. And I'm excited to talk to you today about neutral atom quantum in the AI-focused data center. And there's 2 parts to my talk. The first part is about achieving picosecond level synchronization between data centers using quantum clocks, actually resonant with one of Resza's topics earlier. And the second part is on impedance matching between neutral atom QPUs and GPUs. But I want to start with an overview of Inflection, just 2 slides to let you know who we are. And at our core, Inflection builds quantum computers, precision quantum sensors, and software. And everything that we do in our hardware business is built on this neutral atom core glass cell that's shown on the left-hand side. And depending on how we configure the atoms and the lasers around that core, we achieve a spectrum of different hardware products. In quantum computing, we build a neutral atom QPU called Scale. And in quantum sensing, we build 3 types of quantum sensors. One is our ticker atomic clock. The other is our Skywire radio frequency receiver. And the third is our exact inertial sensor. And we fuse together hardware with the end user applications using software that's deeply intertwined with the underlying device physics, as well as the customer problems. Just to show that in a cartoon fashion, really at the core of what we do, all we do is we shine lasers at atoms inside that glass cell. And depending on the configuration of both the lasers and the atoms is the spectrum of products that we achieve. And one thing that I wanted to emphasize is that although computers, clocks, RF receivers, inertial sensors are very different applications, they have the same fundamental physics underpinnings, and there's incredible leverage between them. So just to illustrate this, I'm sure the quantum computing audience here knows that to have good qubits, you need to be able to put those qubits in superposition, you need to entangle those qubits, and you need to get those qubits to be very cold. And in fact, our sensors exercise each of those 3 different muscle memories, if you will. So for instance, the clock is targeting very precise energy levels of our atoms, and that same capability we turn into producing superposition of different qubit states in our quantum computer. Our RF receiver is exciting the atoms to something called a Rydberg state, which is also the core of how we get to entanglement in our qubits. And then finally, our inertial sensors get our atoms to be very cold
are very still, which is very important for a quantum computer as well. So 4 different products, but the same technical underpinnings under the hood. And so this brings me to my first part of my talk, which is about that neutral atom quantum clock called Ticker. And in particular, I want to tell you about a case study that's fresh off the press. This is a demonstration that we did just a month ago in December that achieved picosecond level synchronization between 2 real data centers, in fact, across state lines, 24 kilometers across, between Indiana and Illinois. This was a collaboration with Quantum Corridor, which runs dark fiber in between them. And this is the team that did this work. Let me start with just what is our Ticker atomic clock. So when you say a clock, at a physics and computer science level, what you really want, specifically a frequency reference, is a very stable ticking, kind of like a metronome for the musicians, the audience. You want tick, 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 tick. But if you zoom into those ticks to a very small level, you'll find that there's deviations of phase noise and frequency noise. So you actually end up getting tick, 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 et cetera. And so what we've done with our Ticker, you get the name, atomic clock, is achieve a new level of stability of those frequencies of ticks. In particular, the way we do this in the science core is we excite atoms to a certain frequency that's 10,000 times higher frequency than what was previously done in similar form factor clocks. And that gives us 100x more frequency stability in the actual clock. And in fact, the previous only way to get to this level of stability in a commercial system was with something called a hydrogen maser, which is much, much larger, much bulkier, and incompatible with the size, weight, power, cost dynamics required for data center deployment. So why does this matter? With this Ticker atomic clock, we can get to picosecond level synchronization. And for workloads that are becoming increasingly important, this is an incredible capability. And to dissect this a bit further, let me illustrate, let's say that you walk into a data center, perhaps one that Cisco is in. And if you walk in and go to the top of a rack, TOR, you'll find an optical switch. And that switch is about the width of a human hair, 200 microns long. And data centers have tens of thousands of these switches. Today, most data centers are using clock sources that come from GPS satellites or GNSS satellites. And by the time that signal reaches Earth, even though the clocks are very good, by the time they reach the data center, there's 10 to 40 nanoseconds of timing inaccuracies that have accumulated. And when you multiply that by the speed of light, you get to 8 meters of error. And so what that means is that if you're trying to aim for a specific optical switch, you're not just going to miss that human hair width, you're actually potentially going to miss the entire data center aisle of racks. And so this is a capability to be able to aim for specific optical switches. You need picosecond level synchronization. And in fact, our lab results, and this is before I show you the real world results, have already for a while now validated that this is possible. So the plot here, the simple way to see it is that lower is better because the y-axis is timing error. About midway in that plot, you see a picosecond. And in the blue and green, you see our atomic clock Ticker, as well as one with a 50 kilometers of fiber. And you see that across a wide spectrum of averaging times, we get to that picosecond level of synchronization, which is 40x roughly better than the standard state-of-the-art techniques that people are using with GPS clocks plus Secure Sync, which is a timing appliance made by Cepheron. So this was the results that we walked into this demo with in confidence in the lab, but there's always gotchas in the real world. And I'm happy to say that the results for a real-world demonstration between 2 data centers came out very strong, and in fact, almost identical to what we achieved in the lab. The key thing to look at here is that, once again, lower is better on the y-axis, and importantly, the pink and blue curves are very similar. The pink curves is just our atomic clocks alone, locally, and the blue curve is atomic clocks that have 24 kilometers of fiber that you're round-tripping in between. And as you can see, across a very wide spectrum of averaging times, we stay at about a picosecond level of synchronization. And this is in a real-world urban environment. So when I reflect on the AI-focused data center, and in fact, data centers that need to be networked, this is an entirely new capability to be in this size, weight, form factor. What we've shown is that this is now compatible with real-world deployments where we have to deal with things like switching, vibration, temperature swings, and for those of us who came from Chicago, like Karen too, we know exactly what that is this week, microbending, and et cetera. And in particular, again, this capability was previously only in the form factor of a hydrogen maser, which is much longer, nowhere near the size, weight, power requirements for data centers. And as I step back to reflect on the applications here, I'm a computer scientist by training. Everything that I've learned in my distributed systems course, I have to unlearn, because the whole foundation of distributed systems is that you can't have picosecond level sync between different data centers or different compute nodes. You have to mitigate the fact that you can't sync with a lot of communication in between. And I think that fundamental calculus starts to change with these atomic clocks that are 3U server rack form factor, 19-inch, can fit into any data center. So that's part one of my talk, and maybe an outlook on how the AI-focused data center and data centers can have new capabilities thanks to quantum clocks. Part two of my talk is on the quantum computing side, and specifically how neutral atom QPUs are being accelerated to have impedance matched to GPUs. And in particular, these are two of our papers in the left and center that I'll talk about, as well as we were happy to announce our integration with NVQLink, which Jin from NVIDIA talked about just earlier. And I'll reflect on some of these and how we can make sure that neutral atom can fully saturate the potential of having co-processing in real time on GPU. To foreshadow, there's really two key contributors to the runtime of a neutral atom quantum computer. One is the atom motion capability, which Misha talked about earlier, and the other is the measurement time. And I'll reflect on both. Let me start with the atom motion capability. I'll shift into cartoon land again to make an analogy. And in this cartoon land, I want to show you two different architectures of quantum computing that have emerged in the last decade, a tale of two cities, but then I'll contrast them to a third style of architecture that we unveiled in September. So in architecture number one, which corresponds to superconducting systems mostly, for instance, it's easy for a qubit to talk to a qubit that's their next door neighbor. They can just have a conversation right in place with north, east, south, west, et cetera. Very easy and in place, and therefore very fast. However, on superconducting systems, we have a challenge if we want to, of architecture number one, let's say, we have a challenge if we want to talk to a qubit that's far away. And right now, with the exception of the cool work that Jason and IBM are doing, the way to do this is to go through an intermediation of many different in-between qubits. And that can work in principle, but it has the downside that it's very slow. You need to step by step by step by step through many interactions. And it also bothers all of your neighbors, and you get a very low fidelity signal at the end. So that's architecture number one. It's easy to talk to your nearest neighbors fast, but it's slow and painful to talk to people who are far away. In architecture number two, which corresponds to most neutral atom and trapped ion systems, but not ours, it's kind of the reverse. On one hand, if I want to talk to a coworker or a qubit who's all the way down the hall, I can literally just walk up, move to a conference room, interact, and come back. And in fact, that conference room is called an interaction zone. But on the flip side, if I want to talk to my next door neighbor at work or a qubit that's right next to me, unfortunately, on these architectures, there's no way to just have that in-place, fast conversation. You have to move over, drive over to the conference room, the interaction zone, have your conversation, and then come back. And that is an incredible accumulation of runtime cost. And so that finally motivates this third architecture, which Inflection introduced experimentally in September, 4 months back. And that is the best of both worlds architecture. That it's on our scale QPU, and in particular, if we want a qubit to talk to this nearest neighbor, they can do that very fast in place. But if we want our qubit to talk to a qubit that's down the hall, far away, that qubit can literally just come over and sit at the desk or empty slot right next to us. And so this is the best of both worlds. You get fast nearby communication, and if you want to talk to a qubit that's far away, which you do need to do every now and then, you can just walk right over. You don't even have to walk to a conference room and come back. And so that was the analogy version. In slightly more technical terms, what we've done is united atom motion with in-place entanglement. And this on the right-hand side is the paper. It's entitled Demonstration of a Logical Architecture Uniting Motion and In-Place Entanglement. And in particular, this architecture gets the full saturation of taking advantage of this atom motion capability, which gives us all-to-all connectivity between our qubits. But importantly, it uses that great power and great responsibility very sparingly. We try to avoid motion except when it's absolutely necessary because motion is slow. And if we want to be impedance matched to the GPU, we want to be running as fast as possible and not using motion unless it's necessary. This is an architecture where in this paper we demonstrated 114 qubits on this array. And in a previous paper on the same hardware that was also published in 2025, we showed 99.73% atom loss post-selected CZ fidelity, which is a commercial record. Now, with this architecture in place, in the same paper, we showed 3 applications with logical qubits. The first was the first ever demonstration using logical qubits of Shor's algorithm for decryption. It's not our intent to break decryption and cause havoc. It's only our intention to show the resource cost and how fast these things are catching up to Matias's point, for instance. The middle application we showed is 12 logical qubits, where we showed fast arithmetic, specifically a CNOT ladder in constant depth. And then finally, on the right-hand side, we showed the first ever instantiation experimentally of the many hypercube code, which is a way to get a very effective ratio of very small number of physical qubits per logical qubit. So that's the motion side of how to impedance match QPUs, neutral atom, to GPUs. How about the measurement side? So this is also fresh off the press. This is a paper that was published by Professor Mark Safman at University of Wisconsin, who's also Inflection's chief scientist of quantum information. And this key figure on the top right is showing an experimental result that they achieved. On the top right, it shows that they've achieved experimentally with cesium qubits 99.93% measurement fidelities. That's a state discrimination fidelity in 100 milliseconds of integration time, which is very fast relative to previous experimental demonstrations. Importantly, at the bottom right, you'll see a with 5D quenching, and that's really referring to analysis that the same team did, that with certain techniques that are in the works, there's a path to achieving, in fact, slightly better measurement fidelities, much, much faster, 3 orders of magnitude faster, in particular, 99.95% fidelities in 60 microseconds of runtime. So I want to step back, and this is my last slide, to reflect in the language of numbers everyone should know. There's this legendary set of talk and notes that software engineers kind of swear by about, given by Jeff Dean from Google, about what are the standard branch mispredict times, network latency times, et cetera, for traditional software engineering. And this is the numbers that I think everyone should know for putting together neutral atom QPUs with GPU. So let's start with the GPU side. NVIDIA last year showed a wonderful result that you can go from GPU to the control for QPU and back in 4 microseconds, which is very impressive. In my eyes, that also sort of sets a lower bound, at least for now, on it's not that much useful to be faster than that for real-time communication with GPU. So I think of this as a lower bound of, it doesn't make sense to go faster than this if we want to sit right next to GPU in real time. Now, what that paper doesn't yet show is actually using the GPU for real-time processing. It's more of the lower bound on the communication round trip. So in fact, in 2024, we published a paper showing if we run a neural network for deep, in fact, classification for quantum sensing, but same principle for quantum computing, we can get down to about 3,000 microseconds of neural network latency on NVIDIA's GPUs. That's a batch latency too. And so let's compare these now to the numbers that I just showed, which is that this Inflection University of Wisconsin collaboration has shown today 100,000 microsecond measurement integration time with a path to 60 microseconds. And in my eyes, that's kind of a Goldilocks zone, because it means that today there is enough headroom for using the GPU effectively for neural network decoding, calibration, co-processing applications. And as we get closer to that 60 microsecond measurement integration time, we're still going to be well impedance matched to the minimum bound, which is 4 microseconds of GPU to QPU round trip, plus some time on the GPU for the actual neural network decoding, calibration, et cetera. So that brings me to my last slide, which is to conclude that I'm really upbeat about how quantum clocks are already delivering advances for the AI-focused data center. I think it rewrites a lot of the rules for how we think about synchronization between different compute nodes. And when we think about use cases in distributed AI training, monitoring infrastructure resilience. What previously was a capability that lived in a very bulky piece of expensive and hard to operate physics hardware is now available in a device the size of 3 pizza boxes. And on the quantum computing side, I think that neutral atoms are entering this Goldilocks zone of being well impedance matched to GPUs. This sounds weird, but they are slow enough, so to speak, to leverage GPU for decoding, for calibration, application co-processing. But they're also fast enough so that you get practical times to solutions. So that brings me to the end. I'll also flag that my colleague Eric Copenhaver, for the in-person audience here, is in the audience as well, and we're happy to chat with anyone in the breaks, and I've left our emails for the virtual crowd. Thank you.
Thank you very much. We have time for 1 or 2 questions. Any, yeah, question?
I'm interested about the ticker. So I'm more interested in the synchronization time within a data center. So do you have a way to distribute with that precision within a data center or just between the data centers?
Good question. So short answer is it's even better in a data center in terms of technological readiness. We actually just announced in December a strategic collaboration with Safran, which many people know is the French defense firm, but they're also the leader in data center timing appliances. And so the demonstration that I did in that lab is probably the first lab of the 2 that I showed is more relevant to within data centers. Thanks.
Okay. Any more questions? If not, then I have few. We'll leave it for a panel. Yeah, thank you very much.
Thank you.
So our next speaker. Oh, yeah. So we have our next speaker is we have a CEO and co-founder of Orcett Computing, Richard Murray. He's coming from UK, and I have to say Orcett Computing is one of the first companies that thought about using quantum computer inside the classical data center and build a quantum computing enabled data center. With that introduction, please, Richard.
Thank you very much for the very warm introduction. It's great to be here. So if you don't mind, in this talk, I'll talk a little bit about Orca, what we do building photonic quantum computers. But I'll spend most of the time talking about something that I'm obsessed with. Firstly, how you integrate quantum with data centers, something that we've talked about, we've worked on for a long time. And then secondly, how you make them relevant and applicable. So no data center is going to use quantum unless it makes sense in terms of the value and the application that it can bring. So I guess we're all here because we like the idea of quantum being applied to classical data centers. And you've probably seen many pictures like this. I think it's great. I think there's a problem in that anyone can take a data center and put some new technology into it. I think the challenge that quantum is facing is that, especially when you look at commercial data centers, there's got to be a reason for doing that. And I think quite bluntly, if you look at the quantum market, trying to interface with the data center market, you find a lot of data center customers really a bit confused about quantum. I think you find a lot of data center users really trying to understand the value proposition, the advantage that they might get. And I think there are 4 reasons for that, 4 challenges for quantum. Firstly, I think a lot of quantum hardware is quite early stage, quite scientific, both in terms of its robustness and its integration. I think, and crucially, I think you find a lot of data center users expecting quantum to be useful as quickly as possible without the long-term horizon that maybe some of the quantum vendors are working on. So we do need to find immediate applications that make sense to data center users. I think we can't hide from the economics. I think it was mentioned earlier today about what's the value of the application we're unlocking, and does that make sense for the price of the quantum systems that we're delivering? And finally, I think we've got to take an honest look at the scaling potential of quantum and the realistic implication of massive quantum computers to data centers. I think there's a big difference about installing a quantum computer inside of a data center versus building a data center around a quantum computer. So I think if we can address these challenges, as Orca has tried to do with our very philosophy, I think we're onto a world where quantum is much more relevant to commercial data centers and industrial companies. So this is Orca. This is our pride and joy. These are the systems we build. So photonic quantum computers. And you can see hopefully immediately how different our quantum computers can look by leveraging a lot of optical fiber, a lot of telecoms equipment to process single photons and quantum information. So this was the system that we provided actually to a UK centre, the NQCC. You know, in terms of specs, it's got about sort of 90 Q modes. It's got fairly reasonable fidelity, so 99.34 measured across 90 Q modes. But it's hopefully relevant to you that it looks and it's easy to imagine this system being installed in a data centre. And in fact, for our NQCC client, our system was actually the only quantum computer to be actually installed and trusted to be installed inside of the data center environment. So then we take a zoom out look and how do we imagine quantum being used alongside classical data centers? So actually Orca ran a project called the Quantum Data Center of the Future about 5 years ago when we noticed that a lot of quantum systems were just being looked at in isolation without the wider infrastructure that makes them, of course, an actual computer. And people in the room who know about data centers will know that it's all about interfacing. It's all about integration of different systems. And I think Orca has started with a unique perspective on the integration of hardware. So our hardware is much more accessible, you know, it's room temperature, it's easy to operate. But I think we learned over the course of the last 5 years that it's as much about the integrated software layer as it is about the integrated hardware layer. So I'm proud that we've done a lot of really great work working with NVIDIA to make it possible to run our system with the CUDA quantum framework, as well as just normal sort of SDKs that work with PyTorch. So in our mind, it's as important to have a robust software integrated layer as it is about having an integrated hardware layer. And if you think about it, that software layer has to do a lot important things like it can't drop workloads. It can't sort of fail in the middle of an operation and other things like that. So we have done some pretty cool demonstrations working with our customers and NVIDIA. So we wrote a paper that demonstrated, I'm going to say the world's first, but one of the first demonstrations of a multi-user, multi-QPU, multi-GPU environment. Again, stuff which people in the world of data centers would expect, but it takes some organization, some important sort of software work to be able to do this. On the really practical side, in terms of demonstrating a return of investment to your data center customers, hanging around in a data center for a year while you install a quantum system is not something that's going to be very, very easily accepted. So Orca really has built a product that we do install in data center environments in a matter of hours. So I think our standard is about 6 hours of installation time from the systems being uncrated to being installed in a data center environment. And the usual, it's expected in the world of data centers, integration within the full software, workflow managers and hardware and software programs that normal data centers would expect. We integrate within all of those. So hopefully painting a picture of quantum, but almost quantum made boring. I'm a type of person who really gets excited when technology can be made as boring as possible. And what's important is so do data centers. Data centers have enough worries. People running AI workloads have enough worries that they don't really want to worry about the quantum side of their system working or not working. So let me move on to the second question. How do these quantum systems do something useful? So we started off by looking at how quantum can be embedded into machine learning workloads. How the quantum system can be embedded within a machine learning a neural network, and we got some good results. So we did find that you can set up your quantum computer to generate an outcome that is then fed into the neural network. We also found quite nicely that actually you can, because of the long-range interactions that you get with photonics, you can actually generate a sizable gradient. Now, in the world of quantum computing, doing something like training gradient descent has been really challenging. But we actually found that changing some of our parameters here actually induced a very, very large change in the output that enabled us to do the parameter shift rule and perform a gradient descent some training. So we very quickly realized that actually this quantum system that we were building was sort of relevant to neural networks. But in order to do that, you've got to have a whole load of different handovers. There's so much information that's being shared between the quantum system and the classical. especially if you're looking at this quantum system embedded in a machine learning, an iterative model. There's so much handover that really, certain properties like the latency of the system matters a whole lot. So we built up this workflow. There is lots of handover between the quantum and classical system, and we're treating this as our list of requirements, including really driving down the latency. So it's already been mentioned today, one of the outstanding challenges of doing all of this, and that is the data loading problem. So all this is well and good, but am I ignoring the fact that your quantum system is tiny in comparison to the rest of your generative AI model? So the way Orca solved this problem is actually we spent a long time moving around this embedded object within the machine learning and generative AI model before landing on the fact that if you use your quantum system in the initial layers of your generative AI model, you can actually overcome some of the data loading and sort of size problems of your quantum system. So quite quickly, over the course of the last year, we've done a lot of benchmarking to find that if the quantum system is used as one of these prior layers or latent spaces, you can actually feed the rest of the model. You can use a quantum computer today to feed an industrial scale model. So there is no toy problem that we're solving here. We are applying this system to industrial scale models. And as you can see from the results, we are finding that the quantum system embedded in the model actually does generate some better results. The images you can see here is a bit trivial. You can see that you're trying to target this distribution that has sort of lumps. The sort of classical model tends to like to smear out the results, and the quantum system has a much better sort of frequency distribution to be able to match the target distribution. So it's a toy result, but a nice one. And I'm running out of time, so I'll just quickly say, since that moment, we have actually started to apply that principle to more and more industrial models across more and more different industries. So working with companies like BP, we found that we could help them identify more novel molecules. So applying this technique to generative AI models of molecular chemistry. We've just completed a sequence of work with Toyota, applying the same technology to image generation, and showed a significant reduction in the energy. So across these different areas, we're taking sort of what started as like a bit of a neat trick and showing that it does apply to many, many industrial scale models for many large organizations. And just to double click on one of those applications, it does seem like this approach is the most relevant to highly structured physical data sets, of which molecule generation or new chemistry is probably one of the most exciting. So this is a summary of some of the results that we got from our project with BP. So what we were looking to do is generate new molecules through generative AI models. And the results that we found by embedding our quantum system are, firstly, you get a better FCD score, which is your ability to generate results quickly. That's shown in the sort of training curve. Your training comes down faster. The ability to generate those results accurately is improved. So you're more likely to develop molecules that are actually real. And finally, you're able to identify molecules. Molecules that have never been seen before. So it's expressivity, the ability of this model to find molecules that maybe fall outside of the training data set, is improved. So it's sort of cool, and maybe to take a step back and think about what quantum is useful for. Like we're taking advantage of the quantum system being quantum, and therefore it makes sense in my mind that it is more natural when you're using it to help generate data that is also quantum, it's also structured, it's also correlated. So we think that this is something that is near term, is applied to industrial models, and does actually provide some value to the different industries and customers that we're looking to support. This is probably the most speculative but the most exciting slide for us. Where does this all go? I mean, we're all consumed with loving AI and generative AI, but obviously aware of the massive energy implication. I mean, let's just imagine if your quantum system can apply those improvements and look at the potential CapEx and OpEx savings that can be made for these data center users. So we're just in the realm now of building these products. We've demonstrated these early results. Over the course of the next 2 years, we've got 3 generations of products, starting with our PT2. Next year will be our quantum advantage machine, and then the year after, the PT4 will be a system where we're continuing to improve the performance, the numbers of Q modes, but most importantly, continuing to drive down the latency, which we identify as one of the largest bottlenecks to making these systems applicable and useful. So that was a bit on the systems level. Hopefully you can see my excitement and our belief in these near-term systems being useful for data centers and AI applications. Because of the audience, I thought I'd take a quick step back and just show a little bit under the hood, a little bit about the types of componentry we're developing that makes this all possible, because it's relevant to quantum, but also it's relevant to networking. So under the hood, it's exciting to me that we are developing our own semiconductor platform that allows for very, very fast, multiple gigahertz, very, very low loss switching. And that is something that I think the requirements are harder in quantum than any other industry, but something that, that we're achieving through our combination of a very low loss silicon nitride platform with the integration of this really exciting material called lithium niobate. So with our team in Austin, we're pressing ahead, developing that PIC platform. Now looking 2 years ahead, and to be honest, something that will be transformative to the area of photonic quantum computing, and maybe more broadly, is the development of a rubidium technology that allows photon-photon interactions, a photon-photon gate. Now, people who are familiar with photonics will know that one of the problems is photons don't like talking to each other. You don't have deterministic gate operations or deterministic entanglement operations. So again, underneath the hood, Orca has been developing this really unique rubidium platform that uses cavities to create a single photon interaction. Now, what this opens up, as we've demonstrated in some papers, is a unique approach towards larger scale architectures that reduce the component requirement by something like a factor of 10 to the 3 and also demonstrate a higher tolerance to losses. So those last 2 slides are me pointing ahead to not only our belief in near-term systems and how cool they could be for immediate utility, but also our roadmap going forward and where we might end up. So that was a real whistle-stop tour through everything. Thank you for your time and hopeful that we can answer some questions.
Thank you very much. We have time for one question and the rest for panel. We have a question at the back of the...
Hi, yeah, I'd just like to ask you some clarifying questions about stuff you said. I think quite frankly, I just don't understand it. So you said you acknowledge that there's this gradient problem in these quantum models, but you shift your parameters in your circuit and you notice a very large change in your output. So this is hopeful because now it gives you indication on how to optimize the overall pipeline, right? Is that correct?
Yeah.
Okay, but how do you know that this is not just noise?
Because it works. When we've trained our system.
But that could just be a coincidence, right?
I don't know. It's work. We can. I'm not sure I know what you mean. We've shown
the reason
that it
people
works.
use gradients is because it gives you information about how to optimize those parameters, right?
Yeah.
And now you're saying you're just shifting them, and the answer is meaningful.
I'm sorry. So the parameter shift rule is a bit of a technical term. It just describes how we change the function and then look at how the
parameter shift rule is an optimization method that is akin to computing gradients. It's computing gradients, right?
Yeah.
So that's all it is.
Yeah.
So I'm wondering, how do you know that you're not just using noise to optimize? Because you're not using gradients, you're just shifting the parameters based on what you just said.
So we shift the parameter, but we get a meaningful. The problem that other quantum systems face is the one called barren plateaus, that you shift your parameter and you get the result from that is within the noise. It's a very small change in the output. But what I'm saying is for our system, when we shift that parameter, we get a very meaningful change in the output. So the result is definitely not within the noise. That's the point that I think I'm trying to make.
Okay, I guess I don't understand what a meaningful result means then in this case.
Not within the noise. So clearly something that is. Okay, maybe we'll pick up afterwards. But
okay, and then just a quick second question about something you said about this generative model and how you quote unquote solve the data loading problem by introducing a quantum processor earlier on in the steps of this generative process. What does that even mean? Like, what do you mean by that? Like, are you?
Well,
I mean, it still has to load data, right? It still has to have data on it.
So the results, so the parameters we have the 344 of those thetas. They are informed by the training, the cost function of the model that we're
Sorry,
training.
I'm not talking about that anymore. There's another thing you talked about with your generative model. Like, how do you load the data onto that? Like classical data.
Because there is no, it's right at the start of the model, so there's no data being loaded onto the quantum computer other than so you run through, the quantum system passes it onto the generative AI model, generates a cost function, and that cost function is then returned back to the parameter that we're using.
So there's no data going onto the quantum circuit? Onto the quantum part of your generative model?
Other than the training data, yeah. It's being used to feed the...
Okay, maybe we can talk afterwards offline, because I don't think I understand any of the things you're saying, and I'm very skeptical.
Okay. Happy to talk. Thank you for your...
We can also continue the panel as well. Thanks, Richard. Thank you. Okay, our next speaker is CEO of the CQC, John Levy. CQC is a quantum computing chip company, which has a base in New York, Italy, and UK. John, please.
Thanks. Here, let's see if we get the right deck. Great. Thank you for inviting me here. This is going to be a very different kind of talk because we are not a quantum system developer. We are a quantum chip company. And we date back our kind of legacy to having spun out of a company called Hypris, for those of you who know Hypris, which came out of the superconducting electronics division of IBM. And the inspiration for what we were doing was a study by the Department of Energy in around 2011, 2012, that was looking at the future of data centers and of high-speed data centers and the energy requirements of those. And what the Department of Energy calculated was that in the future, data centers, classical data centers, were going to need to be powered by the equivalent of nuclear power stations. And that seemed preposterous for most people. But in fact, it's turned out to be exactly where we are today. And so the next year, IARPA put together a program that some of you may know called C3 that was looking at doing superconducting supercomputing using temperature at around 4 Kelvin to be able to develop new arithmetic logic units and new superconducting computers that could operate at reasonable energy levels projected in the future for exascale. And we participated building logic units in memory, logic with IBM, memory with Raytheon, BBN actually. And we did that for about 4 years. And after we were done, we came to the conclusion that we knew how to build very, very fast, something like 40 gigahertz arithmetic logic units. We knew how to build fast memory, and that we could match that really well with this new field of quantum. And our history, by the way, goes back to the fact that we made IBM's first qubits in 2002. We made D-Wave's first circuits back, I don't know, whenever that was. In our foundry, we have a 9-layer superconducting chip foundry where we build all these circuits. And we're using something called single flux quantum, which I'll talk about in a moment. So the idea for us when we spun out was not only to work on scalable systems for quantum, but to build energy efficient systems, not only in the devices we were building, but for thinking about data centers themselves. So where we are today in quantum, it's funny, Misha began this and talked, I think the word that he used was a rivalry among different qubit modalities. And we look at all these modalities and we say, we don't know what's going to win. It may well be there are multimodal systems, there are certain modalities matched to certain algorithms, et cetera. But what we do know is no matter how you build a computer, a quantum computer, you've got to read them out, you've got to control them, you have to multiplex them, you have to do error correction, you have to do GPU integration, all of these things. So our strategy was build all of those capabilities and put them on a chip and make the approach that we're building applicable across the entire quantum ecosystem. Now, what I mean by that isn't that every technology that we use, when we use readout, for instance, for matter-based quantum computers, is the same as what we're doing for atomic-based quantum computers. It's not. they're different. And our focus, frankly, right now is on superconducting because, frankly, as a chip company, we need to be where the largest number of systems are, the largest number of companies, the most mature efforts, and frankly, where the money is. So that's where we're focused on a go-to-market perspective. And so what we're actually doing, I'll give you an example. If you look on the left, you'll see Google's Willow quantum computer. And on the right, this is what Jason was showing, in fact, as the fault-tolerant quantum computing from 2029. And what I would argue is that where we are today as an industry is that almost all of the quantum computers that are being built, no matter what the modality, are in this kind of prototype phase. And we want to get to the scaling phase. But to do it, I would argue we need to go from this kind of vertical integration where lots of companies, system developers, for instance, are building their own racks of room temperature electronics, among many other things, to a point where we have a mature supply chain. So think about if you're, I don't know, Dell or something, and you want to build a laptop. You have a world of suppliers of screens, keyboards, processors, power supplies, I/O, et cetera. And that kind of mature supply chain simply doesn't exist in quantum. So what we're trying to do is to begin to fill that, to populate that, by building core functionality of a quantum computer on chip. So what we have done is that we have already built readout and control. When I mean by control, I mean XY charge control, Z flux bias control, readout, and I'll show you some results in a moment, all on chip. So if we look at the computer on the left, imagine a system where there are no RF components because our systems are entirely digital, where we've reduced the amount of cabling by about 95%, and the only room temperature electronics we need are to get signals in and out of a quantum computer. And all processing takes place at millikelvin. So this is below CMOS, we're in cryo-CMOS, at millikelvin, at speeds where we can operate between 10 and 40 gigahertz. And that's what we have done. In fact, that's what is this chip right here, which I'm happy to show you in a moment. So again, the idea isn't that we're going from room temperature down to cold back to room temperature. We're not going from analog to digital back to analog. It's all digital, all at millikelvin, all processing down below. And to give you a feel for what it means to be digital, let's say in the control plane, if on the left you look at the chart and you'll see conventional analog flux biasing, and this is a 6-qubit module where in qubit 6, for instance, you see a regular control signal. What you're seeing in the other surrounding qubits is crosstalk. And so you can apply all kinds of advanced signal processing like digital pre-distortion and all kinds of other tricks to deal with it. But if you're doing a digital SFQ control pulse, we have undetectable crosstalk across all qubits. Why? Because we're not using an RF signal. So we're not using microwaves. Similarly, on the readout side, we're also doing digital readout. And we're doing it and we think that it's really, really critical. People don't pay as much attention to readout as they do to control. But the core idea is to do digital readout, to do high fidelity and very fast, low latency readout, because we think it's critical for being able to do error correction at scale. And so this is just, I'm just going to go through this quickly because we don't have a lot of time, but to say this is a Josephson digital phase detection, JDPD approach. We gave a talk about it at March meeting last year. We're doing an update talk about it at this March meeting. We'll show some new results, but the idea is that we're able to achieve 99.5% fidelity of readout and doing the readout itself, just the component of it, not the kind of round trips that we need, but right now just the readout, we're operating at 50 nanoseconds, and the whole system is operating at around 450 nanoseconds. And we expect to be able to get that down to an even faster level. So we think readout is a critical technology for doing a kind of precondition for doing error correction. And I'm going to talk about that as it relates to GPU integration in just a moment. But just to summarize where we are at this point is we think that the idea of making chip-based quantum computers, or the core functionality on a chip, is going to be essential for scaling at the large levels that we've been talking about in this conference. Doing it digitally, I think, resolves a lot of the issues. And by the way, it's a theme that I was hearing before in some of the other talks. Being able and being cost effective. Richard, you were just talking about the notion of pulling OpEx out. And the idea of getting rid of all of the RF components, reducing your cabling by well over 90%, reducing the room temperature electronics to a single rack, means that you can take a bill of materials and reduce it significantly. And then whereas in this example, let me just go back for a moment, if you're looking at room temperature electronics, it takes about 3 to 5 watts of room temperature power to control each qubit. We're doing it on the chip I showed you at 3 nanowatts of power. So you're seeing a 10 to the 9th delta between the two. And then a business model where again, the approach that we're taking is to be applicable across the entire ecosystem. And then lastly, this is what I'll talk about next, about our integration with NVIDIA's GPUs. So in order to do this, by the way, you can't just build a chip, because nobody has built the kind of digital controls to operate a chip. In other words, if we're sending a pulse-based system and we're sending digital pulses, we need to be able to have firmware and software that optimizes for that. So we have also developed a firmware system for doing it. And we also think that it's critical from a scaling perspective to develop really advanced packaging systems that enable us to do that at where we're packaging all the elements of a quantum computer at superconducting temperatures. So right now, our core partners that we're working with we're collaborating with IBM on QBI. We're exploring the use of these kinds of technologies. Again, these are single flux quantum, so to be clear, this is not cryo-CMOS. We're using Josephson junctions, we're using niobium titanium nitride, tantalum, et cetera, to be able to build these kinds of devices. We operate it at our chip foundry. It's a 9-layer SFQ foundry. We're also working with Rigetti on quantum readout and error corrections, similarly with IQM. And so this is all working by integrating our chips with their qubits. So that's the system that we're going with. And then on the NVIDIA part, again, I'll get to the quantum AI a bit. This is a very, very simplified version of our roadmap. A few years ago, we built some of our first quantum computers operating over the cloud. It was really basically to test out our firmware. The Seek Orange results are from a couple of years ago. That's the chip I showed you, and that's the first digitally controlled cryogenic chip quantum computer that had been built. In fact, it's the subject of a paper, a peer-reviewed paper that's going to be coming out in the next probably 2 months. And then we're now in the domain of our Seek Yellow systems. So Seek Yellow version 1 is digital XY control, flux bias control on a chip. Version 2 adds JDPD readout. So by the end of 2026, we'll have all core functionality integrated on a single chip. However, the way that we have been working with companies is companies come to us and they have very specific requirements. So we can build breakout chips that deliver a core function. So if somebody wants, they only want charge control and digital multiplexing, we're able to do that. If they only want to have digital readout, we'll do that as well. By 2027, we'll have the digital link I'll describe to you on chip. And 2028 will include mostly, it'll be where we're doing most of our error correction on chip at millikelvin for error correction. We believe in the idea of building out a kind of computational architecture where we have everything from error correction decoding at millikelvin all the way up to room temperature GPU for error correction, and other stages that I'm not going to really go into very much. But the idea is to build a computational environment for error correction where companies can use whatever codes and whatever software they want, and they can use or not use whatever resources we provide. So I wanted to go and talk a little bit more about our view about this integration with with GPUs and with what we're doing with NVIDIA. Because really what I think we're building is we are building the chip-based infrastructure for quantum, but I think we're building the infrastructure for true heterogeneous compute. And this is what I mean by that. So I think Jin Sang showed this example. I think this is almost exactly the same slide, where you're showing, and we just put some numbers next to some of the features, but this is where you're looking at, on the left side, this is, in this case, it's a superconducting quantum computer with all of the, the latencies that are there with having a system where, again, you're going from room temperature to cold, back to room temperature, et cetera. So there's a lot of latency built into that system that we don't have. It's outputting an analog signal, which is a 14-bit signal, so it's terabytes per second throughput, and then it goes to the NVQ link. And one of the critical aspects of it is analog to digital processing. It then puts out a digital signal, which ultimately goes to a digital data center. And so that's great, and that's great for connecting a quantum computer to an AI data center. But imagine, instead of doing that, we do a little bit of what NVIDIA has done in its core module by taking a CPU and a GPU and creating a direct digital low latency link. And we've taken NVQ link and repurposed it to connect directly to our Seek digital link, directly to our digital integrated QPU. So this is essentially a chip-based version of the integration of a CPU, GPU, and QPU. Very low latency, very high speed, and all 7-bit digital. So it means that we're dealing with gigabytes of data, not terabytes of data. And by making it very fast in that way, we think that we can use that for things like error correction. And so we actually did an experiment with NVIDIA at the NQCC, where you're located as well. We have a computer that's set up there. And the idea was we ran an error correction code through a Grace hopper using NVLink, right, between the two. And then we used NVQ link with our Seek digital link to our Seek backend. And we're already seeing this is decoder latency. So this is the full circuit, and this is what, 54 microseconds. And we're doing this at, again, this is at 7-bit, and our chip is running at around 20 gigahertz for co-processing. So we're operating at pretty high speed. So the idea here is to think about what is the implication for building an integrated chip-based QPU, CPU, GPU for heterogeneous compute, and how do we take advantage of what the features are going to be of that, because it's going to be a significantly faster connectivity. And I think that we'll use this as an augmentation to classical data centers, and we'll find out how we can take advantage, and we're already beginning to talk to quantum software developers and AI developers about what does it mean to be able to have access to a tool set where you have a chip-based system that looks like this. And we think we have, over the next 2 years, we have a very detailed roadmap about how to get that latency down to an even lower number, a much lower number. We think we can get it down below that 4 microsecond time frame that we were talking about before as being like the connection, the ultimate connection between computer to computer, because we're operating on a chip-to-chip basis. And again, we think that what we're building here is the chip-based infrastructure for truly heterogeneous compute. So with that, I mean, look, the way that we think about what we're doing is that if you go back in time and you think about the development of classical computing, which started at, with vacuum tubes and telephone switchboard connectivity, it went to solid-state devices like transistors, to integrated circuits, to microprocessors, where at each stage there's more integration of the stack onto a chip leading to a microprocessor. That's what happened for Intel. That's what Intel did. GPUs, the same process. for what NVIDIA did, going from from serial processing to massively parallel processing. And by incorporating the full stack of a quantum computer on a chip, we think that at least that's the effort that we're trying to make. So that's what we're doing at SEEQ, and I thank you for your attention.
Thank you. We can have one question and we move to panel. Question? Yeah.
About the readout, you had the 99.5% fidelity. In the plot, you showed, quantum state 0, quantum state 1. Was that actually the state of the qubit you had initialized, or was it like just a, room temperature generated pulse corresponding to such a state?
It was a ground state reset. I'm not sure that I understood the
I was meaning about the readout. Was it done with an actual qubit, or was it just a...
Yeah,
okay,
it's an actual
so it was
qubit.
not a mock pulse like
this is an actual qubit. This is integrated with a third party's system. So this is not even our qubit. This is integrating with another company.
Can I ask the other two speakers also come? We have one of our last week speaker, unfortunately feeling unwell and left just around the lunch, so we lost one speaker. So we will have a longer break. Okay. Okay, I start with a couple of questions, and then we move to audience to see. I start from the last talk, you talked quite a lot about the control integration.
Yeah.
And first of all, I want to pin on that. Is there any universal way to integrate to make your control faster, lower energy for your qubit modality? Because you talk about the transmode and Joseph Junction.
Right.
But we had two other modality now here. So we start with go there. I mean, what is the bottleneck there? And do you see there is a need for a control? For example, neutral atom has its own big control mechanism. And what was the problem?
Exactly. That's why I was saying that the approach that we're taking, the technologies that we're using are specific to the modality. So you're quite right. This is an example of working with transmons. We're working with tunable couplers, with fixed frequency, we've demonstrated this with fluxoniums. We think that the readout is applicable to topological computing. In other words, and we did a paper around the applicability around spin silicon as well. In other words, matter-based computers. With atomic-based computers, we would do things in an entirely different way. And it may well be, by the way, that we wouldn't focus on control. We might focus on doing, single nanowire, single photon detectors, building digital versions on chip and using those as faster, more energy efficient readout systems, as an example.
Fair enough.
Is there an
No, your microphone is working, yes.
And just broadly on control systems is the topic. So you mentioned energy efficiency, both you and in the question.
And the size, obviously, for your specific modality.
Right now, our quantum computer is about 25 kilowatts of power consumption, which is 10 hair dryers. So I think for all of us, I think this is the potential of quantum computing in terms of ways to solve certain tasks, certain computational problems dramatically more efficiently. And that 25 kilowatts does include things like control systems. One thing I'm really upbeat about that has been a seismic shift in the last 5 years or so is the way to generate some control signals has been overtaken. It used to be you buy these bulky waveform generators that are the same technology from like 1990s, et cetera. There's a technology called RF-SOC, radio frequency system on chip, that has really changed the fabric of how we can generate these signals to be very programmable. It's technology that came out of Xilinx, and it also changes, it's a cost inflection point. It used to be that you might have to buy a box for every single qubit, and now you get a much better scaling of number of qubits and just price per qubit. So maybe that's my high-level thoughts on control systems. One is I'm upbeat along with my co-panelists, I'm sure, on the potential energy implications of quantum, as well as some emerging classical technologies that were not designed for quantum, but are now really helpful to quantum for getting very accurate, cheap, and fast control signals from RF-SOC technology.
Yeah, well, just picking up, I mean, It's funny because sometimes I think you hear people talking about the relative differences in energy consumption between quantum computers. Like my quantum computer is better than yours from an energy consumption point of view. You're talking about within the noise, right? So all quantum computers, even if they're cryogenically cooled, consume far less power than the equivalent classical. So and photonics is no different.
So for your specific, Richard, what is the complexity in the control compared to the transmon or a neutral atom that we talk
So I think, photonics, so much about photonics is different. And I think one of the biggest differences is that we don't really need to spend as much time sort of monitoring or stabilizing our qubits. They're photons, and they just do what they do best. They just shoot down optical fiber while being sort of switched around. So I think from a control perspective, we need to spend a lot less time worrying about the qubit. Our control is mostly on, and I don't mean to oversimplify this, but like beam splitters, beam splitter switches, basically telecom switch type technologies, which in themselves are pretty standard to control. I guess that's why there are challenges elsewhere. Don't get me wrong, but I think from a control perspective, photonics is different because it's that much simpler to do. And I guess that's why we focused on where I think the challenges of photonics are, is speed. Photonics is just a platform that operates so much quicker. That means our requirement for feeding signals back is so much harder. And to give you an illustration, the challenges for us, we measure a bunch of photons and the outputs of photons. And then the intention is to then feed that signal back to photons that are still within the system passing through. So you're talking about feeding back control signals, within fractions of milliseconds. So the challenge for photons, I think, is just the speed and the feedback that's required to build these systems, less on the controlling the qubits, if that makes sense.
Okay. Now I have a question on the scalability, but slightly different for each of you. For you, Richard, I start from you. How you scale your quantum computing, very question, and then second question, which is relevant, how you dimension it. What do you think in a data center, what portion of it needs to be your type of quantum computer to accelerate the type of the machine learning that you...
Yeah, well, I'll talk about what proportion second, because I'm going to frustrate the question. I don't think anyone knows because applications are uncertain. But I think that in terms of how we scale, photonics does have its problems, and I'm not going to ignore that. But one of the benefits is our qubits are already photons in optical fiber. So the idea of us scaling is just, two systems next to each other with an optical fiber link between them. The challenge to scaling up anything in photonics is just loss. And that's probably true in the networking side as well. So the reason we can't just string a bunch of cabinets together is that what defines the performance of a photonic quantum computer is how much you can do before you lose all your photons. So you string too many quantum computers together, you've got too many interconnects, and then the loss becomes, you can't get over it. So the challenge to scaling is pretty straightforward if you sort of skate over the loss challenge, which is pretty hard. And then I think in terms of what proportion of the data center, I had the slide there, looking at my slightly provocative view on what the CapEx, OpEx savings might be. Maybe my more honest answer is, it really depends on the application, right? We're still trying to work out the applications. We certainly don't know how much of a proportion of a workload needs to be ported onto solved on a quantum computer. So I think it depends on the size of the quantum computer that you're delivering. But yeah.
And do you think your scalability would be a fixed connectivity between two quantum fixed fiber, or you need to do some sort of networking?
Well, no. So the current answer would be everything static. Our current answer is that all the links that we have are pretty static. But I think the future of maybe more dynamic algorithms is everything's rooted in different ways depending on the measurements and the observations that you're making of the photons and where the errors or where the losses are occurring. So I think, and to be honest, in terms of the world of networking, I think we are living in a world where people are at the moment building pretty simple, no disrespect, but simple networks, because I think no one's really understood the theory of like routing around the light or the quantum information to accommodate what's happening within the algorithm as yet. So the future is very dynamic. I think the current reality is quite static.
Thank you.
Yeah.
And now, Parnav, the same question, but different angle for you. I mean, how far you think your quantum computing monolithically, what is your roadmap to scale, and where do you think network come to play? And again, is it a static or dynamic or what? Yeah.
Sure. So our roadmap shows getting to 100 logical qubits in year 2028 and 1,000 logical qubits in year 2030. Under the hood, for the number of physical qubits, we have achieved 1,600 physical qubits in-house on our system. That's a 40 by 40 array. And Caltech actually purchased our cold atom source cell and our PCAS cores to achieve 6,100 qubits on a 12,000 site array. So that's kind of the upper bound. That's the absolute record today of neutral atom number of qubits. That gives me a lot of confidence and optimism about getting to the 100 plus logical qubit range without networks. And I think that that 6,000 qubits can be pushed to about 100,000 qubits within a single core before I start to sweat. I start to sweat around 2030 or so, where I think to get beyond that, there's either two directions to travel. One is we figure out really good ways to do recycling of the power in the laser system. So for instance, we don't want to melt the glass. We don't want to put so much laser power that the quantum computer just fries. And so that's we either have to figure out really good science of how to get lower laser power, be more resistant to glass, et cetera, or it's networking. And right now, I would say, and maybe this is a slightly provocative take, that quantum networking between multiple QPUs to get to a higher logical qubit count is not really in my near-term roadmap. And the reason that I say that is I'm waiting for scientific breakthroughs. I think they will happen. I reflect on the fact that in year 2017, no one thought of neutral atom quantum computing as important qubit technology. It was kind of in the Department of Weird Things, So I would put quantum networking personally in that department right now, but I know that there's really wonderful research being done there, and I think that it will break out of that department. But to me, it's more important to do classical networking between quantum nodes, to your point of your talk of having the QPUs talk to the classical computers as well as quantum sensors. So I think there's a role for networking. It's a little subtle, whether it's entanglement between different QPUs. I worry about things like the throughput of communication between different nodes. It would be like taking your 1 terabyte hard drive on your phone and slicing it into 1,001 gigabyte pieces. That could work, but the overhead of compiling to that, the latencies required, they really scare me a little bit.
Thank you. Now, John, again, scalability, from your perspective, we see, IBM roadmap and announcement, they are going very fast, increasing the size of their chip. So do you think your control can scale linearly with them, or you're going to have a network of the control chip sitting in a big CPU or a big computer?
Yeah, so I think there are two things. One is the amount of multiplexing we can do, and because we're digital, we don't have the same sort of crosstalk issues that one might have in an RF domain. So we think that we've already done, I think we've done 16 to 1. We're very confident we can do 32 to 1 multiplexing of digital signals for control. Then it's a question around packaging and how we package our chips with respect to qubit modules. And then it's a question of how do we connect qubit modules to each other, right? So there's sort of a networking component to the module. I think that in the earlier panels, there was some discussion around that as well. And I think that's going to be an important idea around, if you will, kind of tiling these qubit modules and then connected to our readout control and multiplexing and ultimately error correction chips.
Okay, great. I have more question, but I want to open it to the audience. Then yes, we have one at the back question.
This is mainly for Richard. So I have two questions actually. The first one is that you mentioned that in your AI training, you use your all-optical network. In that case, where is the computational nonlinearity come from?
Sorry, where was the
computational nonlinearity come from? Because in the classical optical or photonic computing, they either use a classical measurement or they use like a game media to achieve that. But I don't think a game media works for you, right?
No, so maybe I need to do a better job explaining this. What we're doing at the moment with our quantum system is it's just sort of a single layer. So the nonlinearity comes through the measurement of the photons at the end. That is.
Okay, so you feed it back.
Yeah, you're right. So then the measurement of so we only really, a whole photonic system is only really being used as a single sort of layer to make them, and then the measurement of those photons at the end is then providing the
Thank you. The second question is that you claim that your system in the data center, it can provide a much better COPEX and CAPEX compared to the traditional electronic data centers. But we see similar comments or claims from the optical or photonic computing community. They claim, okay, we have a similar improvement. So because you are mainly claiming that this comes from quantum, so how much quantum helps you to reduce the CAPEX and OPEX?
It's a good question. Maybe I'll just answer in terms of the comparison of what we're doing to the guys doing optical compute, interferometry for optical compute. So I mean, the big difference with us is we're doing similar things. We're sending light into big interferometers and measuring the output. But because we're working with single photons, we create quantum states and quantum interference within that system that's not seen in the equivalent sort of classical photonic processors. So I think, I mean, here's a bunch of stuff we don't know. I mean, we don't exactly, those OPEX and CAPEX calculations I mentioned, we've not tested, it's just sort of hypothesized. I would expect that what we have the potential to deliver is better than those classical photonic chips, but we don't know exactly.
Thank you. Yeah, thank you.
Any further question? Oh, there is one other. Yes.
This is for John. I was wondering if you guys have considered if, essentially you're putting a lot of electronics in a place where it's really hard to remove heat. And so, if that's limit the scaling and, how that compares with, the more traditional way of doing things, which is to, put everything that's not quantum qubits outside.
Yeah, so it's a really good question. Just because we can put it there, that we can migrate all of the electronics down to millikelvin doesn't necessarily mean we should. So one of the things that we have been looking at, and we recently made an announcement, I don't know, a couple of weeks ago, around some work that we're doing in collaboration with the National Taiwan University, with ITRI, and with some other institutions in Taiwan, is that we're working on essentially parsing some of our electronics so that there are certain functions that can happen with cryo-CMOS at, say, let's call it 3 or 4 Kelvin. There are certain things that can happen at 1 Kelvin, where we have different amounts of power available to us in a dilution refrigerator. And so part of the idea is, how do we optimize the stack to be able to have the electronics in the place where they can operate the best while maintaining superconducting speed, right, and connectivity. So a lot of this has to do with utilizing all the power at different levels and with different modalities. And so I think I mentioned this idea around building a computational infrastructure for quantum error correction, all the way from a room temperature GPU down to a millikelvin predecoder, for instance. And so that would be an example of that, where we're using different amounts of computation and kinds of computation at each different power level.
Okay. Thanks. Any more questions? Okay. I have a question, maybe mainly for Pranav and Richard. If somebody wants to build a data center and wants to deploy a quantum computer there, do you think, because the application of your computers is different, kind of, and is different technology as well, do you think you will see that this would be a combination of them, or they have to make a choice that I am going to go for a neutral atom, or I am going to go for a fiber? For whatever reason is your choice. I mean, do you think it would be a combination of them for different applications, or would be a single modality quantum computing data center?
I can start with that, and it's okay if you want to say it's single, but I take a multimodal view long run. I think that when I look at classical hardware, you have different physics technologies for storing bits. You have flash memory, you have hard drives that are magnetic, et cetera. So I think it's going to be the same thing in the long run for quantum computing, where, for instance, superconducting technology is very fast. Photonic is great for networking. I do think neutral atom, obviously, I've actually switched camps twice. I started my career in trapped ion, then I jumped to superconducting, and now I came to neutral atom. I'm very upbeat, especially in the near term, about how to get to many logical qubits very fast. But in the longer run future, I think there's a role for almost every qubit technology, except maybe NMR qubits. And I think that it's important to have software that does compile across the stack. I know you showed some nice work in one of your Cisco slides about partitioning workloads for run this here and run this here. I think that's the right direction we should travel in. And I think that networking does matter in that 5+ year time frame to transduce, for instance, neutral atom qubits to superconducting qubits, perhaps intermediate beta-photonic qubits. So yeah, my short answer is I think they will coexist. I don't think it will be one winner take all. I'm obviously very biased. I do think that in the near future, neutral atoms have a very promising path to 100 logical qubits, but I don't think that other qubit technologies are not going to win either.
Yeah, and I would agree. And maybe to explain, I mean, because why is Orca even working on applications ourselves? Why not just stick to the hardware? And our story is that photonics is so different, or it can be so different from all of the other platforms. Our noise models are very different. The way you operate the system is very different. The reason we work on the applications that we work on is that we wanted to lean into the differences that photonics has. It does operate in a different way, and that's what formed our belief in the things that we talked about, the things we found. I don't particularly know. I don't believe that those applications are actually that applicable to the other platforms, because they leverage some of the specific properties of photonics, which makes us sort of different in terms of having developed applications that are specific to our piece of hardware. And I think, personally, I really believe that the immediate future of quantum is for applications people to be really in the weeds of the hardware, like really working within the connectivity and the noise models that are there to derive nearer term applications. By the way, hopefully I've made clear to everyone that I think that there are applications before error correction where none of that stuff matters. But I think for now and for the next few years, the realities of hardware are there, and applications people can either ignore that and develop applications for perfect quantum computers or live with the hardware. And in that world, there are lots of different hardware platforms, and for sure going to be lots of different types of applications that are suited to the different characteristics of the different pieces of hardware.
Yeah, so I want to just give you, there's an interesting update on your question, which is that there are two efforts that I'm aware of. One is run by DARPA called HARC, which is meant to identify unique combinations of quantum computers where that kind of multimodal approach can take advantage, can be demonstrated. And the other is that there's some active work at AFRL up in Rome, New York, doing the same, looking at photonics and I think ion traps. And now they're trying to incorporate superconducting. But again, I think that the effort is on exploring this multimodal space. Yeah. And I think it's really a valuable way to think about it.
I just want to triple second that we should pay a lot of attention as a community to this DARPA HARC program as well as the AFRL. That to me paves the future of this multimodal, so seconding that. May I break the fourth wall, Resza, and ask you too what you think on this question?
Yeah, I mean, I said it in my slides. Definitely we think in multimodal. Exactly, the HARC is they have done the nicest justification I have seen in their call for the solicitation that why you need a multimodality, and I certainly believe that. I mean, simply because the different decoherence time, different speed, different gate operation models and so on, yeah.
And we, by the way, have been encouraging the HARC team to add GPUs to their modalities.
Great.
Right?
And maybe I'll chip in. I just want to emphasize, we all talk about this multimodal, like how hard that is. I mean, the world of imagining our hardware platforms working together is an amazing future, but it requires wavelength conversion, it requires extracting photons from superconducting qubits. It's really, really cool, and it's got lots of benefits, but there are several, perhaps you might call them networking challenges to actually.
Yeah, exactly. I mean, we hope that the network will be common denominator, but yes, with big challenges on transport especially. Yeah, I agree with you. Now, John, I have a question specific for you. I have seen academics and a startup, especially recently in the last 18 months, start looking at the control for transmon, optics for control of transmons. optical pulses. And
yeah.
So how do you compare your technology with that?
I haven't really looked at it. I can't really comment.
Okay.
Yeah.
Great.
But thank you.
So with that, I don't know if there is, I have one final question, which is copying Ramona's final question. But is there any question? Oh, there is one question from back of the room. Yes, please go ahead.
Yeah, I think Resza brings a very interesting question on multimodality. So I hear some discussions like talking about like the combination of the code atom and superconducting qubits together. I mean, based on my knowledge, it sounds like, okay, superconducting is very mature, like very fast, and it's very easy to be controlled. And the code atom, people had already demonstrated the transduction between the microwave to optical using code atom as well. Then, based on your experience, what is the main bottleneck right now stopping people to demonstrate a hybrid modality system?
I can take that. So our chief scientist of quantum information, Mark Saffman, has done some nice work exactly on this, superconducting to neutral atom links. If you happen to Google search for that, I'm sure you'll find the specific papers. In terms of what stops this from taking flight today, the fidelity of the links on a network are still not awesome. It turns out that there's been a lot of innovation in the last few years on, it turns out you could actually tolerate much higher error rates on the links than within like the bulk of the system. In particular, we usually think about thresholds of you want your error to be below 1%. It turns out that at the edge, 10% is okay. So maybe that's not so problematic. If we had 91% fidelities between superconducting and neutral atom, that's fine. The challenge seems to be the throughput, the rate at which the qubits can travel between two different modalities or even within the same modality. And that needs to go up by orders of magnitude because it's a lot harder to do that on literally moving qubits, entangling them with maybe photons and back to superconducting. The quantum process for that is way more complicated than classical networking. So I think we're sort of still in the networking between modalities in early days. I do think the DARPA HARC program will dramatically accelerate this, or at least reveal the limits of where this can go.
Thank you.
Thank you. Okay, very quickly, we are running out of time. If I want to slightly change Ramona's question that I asked our panel, is if we come next year here and you want to show off one thing that your company or your group has achieved, what that would be? Do you think? Where you hope you be?
I'd say the integration of our chips into a fully functional quantum computer.
30 logical qubits.
30 logical qubits, great. You?
The integration of our systems within proper commercial data centers. Emphasis on the word commercial. I don't mean people building data centers around quantum computers.
Thank you. With that note, let's thank our speakers and panelists, and then we have a half an hour break. We come back in half an hour, yeah.
Thanks.
Okay, welcome back to our last part and one of the interesting part of our Quantum Summit today. In this session, we are focusing on algorithm and application, and our first speaker is an academic, mainly academic and professor from Finland, but also founder and chief scientist of QMIL, which is Mikko Moten, and he's gonna explain to us what his company is doing for quantum machine learning. Yeah.
Great, thanks. It's a great honor to be here in front of such high quality audience. So thanks for the organizers for inviting me here to Cisco. I tend to teach something about Finland when I'm giving talks in the US. And did you know that Cisco actually is a word in Finnish? It means sister. So it's really homey to be here. And I don't need to teach you what quantum computers are. But when I do that to some industry people outside quantum, I start by saying what they're not. So they're not just faster computers. And now when I'm going to talk to you about QMIL, I'm also going to start you by telling what it's not. It's actually not a quantum machine learning company, and it's not definitely a quantum data generation framework that this paper that was put a couple of months ago to archive is claiming. It's kind of, so that's not the real QMIL, trademark QMIL. However, QMIL was founded by these four founders back in 2024, so about 1.5 years ago. Our CEO, Hannu Kauppinen, he is a former CTO of Nokia Technologies. Our CTO, Ville Kotovirta, was a founder and leader of the quantum algorithms and software team at VTT, which I also call the NIST of Finland. And then we have Toni Annala, who is a professor of mathematics at University of Toronto, and also our chief algorithm engineer. Altogether, the team is 23 now, and counting. And the team members, as team members, we have published more than 500 scientific papers. So there's a huge intellectual capacity here that we will use to our best abilities to help this community of quantum. We're based now in Espoo, which is very close to Helsinki in Finland. And we're looking also into expanding into other sites next year. So QMIL is really a quantum algorithm company focused on near-term quantum advantage. We are basically between the middleware and applications. We are connecting, we are basically enabling you to use the quantum hardware for useful applications. Because we think that advanced quantum algorithms will be indispensable for the well-being in the future. So the society in the future will run on quantum computing. If you take it away, lights go out. It's like if you would take now mobile networks away, lights would pretty fast go out. And our mission at QMIL is to accelerate the utilization of quantum computing by new quantum algorithm products or world-leading quantum algorithm products. So we make new algorithms and we make products very quickly out of those algorithms. Okay, here even in this room, and earlier you heard amazing talks by hardware providers. So the hardware is developing very quickly, and everybody has been saying is that, but how can you use this hardware? And I call that the algorithmic bottleneck, that the hardware is now and soon in the stage that can be actually used for something industrially useful, but we don't know yet how, or at least you don't know yet how. Because we think very soon in this level of 10,000 2-qubit gates, there will be quantum advantage with some narrow spectrum of applications. And when we go to about this 100 million gate level, the spectrum will expand, and that's why I call it the expanded quantum advantage. Before the full quantum advantage with the fully fault-tolerant quantum computer with thousands of qubits. Okay, but the most important point here is the first point, of course, the first inflection point. How can we achieve that? You need two things, at least. Of course, you need the hardware, but for the software side, you need very efficient algorithm that provides you something that classical computers can't, but it can at the same time be classically verified. I think that is the route to use cases, because very often in the industry, the problems are classical. If you don't solve a classical problem and you can't verify it classically, it is maybe there's a more narrow spectrum of use cases. Of course, then secondly, you need a very efficient way to compile it, execute it, because otherwise you still need to wait for the hardware to develop further. Okay, so now first I'm going to talk to you about the point one. There was already news out this morning about our new algorithm discovery, and I have never showed this plot in public to anybody else before, so you're the first one to see it. But let me start from last year. Last year we announced that we could achieve quantum advantage, classically verified, with 200 qubits and 4 nines of gate fidelity for the 2-qubit gates. Now, when you look at the plot here on the right, you'll see that we have been able to decrease the error by a factor of, or the error requirement by the factor of 6. So basically the error can be a factor of 6 higher now. So if you have nearest neighbor coupling and a square lattice, 99.94% 2-qubit gate fidelity, and only 48 qubits seems to give you as fast solution to this problem as it would take for the El Capitan, the fastest supercomputer in the top 500 list, to do the same as your quantum computer is doing. And this is classically verifiable in a matter of minutes on your laptop. So this is very different from any quantum advantage that has been claimed before. Well, this is only a mathematical modeling, of course. This is not real demonstration of quantum advantage. Our aim is to demonstrate this or next year with real machines. Of course, we want to do this as fast as possible. But this is very encouraging because we need so few qubits, and you have actually heard the number 48 before, at least twice before today. So we're pretty excited about this. In this plot, we have assumed 10 times better single qubit gates and no idle error. That's a little bit of a caveat. You have idle error in superconducting machines, so we still need to work on the gate depth. But we are improving this algorithm all the time. So I'm pretty convinced that this will provide us quantum advantage very soon. Okay. Secondly, we started to work on a circuit compression tool, a machine learning model, just for our own purposes to make this algorithm shorter. And then we ran it on these sort of benchmark gates that you see there. And it turned out to give better result than any of the other available tools that we had. So then we were very happy, but we thought maybe also others might want to use our circuit compression tool. So we made it actually already a product. So this is a containerized software running on AWS cloud. And next week, external users will start using it. We have a few pilot customers. We have already ourselves used our compression tool to compress their circuits. We could compress all of them. And now they're starting to use them themselves. And if you are interested on this, you can just book a demo using this QR code, and maybe you can become one of the pilot customers as well. You can use this through the graphical user interface or just from your Qiskit code or some other code with a single line, because it has API access as well. I have a little video also on the graphical user interface, how it works. So could you please play it now?
Compressing your quantum circuit is as simple as loading the QASM file into the platform and pressing the button Compress Circuit. The compression runs on a high-performance computer, and upon completion, the compressed circuit is also available as a QASM file. Both the original and compressed circuits can be run on a real quantum hardware through our platform, where the compression's advantage, higher fidelity, becomes evident.
You can either just compress your circuits, get the open QASM file, or you can even run it on quantum computers that are in AWS. And we can connect other quantum computers there very easily as well. So this is our first product. From the quantum advantage algorithm, we will add products as soon as we have shown the quantum advantage. And one of the first use cases of that is cloud verification of quantum computers to make sure that you're actually accessing a quantum computer, because that quantum computer solves the problem faster than El Capitan. So thanks for your attention. I'm happy to answer any questions.
Thank you, Mikko. Any question from audience? Yeah. Paranav, yeah.
Thank you, Mikko. That's very nice. On the quantum advantage estimates, can you describe what type of algorithm is it? Is it like a random circuit sampling or something related?
Yeah, it is not random circuit sampling, because that can't be classically conveniently verified. But it is, the quantum computer is providing, of course, samples. But then we have, it's a special type of a circuit the quantum computer is running. And that's why you can then classically verify that it's actually coming from running that circuit.
Cool. And do you know if there's a relation with the Google OTOC work?
There is no relation to that. This is completely different. The plot that I showed you from El Capitan is actually not simulating the quantum computer, because that's even slower. That is about solving the classical problem behind.
And is there a paper for that or coming out sooner?
What our kind of strategy here is to first demonstrate the quantum advantage with the actual machine, then publish everything at one go. We think we can create much more impact that way.
Great, it's very exciting. Thank you.
Thank you. Let's move to our next speaker. Thank you, Miko. We have a next speaker from Google, Amira Abbas, who is a research scientist in Google Quantum AI. I am going after her talk. Unfortunately, she has a flight. She cannot stay for the panel. So I am going to give her more time so people can ask a question since we are going to miss her. Thank you, Amira, please.
Cool, thank you. Thank you so much for inviting me as well. I'm very happy to be here. I'm Amira. I work in the algorithms team at Google and specifically focus on quantum machine learning, so the intersection of AI and quantum computing, what we've heard a lot about already today. So I kind of, I had the option of thinking about, what I'm going to tell you today. Like, I could probably broadcast a whole bunch of Google results and, tell you about all this work that's recently come out. But I thought what would be more meaningful is actually to give you some perspective on, where I see this intersection of quantum and AI. And specifically what I want to tell you about is this shift in mindset that I'm noticing, the Google team in particular, that's moving from a more theoretical, hardcore algorithms type research to what can we actually run on the devices that we're going to have. And if somebody gave me a quantum computer, tomorrow of a reasonable size, I don't really know with certainty what's going to work in terms of quantum machine learning, right? So I want to give you some real, critical points that I think we need to address as a community before we do interesting, cool research. And so actually what I think a better title for what I'm going to say is this scalability analysis of quantum machine learning models is what I want to tell you, and in particular in this early fault tolerant setting. And what I mean by early fault tolerant is imagine you have a quantum computer with 100,000 qubits. They're kind of noisy. They're not perfectly error corrected. What can you do in that setting, right? Okay, and I don't think we're doing questions in the middle of the talk, but I usually like to take questions. But anyways, keep them, and we have some more time at the end. Okay, so just very quickly for some context, in classical machine learning, very, very quickly, a quick story, there is this massive divide that already exists in classical machine learning between the theoretical and applied community, right? And this theory versus applied machine learning is the contrast is so evident that it really, really matters what type of applied research that you're doing. And what do I mean by that? Well, the theoretical spark for machine learning that we know today comes, I think you can trace it back to as early as 1943, right? Where arguably all of machine learning we do comes from one concept. If you trace it back to the first paper, I think it can go as far back as 1943, where this introduction of the first computational, this idea of having a computational neuron that can do binary logic, right? So this theoretical spark for machine learning already existed a very, very long time ago, where people kind of proved that if you have this computational model that mimics sort of neurons in the brain, we can maybe introduce this idea of training in machines, right? Learning and so on in machines. And so this is arguably the conceptual ancestor for machine learning today. But then some people came around and showed that there's actually a very trivial problem called the XOR problem that a neural network, a single layer neural network, cannot solve. And that's this XOR problem where you take 2 bits, you compute the XOR, and it turns out a linear neural network cannot separate this data, right? It can't learn data from this very simple function. And so this stalled the development of theoretical AI, theoretical machine learning, for quite a while. And so people came around and okay, let's make a quick fix. Let's add more layers to this single layer neural network. Let's make it more expressive. And then what can we do? And this was problematic because for a long time, adding layers, yes, allows you to fit more complicated data, but we didn't know how to optimize these models efficiently, right? And even when this groundbreaking algorithm backpropagation came around, and backpropagation, if you haven't heard of it, it's just a way to optimize a neural network super efficiently. Even when this came around, deep learning still didn't progress. It still wasn't, it still wasn't created. So, and then, Alex or Lynette, I think, is the correct name for the first, I think, generative model came around in 1998. So this was Jan LeCun's model where he like sat in front of a very, very old school computer and trained things to like recognize handwritten digits. This was like our first convolutional neural network. This still didn't push neural networks, machine learning into the right direction because this model that he introduced couldn't generalize, right? Couldn't like do other tasks. It was only sort of good at like guessing digits. And then came along Fei Li, and she introduced this massive, massive data set to the internet. And she was like, okay, here's a whole bunch of images. Somebody designed something that can like, do some interesting learning here. And so all I want to tell you is that deep learning only came about, like all of the nice machine learning we have today, came about through this applied spark that only happened in 2012 as a combination of these three things, right? So in came AlexNet, and AlexNet was the first proposal that used three different elements. It was able to use this backpropagation algorithm that could train stuff super efficiently. It was able to like generalize on lots of different images from different data, and that's because it thought about the hardware. It thought about incorporating GPUs to really like influence the design of the model such that it could like accomplish this generalization task onto other images and do wonderful things, right? And so the point I'm trying to make is that almost everything today in AI is actually about scale, and the theory is being left behind. And it's because there are actually like these empirically emergent phenomena that come at these very large scales where we now have like orders of billions and trillions of parameters on these models that you start to see things that you can't explain theoretically. So an example very quickly is like this idea of diffusion models, right? So if you open up Gemini and you look at the image generator like NanoBanana, all of these state-of-the-art machine learning models are often powered by this diffusion technology. And diffusion theoretically has a very, very simple idea. It's actually super, super beautiful. It's like I have an image, and then I just like add a little bit of noise to it sequentially, right? And if I do that slowly enough, right, eventually I'll end up with something that looks like total noise. And if I do that slowly enough, then I can train a neural network to uncompute the noise as well, because the inverse map, if I do it in a step-by-step fashion, is also approximately Gaussian, meaning it's easy for like a neural network to learn. And so this was like a nice theoretical concept, but in practice, nobody cares that this is the theory. What they do is they actually like hack everything to make it run on large, large devices, right? So they'll like scale down these diffusion models and use autoencoders and decoders and text models and like all of this conditioning just to make it work and run and scale and be super, super efficient. And so all I'm saying is that like people are putting less emphasis on theoretical innovation and really trying to think like, how do I actually run stuff? Okay, and then another example, for those of you familiar with kernel methods in machine learning, this is another example where you have beautiful theory, but people don't care because when you train these things, they kind of train quadratically in the number of parameters. So this is also pretty bad. It's a deal breaker. All right, so I kind of already said that. Okay, so now this begs the question, like, what do we do on the quantum side, right? When we have quantum machine learning proposals and models, what do we do here, and what are we doing, and what are we thinking about? So I think arguably the theoretical spark, I asked Gemini this the other day, like what does he think the genesis of quantum machine learning is? For those of you familiar, there's this paper called Quantum Algorithms for Linear Systems of Equations, and they introduced an algorithm called HHL. And HHL is really, really good at doing like linear algebra type things, but its output is still quantum state. And that's like not really very useful for us in practice right now. And so HHL, this theoretical spark, is arguably still decades away till we have fault-tolerant quantum computers. And so what people try to do in the quantum machine learning community, and I think we've heard like a few ideas around these models today, is they take a quantum circuit, they like have some tunable knobs in there, which they call parameters, right? You can like dial these things, like there are different ways you can imagine parameterizing a circuit. And then they look at the output of the circuit and they interpret that as some sort of machine learning label or equate it to some learning task. But there are many, many problems with these types of models, right? For example, this was mentioned earlier, like if you want to do optimization with respect to gradients, there's a phenomenon called barren plateaus where these gradients sort of concentrate and they vanish. There is also the fact that you can provably show that these models don't give you backpropagation efficiency. So that's also like a big, big problem, right? Like if you use these things, then there's just no way that they're going to compete with state-of-the-art neural networks if you scale them up, right? We're not going to get billions of parameters here and be able to train them like neural networks. And this is a really big problem. And yet like 90% of the quantum machine learning community are still using these parameterized circuits. And yes, there have been some theoretical ideas, some proposals for like how to bypass these issues, how to initialize a model so you don't have a barren plateau and so on and so forth. But I think the more important point is that nobody is really thinking about hardware scaling design considerations. These are all still just like theoretical ways to bypass these problems, these very real problems, right? And so what should we do? What should we do when we are in the early fault-tolerant setting, when we want to use these reasonably sized quantum computers and we think we can get some advantage here, right? Okay, so I'm going to tell you what we're thinking about and what we're shifting our mindset towards. And it's heavily, heavily driven by this publication here. So this is a paper that some of my colleagues put out, and it's literally just a way to cost out quantum algorithms, right? And it's actually a very, very hardware-driven sort of framework, right? So it's called the Flask model, and if you're interested, I put the screenshot to the title there. And the Flask model, if you just use this, and even if it sounds like a foreign language to you when you read it, you can just like pop it into Gemini and say like, I have a machine learning idea. It's this many data points of this many size. Using this as my cost model, can I actually like run this? What are the resources I would need to run this? And using the Flask model, you can already rule out many, many quantum machine learning proposals. And it also starts to inform your thinking about what better primitives look like, right? So this is what we're trying to use to sort of guide and steer model design in quantum machine learning. So what does this thing look like? Okay, so first of all, you can fix a bunch of parameter values for your hardware, right? So in this illustration, so I just like got a little bit lazy and started handwriting some back of the envelope calculations to illustrate the points I'm talking about here. But if you use this Flask model and you choose very, very optimistic like parameter values for this early fault tolerance setting. So what I mean like, if these words mean nothing to you, but I'm like you can take my word for it that I'm making very, very aggressively, what's the word I'm looking for? Optimistic assumptions about the quantum hardware. So I'm assuming things like magic state cultivation is essentially free, meaning like, magic states are things you need to do universal quantum computation, and I'm saying they're basically given to you for free, right? This is a very, very optimistic assumption. I'm saying like if you want to move ancilla qubits that help you do computation, this is also free. I'm saying that cycle times are 400 nanoseconds. It's like very, very fast. And I'm also saying probably the most maybe reasonable assumptions, but I'm saying that we're assuming physical error rates, so like the errors of my qubits are of order 10 to the minus 4. So for example, we want that number to be far, far lower, right? But let's just say we have these assumptions. Most of them are very optimistic. I'm assuming 10 to the minus 3, yeah. So that's like the most reasonable assumption I think I've made. Yeah, everything else like super optimistic. Okay, so what will happen if I have a device with those settings? And let's say I want to build what people call a quantum neural network. And the setup is I have inputs that are classical numbers, right? So floating point numbers. And they have, let's say, a single data point has 1,000 numbers, right? So 1,000 features, how you call them in machine learning. And I've got a data set size of 100,000. So I have 100,000 data points. Each data point is just 1,000 numbers. That's a very reasonable ask in machine learning, right? And now I want to, I don't know why that image is not coming up. All right, so I've drawn the circuit, but now all I want to say here is that with this data set, I'm going to need to encode it onto a quantum computer, right? So how do people do that? There are many different ways, but I think the simplest conceptual way is just to imagine taking those numbers and like turning the qubits, like changing the angles of rotation on each qubit by a value that depends on your data inputs, okay? So I can encode my data set by doing that onto a quantum computer. This is called angle encoding. And I usually want to do this with some precision. Okay, the image works now. Okay, and then I have a model, which is like some parameterized operations, that I want to do. Maybe there's some more rotations on the qubits. And then let's say the readout I do is like a single qubit measurement, and that measurement is going to mean something for my machine learning task. Like I want to do an expectation value with respect to like 1 qubit. And then I want to optimize this model, right? So I'm going to compute gradients, and I'm going to use this gradient information to go back and like change my parameters. So this is what people call a quantum neural network 9 times out of 10. So how much will this cost me in this Flask model? Well, if I'm doing angle encoding, if I'm taking 1 qubit to encode each number, I'm going to need 1,000 qubits. The Flask model tells me that if I'm being conservative, I need an extra like 40% of ancilla qubits, helper qubits, to help me do my operations. And if you just plug this into the Flask model, this already gives you a resource count of 630,000 physical qubits that you would need to actually implement this quantum neural network, right? So you're already out of this early fault-tolerant regime. You're already like asking for hundreds of thousands of qubits to just do this very simple machine learning model. But let's assume we can do that. How much will it cost me in time? Well, I'm saying that I'm doing a number of rotations that's like roughly of the order 100,000. Why? I'm using 1,000 of them to encode my data, and then I have a model of 100,000 parameters. This, if you plug this into the Flask model, equates to roughly like, let's say for each rotation, I would need something called a T-gate, and I would need 10 of them, right, to do each rotation. A T-gate is something you need for universal quantum computation. And not so important, but you can also compute some other things that eventually tell you this idea of how many time steps, logical time steps you need, and long story short, you can compute other objects that are interesting, and eventually you'll get to a wall clock runtime, like per circuit execution, that is something like 2.8 seconds. Okay, so that sounds kind of reasonable. That sounds decent, right? But there's also this sampling overhead, because with each shot that you do on a quantum circuit, there's some noise, and so you have to sort of repeat the experiment. And if we have the parameters that I told you about earlier, this overhead for sampling is roughly about 50 times. So you have to like rerun this experiment. So this will equate to like a single error mitigated shot of roughly like 2.3 minutes. Okay, so that's just 2.3 minutes to get a single data point onto a quantum computer and run it a few times so that the output makes sense. So that's roughly what inference would cost me in a quantum AI, quantum machine learning setup in this quantum neural network picture. How much does gradients cost me? And here's where things get really, really bad, right? So if I was running things over and computing one gradient epoch, one training step for the entire data set, this would cost me roughly like 43,000 years, okay, with these very, very optimistic parameters. And so even, and this is without backprop scaling, let's say even hypothetically, if I had backpropagation scaling, super efficient linear scaling parameters, this is still 160 days. Okay, so even if I was able to like prove this efficiency in line with neural networks, this model is just not going to be optimizable, if that's an English word, with gradients. Okay, so it's like really bad. And even if I took away the need for sampling for this like error cancellation that I need, this still costs me days. So I'm still like really never going to compete with state-of-the-art neural networks. So the point I'm trying to make is we need to shift away from like 90% of how people do quantum machine learning to another type of model, right? And a model that really can scale and run on a quantum computer that we are building today. And so what I want to make a pitch for is models in this flavor of this paper that some of my really brilliant colleagues developed. And they call it like a shallow quantum circuit model. Shallow because the circuit is literally not very long, right? It's constant depth. And if you're interested, this is like a snapshot of the algorithm. It's also in the paper. But the algorithm is very simple. It sort of like encodes your data in a single layer of parameterized rotations, like we talked about. It does some like entangling gates, and then it just measures. Okay? And this model has some really nice provable statements about it. So for example, you can prove that it is capable of sampling from distributions that are hard to sample from classically. You can also prove via some like light cone arguments that the input qubits don't talk to too many output qubits. And so you can actually efficiently optimize this thing. So when we plug something like this into the Flask model, we get much better scaling. So for example, the wall clock time per shot is now 0.028 seconds. If you had this need to do this error cancellation, this probabilistic error cancellation stuff, the overhead is also much more reasonable because the circuit is shorter. And so one error mitigated sample is roughly like 0.056 seconds. And this is the time it would cost to do inference. And here's the beautiful thing. The beautiful thing now is that this model, like I said, because it's short basically, it's also optimizable in a reasonable amount of time. So you can actually compute gradients here much, much more efficiently than like just doing a naive neural network, quantum neural network. And so if you had like this error cancellation necessity. This would cost you like 15 hours to do a full gradient epoch, still quite bad. But if you didn't need error cancellation, then this would be like 7 hours. Okay, so now at least we're in the order of hours and not years. So what are the takeaways in the last couple of seconds that I have? Well, it's just the following, right? It's like, okay, we have some ideas of how to do quantum machine learning, but we should really think about them in terms of a practical point of view, right? Because most of machine learning today is just empirical success, right? It's like these try and see experiments, it's these things that we can scale up. We don't care about explaining the phenomena we see theoretically, we care about if it works. And so if we can't even run our theoretical proposals for quantum machine learning, this is already going to kill us, right? So we need to think about, okay, we need to be aware of these scalability issues. We need to have design choices that are influenced by the hardware that we have, right? And maybe most importantly, we need to like sort of shift our thinking to like coming up with these provable separations, these provable advantages, in quantum machine learning, and more like to what models actually are scalable and how can I think about solving useful problems with them, right? So this is basically all I wanted to say. Okay, good. Thank you for listening.
Thank you. Thank you. That was a great talk. Any question? Yeah, we have. Oh, we have a while. Okay. Yeah, let's start. We go from the front to the back. Yes. Okay. Sorry, companies. Yeah, you have to use microphone. Sorry, because online audience we have quite a lot. Yeah.
So just a couple of things. So one is your assumption. You talked about encoding this. You have 1,000, let's say a real valued vector of 1,000 elements. Mm-hmm. And the way to encode that into a quantum circuit would be through angle encoding, right? Mm-hmm. I think there's something broken about that assumption to begin with, because even if you do that, the model you get will not be very expressive. It'll just be like a linear trigonometric polynomial in each of the things, right? And there's ways to compress that much more so that the loading becomes much more efficient.
So what do you mean by compress?
I'll talk about that in my talk. Okay. But compress as in you use efficient techniques on the classical side to, for instance, encode each real valued vector as a bit string. And then loading a bit string is just some X gates, right? Mm-hmm, mm-hmm. And so you can show that this can be done very efficiently on the classical side. So there's a lot of assumptions in that parametrized quantum circuit analysis that you did that I think are a little bit dated now.
Absolutely. Yeah. No, I couldn't agree more. I think the hope is that the community, so people are still doing this, and I think the illustration we want to make is like, don't do that, right? Like it's not, and think of better ways. Like you're already suggesting a different encoding that would make more sense. Totally agree. I think there's a lot wrong with this proposal for quantum neural networks. So
yeah, the angle encoding certainly.
And angle encoding, even amplitude encoding actually also is problematic. Yeah.
Can you say again what is the difference that you're proposing with the shallow circuit compared to the previous?
Yes, that's a great question. So just to be more concrete, right? So this shallow circuit, there's a couple of things. So because of the way it's designed, it's very simple, but because let's see, how do I explain this nicely? So there's a light cone argument, which I mentioned very briefly earlier, that ensures that like your input qubits sort of only talk to a finite number of the output qubits that you measure. So having this property ensures that you can compute what we call like expectation values with respect to local observables, meaning that you can sort of get information out of your circuit efficiently. And you need that information typically to like go back and optimize your parameters in your model, right? So it's a long-winded way of saying these things are trainable. So that's good, right? They're trainable, and as you scale them up, they don't become more expensive to train. It's sort of like a very nice scaling in the trainability. So that's great. So it ticks that box. It's also fairly straightforward to put data in. And then lastly, it's got a very, very important property that we need to sort of use to argue against the classical machine learning community who always come to us and say, why are you doing that? Like, why are you putting a quantum circuit in this model that already works so well? It's got a property that you can prove that the shallow circuit can sample from distributions that a classical computer cannot sample from. It's really hard. It will cost you exponential time on the classical computer to sample from these distributions. So it can sample from provably hard distributions. They are efficiently trainable. The last thing, which we don't have, is what can we use them for, like a useful problem. Yeah. So to make money. Yeah, to make money. I don't know. Like, I guess you should care because like if we build the computer to a large enough scale, then we can use this to like do the try and see experiments, right? And hopefully find something that is cool, that is making us money, right? I mean, making you money. Sorry, that was your goal, yeah. I already make some money, that's okay.
Okay, I think next question, yeah.
Yeah, thanks for the talk.
Where are you?
Just a little bit.
Hi.
Maybe a little bit technical comment on the training side and the arguments that you were making.
Sure.
I mean, obviously, you're ignoring the fact that you can do data parallelism. I mean, okay, so you need multiple QPUs, but you don't need quantum communication between them, right?
Mm-hmm.
So you can, all I'm saying is this argument that you're making is a little bit flawed in the fact that you can do data parallel and reduce that time significantly.
Sure.
Yeah, but that requires many QPUs, I agree.
Sure, I mean, the qubit count in absolute values would still be this. Well, actually, yeah, you're right. You can just like run things in parallel if you had multiple QPUs of 1,000. Yeah. That's true. And there are many, many other things you could do to get that cost down, right? Like, you don't have to have a parameterized model that's so big, right? 100,000 parameters. Maybe there's something cool you could do with a shallow circuit type argument, which is exactly the next point.
Definitely, I see the advantage of moving to a shallow circuit. It's just I'm saying the argument is flawed in the sense that you can do data parallel, or maybe all sorts of tricks that we have in AI. I mean, right now, majority of audience are quantum people, so they may not be aware of all these technologies and like AI training for large models. That we are facing similar situations there, where the iteration time is slow, but you can parallelize a lot so that you can train on large data sets, trillion of tokens in a feasible time.
So I'd like to maybe just caveat that I'm not advocating for a quantum neural network that runs like that, right? Or that is designed like that.
No, I'm just saying the need to go from the first one to second one.
Yeah.
Like the numbers are like right now, the way you wrote it is like so pessimistic. I'm
exactly,
just saying
and that's the point. It's more the illustration of how bad it could be if you were doing something in the most naive sense.
I see, okay,
versus
if that's so.
Actually thinking about your design considerations, right? And one more thing is that most of the community think like that in the naive sense, right? I think like a lot of people, like I was just at this quantum techniques and machine learning conference. This is, I think, the biggest quantum machine learning conference we have right now. And there's hundreds of PhD students constantly running circuits like this. And the point of this type of, hopefully like perspective piece that will come out is to just illustrate how bad this naive approach is, right? And then encourage people like you to say, okay, but I can parallelize, or I can not use optimization like this, or I can do something more clever with my encoding, So that's the story I want to tell. So not like this is a good idea type of thing. Yeah.
Okay, thanks.
Sure.
Peng, do you want to go, Peng? Yeah.
Okay, so I guess my question is like, so the short question is that why you limit your error rate to 10 to the minus 3 or 10 to the minus 4? The reason I'm asking is that in 2017, MIT already shows that in your training, you don't have to worry about your error so much. They already demonstrated in their optical neural network, an analog can give you a pretty good result. And also, especially you also mentioned like the main benefit comes from sampling. Right now, the Boson sampling and random circuit sampling can already give a pretty good result. So why you limit yourself to 10 to the minus 4?
Sorry, just so I can check if I understood your question. Is it like you're saying, why am I assuming 10 to the minus 3 and not 10 to the minus 4?
No. Why you limit your error rate to such a low level? Because people already show that it doesn't care so much error.
Okay. Yeah, it was honestly just a back of the envelope calculation. Maybe you can have a better error tolerance in real life. Maybe the models can be robust to some sampling error. But what I should say is that I didn't even include, for example, when you do expectation value shots, you need to fix some output precision, right? You need to fix some epsilon, and then you typically like sample like 1 over epsilon squared times, or sometimes 1 over epsilon times. I didn't even do that, right? So there's an additional 1 over epsilon squared factor of output precision missing from all the calculations, which makes things even worse. So maybe that like sort of offsets my pessimistic, 10 to the minus 3 estimate.
Okay, thank you.
Sure.
Is that on? There we go. Hey, so is the kind of anaphylactic response to some of the numbers aside, is the right way to read this, read your argument here that, taking close analogs either to the cool applications that are being used and useful applications of machine learning, or the kind of architectural model designs is the wrong way to approach this, and we really need to be thinking about both applications of quantum machine learning and kind of architectural model choices associated with quantum machine learning that are architecturally different? Is that kind of the appropriate takeaway, not the back of the envelope? Okay.
Yeah. I think that's actually quite very well put.
Okay,
cool.
The last question, yes.
Oh, I was a little confused about something that you said on the shallow models, where it seemed to me that what we were saying is that you sort of have localized entanglement. And that to me means that sort of you can split the system and then it's like relatively easy to simulate, but then you say, no, this generates things.
From a hard distribution.
Yeah.
So it's a little bit technical, but I think what you can do is you can sort of, there's this mapping from these shallow models, if you set it up in this certain way, to a how do you call it? So imagine, so a shallow model is like very wide, so lots of qubits, right? And then constant depth circuit. You can map these using like a measurement, this like measurement-based quantum computing type framework. You can map this to a smaller width model with longer time. So there's like this trade-off between width and depth. And so you can map it using this like measurement-based quantum computing argument. So they're like these mid-circuit measurements that you would do and this feed forward. And this gives this the model this expressivity power. So even though it's shallow, like it maps to something very complicated and in theory can sample from an ensemble of distributions that's hard to sample from. So.
Isn't there some conservation of the quantum volume, and that's kind of ultimately the...
Yeah, I don't know. I don't know how to, I don't know. Would have to see the paper. It's probably in that paper. It's very long.
Fair enough. Yeah.
Awesome talk. A lot of great discussion here. Just a very specific question on the slide with variational quantum algorithms. If you go back, maybe it's like 10 back or something.
Like the scaling?
I think there's something, I saw it briefly about back propagation, or rather parameter shift is quadratic, unless I read that wrong.
Yes.
I was just going to ask you to explain what that meant.
Yes, of course. Right, so I can just tell you. Right, so this parameter shift rule, if I assume my cost model, like let's say I have m parameters, and if I assume my cost model is unit cost for each parameter, right? So now if I run my circuit once, it's going to cost me m units of computational time because there's m parameters in there, right? And now for parameter shift rule, I need 2 circuit runs for every parameter, and there are m of them. So now I'm doing m times, and then twice. So it's 2m squared.
Got it. Thanks.
Sure.
Thank you, Amira. That was a great talk and conversation.
Oh, this is it.
Yes. So we swiftly move to our next speaker. We have next speaker from quantum research at HPE, and we have Marco Fiorentino. He's a senior distinguished technologist at Hewlett-Packard Quantum Lab.
Thank you. Right. Okay, thanks a lot for the introduction, and thanks for having me. Really, really fun to be here. I will talk a little bit about quantum research. Sorry, the title is pretty boring, but I would say some of the ideas that we have about quantum computers and integration of quantum with high performance computer at HPE, and what are the applications that we think are credible, and how we move around to getting to the place where we can actually do things that are useful. And so this is pretty, probably have seen some of this, and this is kind of what we worry about at Hewlett-Packard Enterprise. We are kind of the largest provider of high-performance computer in the world. compute is not keeping up with the amount of data that we have. With forget about how fast the models, the AI models are growing. So this as you can imagine is a big problem for us. And so everybody says, hey, what about quantum? I have a bunch of headlines here. I could have probably taken this. These are kind of old, but everybody's saying, oh, quantum will resolve all our problems. And I think I don't know, I think it's kind of somewhat uncontroversial, but we kind of, I'm gonna build this one, oops. But we think for a good candidate for an algorithm or something that's useful, you kind of need these three things. And I apologize, this might be too stupid for this kind of audience, but you need a few data in, an algorithm that can run with an exponential speed up and a small amount of data out. If you don't have these three things, then any advantage that you have from a quantum point of view will be eaten up by something else, data, the number of data, or you kind of how much measurements you have to do, and sort of you're kind of going to be it's not going to be you're not going to be able to beat classical computer, and by those I include things that might be more as analog computers than the digital that we have, but nevertheless you don't need to be in the quantum regime. And so again, that tells me that essentially quantum computers are not going to replace classical computers, at least in our view, anytime soon. And so the way we see this is as a kind of we go along the way to a large-scale, utility-scale quantum computers, is that essentially we see a quantum computer as an additional accelerator. And so we think of it as an accelerator to traditional high-performance computers. And why high-performance computers as opposed to like data centers? And the reason is that the applications that we think are kind of reasonable for a quantum computer, sorry, I'm going to build up this one as well, but the applications that we think are kind of credible for quantum computers are typically in sort of scientific computing type of applications. And so, that's already something that happens in HPCs. And so we think that quantum computer is going to be sort of an ancilla to high performance computer. And so, essentially there are things that kind of deal with quantum data. So quantum chemistry, material designs, drug discovery, fundamental physics, things of that nature. Those are things we think the places where a quantum advantage will show up. Of course, there is the encryption, Shor's algorithm that technically has classical data. There's a very small number of inputs and a very small number of outputs, and that's why Shor algorithm it's kind of proves that in a way kind of aligns with those 3 points that I was making before. But so this is the type of things that we think are credible, and I kind of have a little sort of anecdotal evidence. I was in a panel, I was actually moderating a panel a couple of months ago, and I kind of asked the panelists, so what do you think are the reasonable application for quantum computers? And everybody came up with exactly this. At some point, I'm like, this is boring. Somebody argue and start fighting about something, but everybody, it seemed to be very uncontroversial, at least in that setup. And the other thing that we kind of need to figure out in our view is it worth it? And so, meaning if you have this specific applications, and this specific application have kind of a market value in a way, right? So is it worth the investment that we're putting or into quantum computers? And is it worth the cost to build and run the quantum computers? The quantum computers will have kind of a limited life. And so you add up all those things and you add up all the things that, the value that you can get out of it, is it worth it? And, we did some of this, and, probably other people that were in the QBI program had to go through a similar thing. And sort of the answer is really maybe. I wouldn't say it's a resounding yes, but it's not too far. And so I think it's worth, and for sure there are things we're not, we don't have necessarily all the smart people, but definitely there might be a lot other new ideas, new technologies, and so it might get better. It probably can also get worse, but in general, I would say the answer to this question is maybe. So why HPE? Why HPE is interested, probably kind of, I say that, but why do we think HPE is kind of well positioned to make a good contribution in this space? And we think that sort of one of the key things that we think is true is that to achieve utility scale, you need integration of quantum computer with high performance computer, and obviously HPE is the prominent company in high performance computing. You also need networking, where we also play pretty big role, especially in the HPC world. And so, that kind of gives us a right to play, so to speak. And the other thing that we think is needed and we think we can bring to the table is kind of a quantum environment. And by this, I mean a programming environment. And our idea is that that programming environment will have to be something that people who are used to program HPC, high performance computers, can be familiar with. And so the idea is really, how do you build a quantum computer that can be programmed and utilized by somebody who is not in this room, essentially? And so that's the type of thing that we're trying to build and we're trying to develop as this quantum development environment. And so, a lot more detail about this vision and these ideas that we have has been published in this paper. There's, in addition to Hewlett-Packard Enterprise, there are a lot of other collaborators from industry, academia, national labs. And so, it's a long paper. There's really a lot of, and one of the interesting thing that we think was very interesting about this collection of people is that we were able to collect people that went all the way through the various different kind of layers of the quantum computing stack. At least as we see it, we had people that can work on simulating and sort of making sure that when you build something, it comes out the way you want it. The people that design and fabricate qubits, the people who build the control hardware, compilers, emulators, and at what we consider the top of the stack, HPE, which is really an expert in software and hardware integration. And that's kind of the other thing that the way we see that HPE might have something a little bit different to bring to the table, which is we are not planning and we have no plans to build our own QPUs. We kind of a lot of the things in this stack have no plans to really do ourselves, but we want to partner with people and bring them in and essentially kind of you teach us how to build a quantum computer, we teach you how to build an HPC, and we can integrate that. So that's really kind of the goal. And also we kind of build the software stack that can be used by people that people are kind of familiar with. So that's kind of where I am. And so I'll close here. I don't know if there's any questions.
Thank you. I think since we ran a little bit, one question, and we then leave it to panel, the rest of questions. Yeah.
Every time when I see cryptography, I cringe.
You cringe.
Yes, because since 2013, the whole internet has been covered by the perfect forward secrecy. And if you take into real life examples, quantum computer, the modern cryptography is quantum resistant. That's one part. And the biggest valuable part that is out there is the Satoshi Bitcoin block, which is currently about $125 billion worth. And this is the one that you could break. But then you have legal issues. But collecting now, storing now, and breaking later, I don't believe that.
Perfectly in agreement, and I want to say HPE as a company. Sorry, I think we're kind of working in post-quantum, and so you're not getting any argument from that. But I have to say, do not discard. I mean, there was somebody who was actually making a business case for breaking the Bitcoin, not for the Bitcoins that are owned, but the Bitcoins that have been lost, where nobody had. And that's still 8 billion. So hey, I don't know how much it is.
Satoshi block is 125 billion alone.
But some of those are kind of owned by people, right?
Satoshi is one owner. The founder of Bitcoin, the mythical founder, his block is 125 billion alone.
Okay. Anyways, I mean, I do not want to kind of, count me out on breaking that, but it still exists.
Thank you, Marco. Thank you.
Thank you.
So my pleasure to introduce our next speaker, Sonika Jory, CEO of the Coherent Computing. She has a great and impressive background of scientific publication on quantum algorithm development. And before I believe, is her own startup that she's CEO, but before that, she was the senior scientist in IonQ. Please.
Okay, great. Hello, everyone. Thanks to the organizers for putting together such a great event, and thank you for the invite. Okay, these slides are. Oh, this is showing the next slide. Okay, got it. Yeah. Hi. So Coherent Computing is a new company, and many of you may not, or I guess most of you probably don't know what we're doing. So we are a quantum software company, and our flagship product is going to be Red Cedar. And this is going to be a quantum computing stack that has all of these nice properties. It's going to be scalable, modular, portable, and user-friendly. The overview of the stack is shown here, right? So the top of the stack is obviously hardware independent, and the bottom of the stack is hardware specific. The top of the stack integrates with APIs for different use cases for domain experts in different industries. And the bottom of the stack will integrate with different quantum hardware APIs, whether it's superconducting qubits, photonic qubits, trapped ions, neutral atoms, whatever. And whatever other technologies emerge. And in between these two limits, we are designing our stack to have a number of layers, ranging from quantum application libraries to a quantum programming layer that we call quantum structures, where quantum abstractions, such as tensor networks or Hamiltonians or Bell states, different kinds of entanglement patterns, group theoretic structures are first-class objects in that language. And then our compilers will lower quantum programs implemented in that language to high-level quantum circuits, which are then lowered to hardware-aware quantum circuits, which are then interfaced with quantum hardware APIs. So anyway, that's the long-term plan for the company. In the near term, the first application that we're looking at is quantum machine learning or quantum AI. And we've heard a lot of very nice talks about the hardware, about all the cool hardware that's being built. And a question that's come up again and again is, what should we use this hardware for? And here I will talk about the possibilities of using that hardware for quantum machine learning for classical data. I know that there's been some work done on using quantum computers for quantum data, but the reality is that most of the HPC compute and data center compute nowadays is on doing AI on classical data. So if we can get some kind of quantum advantage over there, it's going to be very, very impactful in a lot of different industries, right? But unlike applications of quantum computers in areas such as factoring or chemistry, where there's those applications rest on a very solid theoretical foundation. For real-world classical data, there's very few theorems that we can use to analyze quantum machine learning. And so we really have to kind of answer very, very basic questions, right? So how do we even map learning problems to quantum computers? How do we identify which data sets are likely to have quantum advantage? And once we do that, how do we scale the training of quantum models? And Amira's talk, of course, address some of the issues in the ways that people go about answering these questions, right? So here I'll give an overview of the way, I'll give an overview of the techniques that we're developing to answer these questions. So the first thing is, we're working with classical data, and we want to build a model that runs on a quantum computer that captures essentially the correlations in that data set, right? And what turns out to be very, very important is the way that you encode your classical data into quantum states. So I'll illustrate by the example of classification, which is one of the simplest formulations of machine learning, where you're given a data set which has samples X and Y, and what you want to do is find an efficiently computable mapping between X and Y, right? And so the first thing, of course, you want to do is load your data into the model, in this case, a quantum model. And it turns out that in quantum machine learning, if you choose the wrong data encoding, right, no matter how fancy of a quantum neural network you build, your model, if you don't choose the right data encoding, your model will just not be able to learn the relationship between the input and the output, right? So basically, the data encoding in quantum machine learning constrains the expressivity of the model very, very strongly, right? And so two of the common methods people use are amplitude and angle encoding. And the amplitude encoding is actually very bad. It just leads to essentially models that are linear in the encoded data. And angle encoding essentially leads to trigonometric polynomials, where the degree of the polynomial will be constrained by the number of times you upload the data into the model, right? So these are, you shouldn't, and Amira pointed out that most of the students, or most of the research projects that work on quantum machine learning will typically end up using one of these two encodings. But in our work, we've proposed this new kind of encoding scheme called bit-bit encoding, which actually leads to unconstrained expressivity. It saturates the expressivity of the model. And so what is this bit-bit encoding, right? So in bit-bit encoding, what you do is you encode both the input and the output of your classifier as bit strings. So you are essentially, your original data set consisted, let's say, of a function where the input was a vector of real numbers and the output was again some kind of real number, let's say. But you approximate that data set as a binary problem now, right? And in the equation here, you see that I've encoded the input bit string in one quantum register, and I'm reading out the output from another quantum register. Now the question is, real data looks like images, or it could be a data set of, let's say, some kind of gene expression, or it could be a data set of text, right? And those are typically not bit strings, right? And if you naively try to encode an arbitrary vector as a bit string, the number of qubits you would need is going to be extremely large, right? You would maybe need 1 million qubits to encode even an image from the MNIST data set, which is one of the most basic benchmarks that people use in machine learning. So instead here, our idea was to figure out how to extract the most predictive bits from each sample in the data set. And it turns out that it's actually not that hard to do. You can do some, you can start with, you have your original data set, and you can do some kind of efficient dimensional reduction scheme, such as PCA. And once you've done that, you've taken your original data and reduced it to a smaller number of dimensions. And then you can measure the mutual information relative to the learning task for each dimension, and the directions which have more mutual information are assigned more bits, right? So let's say you have 10. Let's say you want to encode each sample in your data set with a bit string of length 10. So in the example that I've shown on the right here, I've done the procedure outlined on the left, where I've done a PCA on the original data set, and then I've measured the mutual information. And then when I have a bit string of length 10, you can discretize each of the PCA directions. And in this case, you're assigning 3 bits to the first dimension and 1 to the rest of the dimensions. And does this work? And it turns out that this actually works extremely well. What you can show is that when you have very few qubits, when you encode your data set in this way, you're going to have collisions where each encoded input corresponds to more than one output. But as you increase the number of bits, the fraction of the collisions goes down very, very fast. And then you can essentially create this resource estimation framework where you figure out how many bits you need to encode your data set to 100% accuracy. And that tells you that once you have that number of qubits, you are going to be able to you don't need any more qubits basically to encode the information that is already present in the data. Right, and it turns out that each image in the MNIST data set, it's a grayscale image which has 700 something pixels, right? So if you try to encode it with the angle encoding, for instance, that Amira showed, you would need 700 qubits. But instead, it turns out that you can encode it exactly in about 27 qubits over here, right? And so with bit-bit encoding, you actually require much fewer qubits while maintaining full expressivity, compared to compared to how many qubits you would need for using a naive basis encoding, right? And now what this gives you is a way to figure out which data sets have quantum advantage, right? So we define in one of our papers this resource metric Q data set, which is essentially, the technical definition is the number of qubits required to encode both test and training data without collisions. And so on the left over here, you see the MNIST data set takes 20-something qubits to encode to 100% accuracy. Then we went ahead and looked at all medium-sized data sets on OpenML and found that most of them require only 20-something qubits to encode. So these data sets are not a good fit for quantum advantage, right? Because if something only takes 20 qubits to encode, you can just solve it on a classical computer or with a classical circuit simulator. So that's not a good fit. But then we looked at this gigascale data set, which is this Tahoe data set, and which has millions of samples and hundreds of I forget, I think it has hundreds of thousands of features even. And there you see, you start to go into the regime where to encode the data set, you need hundreds of qubits to do that, right? So that data set then is a good candidate for quantum advantage, or at least for trying out, or at least for trying to model it with quantum computers. Right? Whereas most medium-sized data sets are not good candidates for quantum advantage, right? And so this is a tool that we're building out, and hopefully it should be online soon for anybody to upload a data set and figure out how many qubits are required to encode it, and whether that, and you can use that tool to figure out whether the data set you're considering is a good fit for quantum computers or not. The lesson of all of this is really that, when you're thinking about quantum AI, you should figure out how to combine the best of quantum and classical, right? Classical computers are efficient at things like arithmetic or trigonometry or calculating polynomial functions, and quantum computers are good at modeling high-dimensional correlations or sampling from non-trivial probability distribution. And so what we're building within Red Cedar is this kind of data flow framework where you have custom interfaces that handle the probabilistic output of quantum transforms. And so then the data just flows very smoothly through either, whether there's a quantum transform acting on it, classical, quantum, classical. And the simplest version of this is shown on the right. There's much more complicated versions of this as well, of course. Okay. And so in Red Cedar, one very nice thing we're doing is we are providing two modes of operation. So we don't call them quantum neural networks because that's not quite accurate. The quantum models are not really neural networks. We call them entanglement nets. And we've extensively tested out some quantum entanglement net designs, right? That should be available for immediately training on your data, but we also are building a framework which provides abstractions for people to build their own custom entanglement nets, right? And these abstractions, as you can see, are quite different from what you would use to design a classical neural network, right? So here you would have things like Hamiltonians or symmetries or defining quantum spaces, which you can then compile down to different kinds of hardware backends, things like that. Okay, so so far I was talking about how you load your data, how you can design different kinds of entanglement nets. Another very important thing is how do you train your entanglement net. And here it turns out that classical optimizers or classical gradient descent is not really a good choice for training quantum entanglement nets because classical optimizers come with all this baggage, right? For instance, if you use gradient descent or Adam, something like that, you need to set a learning rate using educated guesses. And there's no guarantee of convergence. You also may need to store the memory of the optimization, right? So that makes it very memory intensive. But what's very cool about quantum machine learning models is that they are much more analytically tractable. So that you just know the analytical form of them much better. And you can actually train them without using any kind of optimizer, but by using sort of analytic updates, where if you update just one parameter at the time, you can find the exact formula for the minimum, right? So you don't need to use any kind of gradient descent. Another interesting thing that we found is, if you try to train a quantum machine learning model from scratch that's very, very big, you're going to run into this issue of barren plateaus or zero gradients. But one very straightforward way to address that that is very compatible with our bit-bit encoding scheme is to first train a model that is small, right? And then use that to initialize a larger model where the new operations in the larger model are set to identity. And because of the mathematical structure of quantum entanglement nets, this operation is exact. So the quantum model, the bigger quantum model on the right, is exactly equivalent at initialization to the quantum model on the left, right? But it has more expressive capability because it has a larger input, right? And so putting all of this together, what you see here is that you can iteratively train a very large quantum model, where the training of the smaller models becomes a critical step in the training of the larger models. So here you see on the right, for instance, a 6-qubit model is trained, and that is then used to initialize an 8-qubit model, which is used to initialize a 10-qubit model, and so on. And this means that actually, in some sense, near-term quantum computers can contribute to building large models. So suppose you figure out that to model your data set on a quantum computer, you need 200 qubits. It doesn't mean you need to wait until your hardware has 200 qubits. If you have a 40-qubit simulator today, train your model on the 40-qubit simulator. Next year, you have a 50-qubit quantum computer. Train use the model you trained today as a starting point for the next, for the 50-qubit model, and then so on and so forth, right? Yeah, okay, so I'll stop here on the technical results. We're, of course, working on many other things at the company. We are designing operator theoretic compiler specifically for quantum machine learning algorithms. We are very, very interested in benchmarking real-world quantum advantage for machine learning, right? And that is, of course, very empirically driven as well. We're working on some emerging applications, such as fine-tuning LLMs with quantum computers and modeling chemical properties, and also have a real focus on using QML for biology applications. Yeah, okay, so I'll end here. I'm at the end of my time. My message to different organizations today would be that if you're interested in machine learning and AI in general, and you want to see what this new emerging technology of quantum computing can do for you, you can already start trying to identify which applications, domains, and data sets are likely to have quantum advantage. And then you can already do this fruitful thing of using simulators and small quantum computers to train small models, which will become the building blocks for larger models in the future, right? So you don't need to wait 5 years till you have 1,000 qubits to do something useful with the quantum computers today. Okay, I'll end there.
So I am very glad we had two women speakers, both of them great talks. So any questions? Yes.
I have a question mainly about could you explain a little bit more on why for some specific classical data sets, quantum machine learning actually works better than classical machine learning? I'm confused because if I ask a person doing CNN, say, hey, why it works well for the image recognition, he will tell me because the image is based on the 2D correlations, and the convolution itself naturally works for this. Could you share some insights like this?
Yeah. So, okay, the hand-waving answer, right, would be you can model high-dimensional correlations, or some kinds of high-dimensional correlations you can likely model better with quantum states rather than with classical methods, right? That's a hand-waving answer. I think the concrete answer will be very, very domain-specific, and that's I haven't covered that here, right? Over here, I'm just talking about how many qubits it would take to encode a data set, and the second part of figuring out the quantum advantage is actually to figure out, do you need fewer parameters to, let's say, model a data set than you would need with a classical computer, right? So that's the second part, which I haven't touched on over here.
So can I say for the high-dimensional data that it takes more computational power for the classical neural network, but it's gonna be easier for the quantum?
Say that again?
And for the high-dimensional data, if you train it with the classical neural network, it's gonna take more power, computational power, but for the quantum ones, it's gonna be easier. Is that your conclusion?
I think what you can say is that there should exist some data sets for which it is easier, right? And then our task is to figure out which data sets there are. So then if you are like an end user, you have a data set, before you go off and invest in building a large classical model or a quantum model, you can, before you invest in the training, you can do some analysis and figure out, is my data set appropriate for quantum learning or classical learning?
Okay, thank you.
Thanks for the talk. I have a kind of a little bit technical question, which may have like long-term, which may have like some long-term implications, I would say. So how robust is this encoding that you guys invented for out-of-distribution data? Like, let's say you said you find this, you run and you find some PCA on some training data set, but let's say later on you decide to change the data, you do some supervised fine-tuning.
Yeah.
So do you need to redo the encoding? Or?
Yeah, so what we found, so it wasn't just PCA. We looked at a bunch of, so on the x-axis of the middle graph here, we tried a bunch of dimensional reduction schemes, right, on some standard data sets, and they gave almost the same answer, right? But it is true that the dimensional reduction you do can be very, very domain specific. So for instance, we were looking at time series data, right? And their PCA does not make much sense, right, on the original data. It's much better if you do a Fourier transform or something like that first, and then you run some kind of dimensional reduction, right? So I would say that the solution that I've presented here with PCA, it's like 90% there, but 10% of it will be customized to some specific domain area or to some specific learning problem that you want to answer. So there's a lot of scope for adjustment here. This is just like a very general framework.
I mean, one of the big things with large models in general, apart from large language models, is this concept of generalization. I know it's still kind of subject of,
yes.
It's under debate, but one of the big things in like classical AI is generalization. And my question is whether this idea of kind of efficient encoding undermines that, or because the claim is that the model, if it is large enough, it can generalize, right? So you train on like some data sets, but then it can kind of generalize to other out-of-distribution data sets. I mean, that's what we are seeing like in LLM, for example.
So if you go and look at a paper, so if you look at the curve on the left here, there's a training curve and a test curve, right? So what you do is you calculate the encoding for on the training set, and then you figure out how many collisions are happening on the test set, right? And that gives you some estimate of what your testing accuracy, the maximum attainable testing accuracy of your model with that encoding could be as well, right? So there, we haven't gone in and completely analyzed like, what different encoding would lead to better generalization, right? At least theoretical generalization.
Right.
But this an analytical frame or this framework of analysis can give you some indication of it as well.
I see. So if I want to summarize, then this type of like encodings and all these tricks are not kind of competing with generalization, or you have good evidence.
No, they should not. Theoretically, I don't see why they would.
See. Okay.
Yeah.
Thanks.
So there's a lot of complexity here, and certainly a lot of techniques and tools that you're developing and want to make available. Would you envision that your company would also be providing the expertise in actually applying these tools?
I think yes, definitely. We want to become experts at using our own tools, right? And the goal is not just to provide tools for people to use, but I envision that at some point we may start training our own large models as well, right? And maybe we're the next OpenAI. I don't know. We'll see.
Hopefully. Great. Thank you very much. That was a great talk. Let's move to our next speaker. Our next speaker is a lead research scientist from Wells Fargo, Samuel Yin-Chi Chen, and he's going to talk for us about the quantum circuit, quantum agents toward a scalable and self-programmed quantum AI. Thank you, Samuel.
Hi, everyone. Thank you for having me here, and thank you to the organizing team. So today I will talk about probably very biased perspective on the next generation of intelligence system. And I will focus on the quantum system, which is not just a model, but a system that can evolve or program or modify itself. So we all know that currently we have very amazing AI system, classical AI system, probably already know that. And most of these classical models are based on the handcrafted architectures, transformer system, or diffusion model, etc., etc. And this model, you design the architecture, you choose the hyperparameter, you choose the training settings, a lot of other things. And quantum models, already several very good talks now, until now. They are good, and but they inherit some of the issues from the classical machine learning, right? So you still need to design some quantum circuit, and some of the quantum circuits, for example, how to encode the system, how to design the learnable part, they may not scale, or they may not be very generic, right? So you design a model which is very good for a particular problem, but probably it totally fail in another task. So I want to think that what is the system that can modify or change itself, because our environment, our data, and our mission will change over time. So here I will propose a set of tools that I developed over the past several years about how to build this kind of self-programming quantum AI. So the first is the quantum LSTM, which is a quantum recurrent neural network. And I list it first because building a quantum machine learning model which can memorize our information is the starting point for all kinds of intelligence that we want to pursue. And the quantum reinforcement, we want to build an agent which can learn in the environment interactively. And moving forward, what if we can build a system which can dynamically change the quantum system parameters? But this is not enough, because we have a fixed quantum circuit architecture, and we build another AI agent to program it. So the next step is to automatically find the quantum circuit architecture. So this is the quantum architecture search. So for the scalable part, we can consider the quantum federated learning. So originally, federated learning is designed to provide privacy-preserving features, right? So you don't want to share your data. You can only share the models, train the models, and using some aggregation techniques. But we also find that federated learning, you can rebrand it as a distributed learning system. Okay. So the last part is the quantum train. So this is a quantum-enhanced classical training. So we use a quantum system, quantum neural network, or variational quantum circuit to generate the parameters of classical AI or classical neural network model parameters. So we can use these stacks to build various kind of quantum AI applications. So the first is the quantum LSTM. So this is actually the more generalized version of the classical long short-term memory. So here we have replaced the classical neural network in the classical LSTM by the quantum neural networks. So why we do that? So because if we want to, when it is first proposed, if we want to rewrite all of the contents in pure quantum operations, then you need a lot of different kinds of, the mean circuit measurement, dynamic circuit, etc., etc. So it may require a lot of resources that we don't have at that time. Probably even today is still very difficult. So we build a hybrid system, right? We still use some classical gating mechanism, but we use the quantum circuit to represent the function approximation. And we can show that, at least numerically, that this kind of quantum LSTM can outperform the classical LSTM when the parameter or the model size is extremely small, or the data set is very small. So once we have the sequence learning, we want to go one step ahead. So because in the original quantum LSTM, once the model is trained, the model parameter is fixed. So how can we go beyond this? So I proposed the quantum fast rate programming, which use another classical controller to generate or update the quantum parameter from the context. And we can go further to allow the circuit architecture to change over time or change according to your task. So we can consider reinforcement-based quantum architecture search or end-to-end differentiable quantum architecture search. And this is the fast rate programming framework. So here, this is the whole architecture. So you have an input. And originally, if we only have a quantum neural network, then you just put in the encode the input and go through the variational circuit, and finally you do the measurement. But here we can use a classical controller. It can be a very simple multi-layer perceptron or classical LSTM transformer, or even a large language model to use it to process the input first and generate some update signal and put this signal into the quantum neural network. So you can not only change the variational part, but also how the system is measured, right? Because quantum measurement is basically a Hermitian matrix, and you can parameterize the Hermitian matrix, so you can dynamically change how you project your quantum information back to the classical space. But this is not enough, because originally we still need to design our quantum circuit architecture. So now if you want to build a quantum AI application, you need to decide how to encode the contents, right? So how to design the encoding circuit. Do you want to use Hadamard gate to initialize the circuit, or RX, RY, RZ, which kind of rotation? And how to design the variational circuits, because you can choose different kind of entanglement, different kind of rotation, etc., etc. So first, if you start a circuit from scratch, then imagine that you want to build a circuit, so you put one gate at a time, right? So this is a sequential decision-making problem, and indeed, reinforcement is a very good universal solver for this kind of task. So we can use reinforcement to build quantum architectures. So imagine that you have some quantum task. It can be synthesizing a quantum state or performing a quantum machine learning task. So you gradually add some gates and use the performance metric to guide the reinforcement learning agent. But reinforcement suffers from some issues, right? So for example, it has a lot of hyperparameter to tune, right? And for discrete search space, the scalability may not be very good. So here, we can consider the differentiable quantum architecture search. So imagine that you have a task, and you have some candidate circuit. You don't know which one is the best. So you collect all of them, and you create an ensemble. So you can load the data into all of the circuits and run all of them and get some output. The point here is that we have W1 to Wn is trainable structural weight. So you basically create a weighted average or an ensemble function. You use this to replace your originally handcrafted variational quantum circuits. So if you train this model, then you treat the circuit rotation parameters and those structural weight W1 to Wn in the same footing. So you can use gradient descent backpropagation to handle this. And the cool thing is that you can connect the several circuit blocks together. So if, for example, if each of the circuit block you have, say, n candidate circuit, then you can use the n-to-n differentiable method to search those n to the power of m possible paths. So we have these models. We have memory models. Then the next step is to combine them and to build some agent, right? So it can learn interactively in the environment. So we can consider the quantum reinforcement agent. So actually, this is a hybrid quantum classical reinforcement. It means that originally you used classical neural network, and now you have quantum neural network or variational quantum circuit as the policy function or value function. But you still use the classical reinforcement algorithms such as policy gradient or actor critic, etc., to learn those parameters. But when we want to go to the scale version or privacy preserving version, we can consider the federated learning. So here, imagine that there are banks, hospitals, or other different institutions. They have their own data, but they don't want to share the data. But they can train in their own data center, right? And then they share only the model or the gradient. And the centralized server can aggregate those parameters and distribute it to all the participants. So it basically can provide not only the privacy preserving feature, but also the efficient distributed learning. Because imagine that you have a lot of QPU quantum computers. You can chunk the large data set into several quantum systems and train the model. Final example is the quantum train or quantum enhanced neural programming. Okay, so here, until now, the models are a quantum model. It means that we train a quantum model and we use the quantum model in the inference. But classical AI is very good, and inference on classical AI on GPU or those FPGA, etc., are very efficient. So is there a way that we can use both of the benefit, right? So some representation capability in quantum and very cheap inference in the classical. So here, if we have a quantum system, if we have n qubits, then actually if you measure the amplitude or the probability, right, you get 2 to the power of n numbers. So why not use this to generate 2 to the power of n numbers in the classical neural network? So this method actually has shown some application in LLM LoRa fine-tuning and generating classical LSTM, larger LSTM model, and classical image model, for example, those CNN models, or even climate or typhoon trajectory prediction, etc. So it's very useful now. So there are several possible impacts of this model. So of course, finance. So for example, if you have a sequence model, you have a reinforcement, then you can use this to do forecasting or trading, etc. And healthcare. So again, similar the diagnosis or predictive modeling and communication system. In the communication, there are a lot of optimization tasks, or for example, spectrum allocation, and multi-agent reinforcement is very useful here, potentially. And similar problem also in the energy sector. So what I propose here is the we want to build quantum machine learning model. It's not just a simple quantum circuits, but a system with different level. For example, from the simple memory to be able to adapt to different environments or data set, and probably can reprogram itself and use in different field. Okay, so I will stop here, and I can take questions now.
Okay. We have time for one quick question, otherwise we move to panel, because we are over time slightly. So let's move the question to panel. Is that okay, Sam? So we go to our next speaker. Is our last speaker before the panel, but not the least, is Executive Director of the JP Morgan, Rudy Raymond, and he's going to talk about optimization parameter for quantum circuit via sparsely coordinated distance. Yeah.
Thank you very much for your inviting me and for giving me a chance to present. I know it's a challenge to give a last talk, because probably like the focus. So again, I'm going to talk about actually different perspective. Instead of using quantum computing for solving machine learning AI, we have seen that a lot. my argument that to make quantum computing useful, we have to use the latest and even the best machine learning and optimization techniques. And that's why we need a data center that actually integrate all these technologies together. So that one of the examples that I'm going to show is the role of sparsity in constraint optimizing the parameters quantum circuits. So again, just a disclaimer, this is not about market research. So it's not about, please do not use it for investment or something like that. So it's really about research. A lot of things are still debatable. We have to, scientifically, we have to discuss about this, right? So, okay, so why we do quantum computing? This is the motivation that we have to think about, right? And of course, for example, for myself, I work in finance application. Then, for example, we have to, let's say, we want to work with stock selection. And for example, on New York Stock Exchange, there are about 2,100 stocks. And actually, surprisingly, ETF that consists of a lot of stocks, actually more ETF than stock there. So you see the combination, the explosion of combination that will come later. Of course, we want to, for example, process the credit card. 2024, there are about like 1,700 transactions per second. We have to deal about this latency also. So the challenge in the scale of quantum computers, right? Number of qubits, also the processing speed, it really that matters. And for example, okay, every time a quantum hardware provider will have a news about, oh, we have this quantum computer, we have probable quantum advantage, people in the firm will come to me and ask me, can you run this algorithm and solve it, right? Of course, the answer is no, because we don't have the number of qubits. For example, if you want to do this with the 2,100 stocks that are available, assume that each of them we present is as just one qubit, one line here, right? And the decisions will be yes or no, included or not. We need 2,100, at least physical qubit, right? Then, of course, if you want to do entanglement, because without entanglement, we know that quantum computing will not have had advantage. We want to have this decision that entangle all inputs, right? So it's this layer operation. So we need a number of qubits. We need also many operations. We don't have them. Classically, these are not problems because I remember when I was a student, when I do programming, I had to be very careful with memory management. But now people use Python, just throw away everything. Like memory is free, almost free, right? And again, like data also. We have Wikipedia, all this data, and you combine them, you probably get artificial general intelligence within a few years, something that people don't think about it, right? How about quantum computer? We don't have the luxury. Noisy, few quantum qubits, no memory, slow, 1,000 times slower than classical, right? Then how can we are going to use it? And operations are limited. And no data, right? Or small-scale data sets in instant for machine learning. But we still want to use it for portfolio, risk modeling, anti-money laundering. That's what we have been hearing so far. But of course, there are another aspect. We can use AI, machine learning, actually to improve the quality of quantum computing. Of course, for real time, for compilation of circuits, control, things like that, error correction, very trivial things. Now, if I want to overcome the limited number of qubits, where one of my challenges, of course, then I have to work with large-scale data, which we don't have the luxury now. There are two strategies that I can apply. First is, let's decompose the problem, right? I think this is really classical. Like, if you remember divide and conquer method, we have large instance, we divide them into smaller instance and solve them the smaller instance. This also we can do it with the quantum device that we have now, or identify the kernel of the problem, right? There are examples of doing this with maximum independent set that we did with AWS and other providers there. Then actually, yeah, we can do that. That's really classical technique that you can use to avoid this, overcome this limitation of a number of qubits. But there's also another one, just like utilize the quantum superposition. It's really unique to quantum, that actually using entanglement superposition to encode more variables into a limited number of qubits. And we have some example of doing that. And how can we do that? For example, like we work with bits. Classical bit, I can argue that classical bit is aligned because you have like 0 and 1, and you have probability. And if you map this probability, it's actually form a line between 0 and 1, like North Pole and South Pole. And quantum state is actually a sphere, right? So if you like pure quantum state in 1 qubit, it's a sphere. And actually, you see this sphere, there are many ways to put a line inside this sphere. So there are many ways to represent 0 and 1. It's not one way, right? So you can measure in the z basis, in the x basis, y basis, and many other bases. And there are many ways to represent 0 and 1. So why? So this is actually the problem that I worked when I was a student. This is called quantum random access code. So remember, if we have Alice, let's say they're separated by distance, and Alice has to send 3 bits of information to Bob, and Bob wants 3 bits, but Alice can use qubit, let's say m qubits. Then how many qubits that Alice C has to send to Bob to deliver this bits, right? And actually, unfortunately, there's no quantum advantage if you require no error at all, right? So if Alice wants to communicate 3 bits, C has to use 3 qubits. Holef about 1970 something. But how about if Bob wants only 1 of 3 bits? Still bad news. Actually, you still need 3 qubits. But how about 1 of 3 bits? But you allow error. So this is something that very interesting. If you allow error, even classically, you cannot do this. You need 3 bits classically, but quantum you can do with 1 qubit. So actually, if remember before, right? So because Alice has 3 bits, so she needs 8 quantum states. Bob wants to be 1 of the 3 bits, which he doesn't announce before. He didn't announce before, so it's like he can choose later. So he has to decode the measurement, three type of measurements. And actually, remember the block spheres I mentioned to you. Alice can put 8 states in the corner of the cube there, and Bob can measure it either in the x, y, z basis, 3 type of measurements. And actually, Alice can have this. So this is kind of quantum advantage in communication. 1 qubit can have something better than 1 bit, right? Unfortunately, this is very interesting thing that we know this 1 qubit because it's perfect ball. And actually, like you cannot do more than 3 bits. If you want to do 4 bits, no, you cannot do that. So you can do 2, you can do 3, but not 4. For 2 qubits, well, a lot of things to do in that. That's actually like we know that you can do up to 15 bits, but not more than that. And to have the constructions, right? There is a classical construction for generic one, but to have like very good construction with provable advantage or provable like probability, you have to solve bilinear semi-definite programming in large dimension, a lot of variables. It's very hard. Nobody knows the optimal one, up to very trivial one. But why it's very important? So because this is a very interesting application, people know about this application in automata, locally decodable code, private representative, random number expansion, many other things. Theoretically, it's interesting. Actually, we have been working at that when I was before. We use it for discrete feature encoding, where like zip codes, age, or something like that. Recently, we applied for random access optimization. So instead of using 1 qubit for 1 binary variable, we can encode more binary variables into qubits. And we call it random access optimization. And we show that we have a QAA-like scheduling. So instead of doing training, actually, you can use like QAA inside to optimize the parameter. And even recently, people saw that you can have some sampling-based quantum diagnostic. So it's like low depth circuit and run it and to solve some optimization problems. Now, we've succeeded to reduce the number of qubits, still constant scaling because we don't know the optimal construction of random access code. But now there's a problem that we have to make the operation longer. Now we have another problem, and actually we solve it partially by some sparsity-inducing coordinate descents. So, well, there's also this very interesting thing in quantum world, like you want to solve this NP-hard problem, max cut, by using QAA. But if you remember, QAA is really QMA hard, which is actually more difficult than NP hard. But why people are using quantum computer for that? But okay, I'll leave that answer later. But okay, why it's very interesting because QAA, if you have this QUBO from like unconstrained binary optimization objective function, you can design the algorithm immediately. You don't need to ask ChatGPT to do that because there is generic construction to do that, right? Now, how to schedule the parameters of QA. Of course, we want to have this less layers because we don't want to do long operation because the qubit will decohere, and people smaller angles, right? Because it's easy to control. And people have come out with this like adiabatic-like scheduling, so you can do transfer learning. There is analysis on small number of layers. What is the optimal angle? So actually, you don't need training. Yeah, so even there's evidence by Google team that's saying that, oh, we probably some algorithms there that actually beat the best classical algorithm for optimization. So, and I think we have heard also from Josie and also from Amira before, the optimizing this parameter quantum circuit that has gradient-based, gradient-free, and other things. And it's actually like this is very difficult because then you need very like high level of optimization also, right? But interestingly, in quantum, there's a very sinusoidal function that we can use, and actually already mentioned by the speaker from Coherent Computing before, which we call like Grothal solve. So if you fix all other parameters instead, except the parameter that you want to optimize, it's actually a cosine function with 3 unknown variables. So if you evaluate the circuit 3 times, you can jump to the optimum one without gradient, right? So just jump to the optimum because you know the functions. And yeah, this is basically the Grothal solve. And this actually, in classical, 30 years ago, people used this for simplifying the regression method. So it's actually like people use machine learning. For example, you have regressions, you have many unknown variables, but you want to have explainability. So you want to have less number of non-zero, because the more complicated your model probably will not be generalized. I will have error in testing. And people use this method called lasso to find this sparse coefficient for this regression. And our idea, like, why not use this sparse coefficient lasso to actually make the circuit sparse, or the layer, reduce the number of layers, and like prioritizing smaller values on layers here. And actually, we could do that because the objective function of this lasso is similar. Like we have f, which is like smooth function, which with penalty on the sum of the L1 norm of the parameters, right? And this coordinate descent is being used for solving this with very good analytical form or closed form. And QA, you can also do that because the objective function is also smooth. Now the parameters, the strength of the parameters, you can also have a penalty on that. But of course now, because QA, there's a group of parameters. So there are many gates with the same parameters. So instead of a cosine function, it's actually the sum of cosine function now, where the sum is m is actually the number of Pauli terms in the Hamiltonian, which can grow quadratically, cubically to the number of variables that you have, right? Depends on the objective functions. And well, still, basically, if you evaluate your circuits by fixing other, except the one you optimize many times, like 2m plus 1 times, actually you can jump to the local optima each step, right? So this is like coordinate descent. It's a very naive way to do that. And actually, like to do that, you have to solve a linear equation, a system of linear equation. And then, of course, you can. There are many ways to solve this system of linear equation, but still you need many evaluation of circuits. But interestingly, this is very interesting. Like in classical, there's called compressive sensing. When you have this system of linear equations, when you can actually reduce the number of evaluations exponentially smaller, this become log m, while kappa there is kind of 20. So people know this by analyzing many things, by theoretical analysis there, that actually you can reduce exponentially number of measurements there. So great. So we can jump to the local optima every time exponentially faster. But unfortunately, when you run in quantum circuit, I think Amira mentioned about this before, that actually you have to estimate the energy estimation, actually destroy this exponential reduction that we have. Exponential saving become polynomial saving now. But still, we have something there that by using this compressive sensing. And the compressive sensing, you need GPU and something like that to solve it. I will not go into details, but it's something very interesting technique to reduce the number of execution of the quantum circuits, right? So we have also, like, because we know the function, we can approximate it with this sparsity constraint. We can have the derivative. We also know how to make zero many parameters there. So the parameter circuit becomes sparse. So just as a concluding remark for my talk here, right? We start from motivation. We want to, people come to me, okay, I want to run this algorithm. We don't have enough qubits. We want to run them. We know that there are techniques to reduce the number of qubits, reduce the number of operations by solving large-scale combinatorial optimization problem, by solving large-scale linear system of equations. And we can use compact encoding, and also we can use this L1 regularizations that are probably useful. So quantum computing can be used for AI, machine learning, and optimizations. On the other hand, quantum computing also needs powerful AI data center or AI framework or something like that to improve their performance. So I think that's also important, and that's why these two have to be integrated tightly. Thank you very much.
Thank you. Can I talk? We can have one question, and then we move to panel, slightly running over time. If not, then let's do the question across the panel. I mean, if all the speakers can come up, please. I know we don't have Amira. She has to leave. But. So this time I start from the audience, then I go. I have a few questions also to ask. So, any question from the panel, from audience? That's obviously the heavy topic, but yes, there is a one. Yes.
Okay. One quick question is, when you want to apply PCA kind of techniques that are developed for classical machine learning or classical data analysis, would they also directly apply to quantum machine learning or quantum data analytics, or you want to have a different set of approaches like quantum specific PCA or other similar techniques?
It's a question for me, or?
I think we go across the. I mean, I think yes. I mean, certainly for you, for Wells Fargo and JP Morgan, but I mean, everybody is more than welcome to answer. Yes.
Well, to my understanding, I think quantum is really a system to solve many problems in linear algebra, because it's really a linear algebra problem. And I think if I'm not mistaken, there's algorithm, for example, tensor PCA, which is probably have some quantum advantage and other things, right? So, yeah. So even there is also variational algorithms for solving PCA. So yeah, something that might be realizable. But again, every variational algorithm will have challenge in training. So.
Someone?
I think I will talk about the perspective of using PCA or in the dimensional reduction of large quantum systems, large input data for small quantum systems. So a lot of quantum machine learning work out there use those PCA or other non-trainable method to trim down the data and load into the quantum circuits. But another perspective is actually use a learnable layer, right? Classical neural network, tensor network to compress the data into the lower dimension and use the quantum circuits. But if you use this, then you need to be very careful to do ablation study to single out the effects of the quantum circuit itself, because if you use a very large learnable model to do dimensional reduction, then it's very likely that the reviewer will challenge you that, okay, probably the quantum system, the classical neural network, large classical neural network already did most of the work. So I think PCA is still used in this scenario is because it is non-trainable. Yeah.
Okay.
I'm gonna pass on this.
Okay. Sorry.
I really agree with that point about being careful about if you make the classical part of the model also trainable, right? Then it's hard to figure out what the quantum model is contributing. So PCA is useful in that sense because it's it's parameter free. One thing is that if you go to our website and look at our papers, right, it's hard to do PCA on very large data sets. Like if you have a gigascale data set, I think PCA scales quadratically with the size of the data set. So it's hard to do there. So we've developed this batched PCA processing technique where you divide your data set up into batches, and then you run the data encoding schema discussed on each batch, and then you make it consistent across the batches. And then that's non-trivial to do, but it actually turns out to work very well for this data encoding, large classical data into bit strings for loading into quantum states.
Mikhail, do you want to answer your?
I have no comments on that.
Okay. So, Richard, you go ahead, please.
Hey, thanks. I have a controversial question. Controversial because it's not about technology. Who are your customers and how are they interested in your work? What's your pitch to them? Value proposition type stuff. Just who are your customers?
Who are you asking?
Yeah. So, let's start. I think
who are your customers, internal or external?
Let's start from the Mika, and then we go from Mika, and then we go Sonika.
Well, yeah. Well, currently our customers are the quantum community. So anybody who is running quantum circuits, they might want to run them more efficiently, especially with the NISQ machines. Our compression tool gives you 20 to 30% typically shorter circuits or shallow circuits, and that can be a deal breaker whether your circuit is actually giving you something sensible or not. Now when we get the quantum advantage algorithm working or demonstrated, it's already working on paper, that would again have applications in the quantum community itself in cloud verification and benchmarking, but we also have pinpointed a couple of industrial applications that we can then talk about later at later stage. Yeah.
Thanks. So in my case, so our customers are actually people who are very much not part of the quantum industry. So what we're focusing on right now in our pilot projects is to help users in different domains. Let's say people who are working with genomics data or people who are working with some ECG data, things like that, figure out which of their data sets are actually suitable for quantum computing or not, right? And that is already quite a lot of work. And we find that that's something that we can do very effectively in this, we don't have like commercially viable real quantum computers yet, right? But there's a ton of work that needs to be done on this side.
Yeah, so for us, really, the way I read your question is, who's going to spend hundreds of millions of dollars to buy a useful quantum computer? And so that's a pretty small number of companies maybe, and mostly national labs and government institution. But there is kind of like they also serve some users, and that's the user base of what we think of as people that do scientific computing. So that's what we think of as our customer base.
So my official answer is we build this model and trying to find if there are possible business use cases from other units in the company. Yeah, but usually we test on some small data set. Of course, you cannot expect that using the real-time trading data set or the data stream and run a production level quantum system now. I think it's not practical at the moment.
For my case, our clients are internal facing, so I'm mostly trading or other people who have data, and we try to bridge them with external vendor also. But actually, the challenge is actually how to hide the data, so because even we cannot access their data, formulating their problem also. So this is something. So even because quantum computing has limited ways to solve problems, so we have to find mapping their problems into problems that can be solved by quantum computing.
Really cool. Can I ask a follow-on question?
Yeah, please.
So obviously from your perspective, is there anything you need from hardware vendors that you're not getting? I mean, if you had a wish, is it just a bigger quantum computer, or is there anything you'd like to maybe ask the hardware providers for, or maybe it's nothing?
Well, for me, it's not just about hardware, right? For example, like people have been solving their problem many years by specific software. So we have to also understand how they operate and like try to like transition it by the way that they're operating. So understand like how the modus operandi, like how they work. It's also something that we have to think. So because like if you come and they completely change the way that they work, probably it's very hard to accept it. Even like because classical algorithms, they already have very good solver. For example, like Groby or CPLEC or combinatorial optimization. They're very good, right?
Does anyone else want to come in? I have a specific request for hardware providers. So everything I talked about today, right? It was very theoretical in some sense. Like I didn't mention any qubits, like physical qubits or any kind of real-world quantum advantage yet, right? Except I just mentioned like this metric of measuring how many logical qubits. I think what would be very useful is if hardware providers can start to provide things like the power requirements, that it requires to run, certain size of quantum circuits or number of quantum gates, and timing and all of those, physical parameters, so that we can start to build models of how much it costs to run, how much it costs to train a quantum model versus a classical model in the real world.
I think, for us, specifically for the hardware, I think it's a really complicated set of requirements and interlocked, right? You're saying, do you need just more quantum qubits? The answer is no, because how much they're going to cost, right? And can I actually control them? And the type of questions that you were asking, which is, what's the timing and so on and so forth. So I think that's kind of like a really complicated answer in the sense that, we're trying to look at something that's useful, meaning that, can do interesting things and in a cost-effective way. And that's I don't think we have the answer of everything that we need, but I would say that's the thing that people should start thinking about, is like, how do I make it like affordable and useful?
Yeah, well, for us, it's quite obvious from the plot I showed. The first applications, also industrial relevant, would be there around 50 qubits and a bit better than 3 nines of fidelity for 2-qubit gates. And then for the next industrial applications, it would be more like 70 qubits, something like that, and a bit worse than 4 nines of fidelity.
From my side, I think it's hard to say, right? So if you have a lot of qubits, but the topology is very bad, then even a very simple circuit, you need to have a lot of swap gates, then basically destroy the performance. So I think the interesting part is the hardware-software co-design, right? So if you have a particular quantum hardware, and how do you build a good tool chain that can efficiently translate or compile the problem into the hardware native instruction sets.
Yeah. What we saw for us is that if you have nearest neighbor coupling versus all-dual coupling, it's a factor of 2 or 3 that you win.
Can I ask a follow-up question on that? And then we go. I use my chair privilege. Do you think that you're gonna go, because if you look at the, let's say, large language model companies now on the classical side, either they are some like big one like X and Gorek and OpenAI, they have their own in-house GPU and they train and they sell the service or whatever they provide a service, or some a smaller one, they go and rent GPU. So you see in your business model, which one is going to be? You're going to go and train model, rent a quantum computer somewhere and then provide your service, or you're going to think that somebody has to bring a big quantum computer and use your model locally?
Well, for us, we are not buying the hardware. We're using it. Currently, we're using the Lumi supercomputer that is locally in Finland. But we also, I think we have already, or then we are about to map also the AWS, classical computing resources to the service. And then, as I said, we have all the.
No, that's for, I don't want to say for proof of your concept, I understand. But as a service, how do you see that? You're going to do this for your customer on top of the third-party quantum computer and give them you give them the model, the trained model to use? That's how you see that, or?
We are training the models ourselves.
Okay.
They're just using it. Yeah.
Okay. So Sonika?
Yeah, I think, I don't know, it might depend on the industry you're serving too, right? Maybe there are some like defense applications where, they don't want you to have your model running on some remote hardware somewhere, right? And they want to have everything in-house. So I think it would be very specific to the industry you're serving.
Because the question, in fact, came from your talk, that you said that your ambition is to become like OpenAI of the classical.
Yes.
But that means that you have to have everything on house, just provide a service for whoever wants it.
Yeah. I think it's too early to answer that question. I think it really depends on how the hardware is going to evolve and how many quantum computers are going to be there in the world. Are we going to have millions? Or are they going to be a few hundred? I don't know.
Well, but what I said is that we're not going to buy the hardware ourselves. It doesn't mean that it couldn't be a private cloud installation.
Yes.
Yep. I don't know for finance sector or HP.
The regulation is very tight. So I think it's probably more on-prem or something we build ourselves. But maybe look what classical happened. Maybe follow what the classical technique or classical solution we're using, right? So. I cannot really say, but maybe a good chance for data center trying to have this confidentiality computing or something like that.
A question, yes.
I would like to just extrapolate a bit on Richard's question here, because I think it was a very good question. Just imagine yourselves some number of years in the future, and the hardware is not a problem anymore. The hardware works, right? You have 70 qubits, you have as many as you want. Who would you
70 logical or 70?
700, whatever you need. Let's just say it's not a problem anymore, right? What would you, who would you be helping, and what would you be helping them do better than they're doing now? Just, imagine what that might be. The hardware's not a problem.
I mean, to me, again, I go back to my presentation. I think that the things that are kind of interesting is, quantum chemistry. So you have 100 logical qubits. You can start kind of creating, sort of simulating molecules that don't exist and you cannot simulate classically currently. And so you can start thinking new pharmaceuticals, catalysts for reducing greenhouse gases, what have you. It opens a whole range of new applications. That to me is kind of the sort of the pot of gold at the end of the rainbow.
I think we have a question, yes, Dean.
In the quantum industry, there is a concept that each new generation of a computer will be more expensive than the previous one, and that people will not be buying the first one because they'll be waiting for the next better one to come out. And this is something that is, for me, very counterintuitive from my industry experience. I'm coming from a telecom world, 30 years of telecom vendor experience. So it is sort of, you develop something, the people buy it, they learn, and they do step by step, forwards. And here, when I'm also after this whole day summit, it seems like, except in one presentation, I'm sorry, I apologize, your name, I forgot you. Yeah. So you said start doing in many small steps. So why don't you see that a quantum computer with 1,000 logical qubits could be $20 million in 5 years?
Sorry, what's the question?
It is why the community cannot see that a quantum computer with 1,000 logical qubits can be available in 5 years for $20 million. Why think everything it will be in the hundreds of millions of dollars? With the increase of the capabilities, the price is staying the same, and the price of qubit is going down.
First of all, I don't fully agree with you that the quantum computers are getting more and more expensive, because at least IQM, the company I've co-founded with the other co-founders, they, of course, the first quantum computers of the first generation, they are expensive, but then the price actually drops quite quickly. They also introduced a quantum computer with less than $1 million. So that's not necessarily the case. Of course, now we're talking about 1,000 logical qubit quantum computer. If you would think 5 years of hardware development, I think just because of the bill of materials you would need for that technology would kind of cost quite a lot. But then if we scroll further into the future for superconducting quantum computer, when we are doing everything at millikelvin, like you heard that there is some efforts on that. We also have an effort in Helsinki on that. That will cut down the cost by 3 orders of magnitude. So then you would be actually talking about that kind of cost that of a quantum computer that you want to pay for it.
When you said, just one follow-up, you said the bill of material is quite a bit. Are you saying across all the modalities or just your?
No, that was just for superconducting. Of course, there are these other modalities where it's not necessarily so expensive per qubit, but it remains to be seen how it scales. Yeah.
Thank you.
I don't know the rest of the team, Sonika.
Yeah, I just want to add to that. If you weigh the cost versus what the benefits might be. So if you look at classical AI, right? People are spending trillions of dollars building nuclear reactors, putting data centers in space, like all kinds of science fiction projects. And some of that sounds crazy, but I think the nugget of truth in there is that what the release of ChatGPT and all these different models showed is that there's like an insatiable hunger for intelligence in all kinds of different industries and different application areas, right? People are figuring out how to speed them up with AI. And if quantum computing, what is 1% of $1 trillion, right? If quantum computing can even help 1% there, right? That will pay the bills, essentially.
I think Ramona, you have.
Yeah, so great talks. So I guess I think most of the talks actually touched upon, the training phase of AI/ML. Do you foresee a, specialized quantum device that can do inference, which is like, pocket-sized or maybe like, small number of qubits, like, on the edge that can actually like, store a neural network equivalent model in the quantum space, and that can actually like, perform inference. So my next ChatGPT will go onto a, query will go to a quantum computer instead of. I mean, I understand the training phase, but like I think what is the equivalent in the inference, and do you see any advances there?
Should I answer it? I think it's still a matter of research, but there is a possibility that when we are training these quantum models, during the training phase, they go, the path they take to find the optimal parameters is inefficient to simulate classically. But once they find the final set of parameters for that data set, that actually maybe can be approximated classically. So it's possible that you may have training on quantum and deployment on classical, like a tensor network simulator, right, that can approximate the quantum circuit that the quantum computer found, right? And in that case, tensor networks can run on TPUs or GPUs, right? And you can deploy them at the edge, but the model training can happen, in a centralized fashion in some quantum data center.
I'm actually asking the exact opposite, which is training, can be classical, doesn't matter, right? At the end of the day, it's a neural network with some weights. can you actually map that onto a quantum computer, right, in a much more denser or condensed format, and you can have a quantum device do the inference? Is that even possible? I mean, I guess I don't really understand the relevance of a quantum computer. At least I have not followed the space enough to say.
The quantum, like when people say quantum neural network, it's not exactly true. When you train a quantum machine learning model, the trainable parameters are basically how much you're rotating a qubit and how strongly you're entangling different qubits. So that doesn't have a one-to-one mapping with weights and biases in a classical neural network. People say quantum neural network, but it's actually not a neural network. It's a class of parameterized functions that you can optimize to model correlations in a data set.
So are you saying that there's no equivalent in the quantum realm for inference? Is that
functionally there's an equivalence, but the input and output can be the same, but what's happening inside?
Sure, internally it could be completely different. I don't have any problem with that, but my question is, if such a machine existed, what would it, what type of properties would it exhibit? Is it actually better in terms of like efficiency, power consumption? Is it compact representation? Is it accuracy? I mean, I'm trying to figure out what would be the holy grail for inference in the quantum realm look like, and what type of properties would it kind of give you to even pursue that kind of a goal?
If I might try to answer, I think it's really speculative about this, but I remember I talked about this random access code before, and I remember my college in Singapore that tried to model this quantum agent using quantum memory by using random access code. And probably like you remember, measurement affects the quantum state, right? The way you measure sequentially, the first measurement will affect the second one and things like that. Exactly resembles what economic behavior. For example, if you ask somebody, a question about how many times you date last week, and then after that, are you happy? Depend on the answer of the first one, the answer to the second, are you happy, will differ from the anchor of the first question. Resemble quantum memory, something like that. And he argued about this. Probably we can use this model's inference in quantum computing. I'm not sure, right? This really speculative, some behavior in economic which might be explained, but maybe also classically simulable. I'm not sure, but something, yeah.
Thank you.
Any question more? Okay. If not, in the current, a final question from me. In the current quantum computing available, you see a lot of companies make it available via AWS or individually make it available. Is there anything useful for a customer? Is there anything that solve any pain point we can do with all the application that you propose today, or we have to wait still for the next one?
Maybe there is. Maybe there is.
And do you have it, or you don't want to expose it? Yes.
Yeah, I mean, it may be that some of these machines that you heard about today or didn't hear about today actually already have high enough fidelity, or maybe they're going to be calibrated soon to have a little bit better fidelity so that this quantum advantage algorithm can run. And I think that's very exciting. Our aim at the company is actually to demonstrate quantum advantage as fast as possible, and my feeling is that it will come this year.
Okay. Sonika?
I think we're probably at the edge,
Yeah, we are getting there.
Edge of it. It's still probably classically simulatable, but it's pushing the boundaries.
And
yeah, I kind of I kind of disagree. I mean, I haven't seen a useful application that can run. So I would say they're useful in the sense that they teach people how to program them, they teach how to use them, but I haven't seen anybody saying, this is something that will make me money. And that's my definition of useful. I mean, it will make money for some people, but it's kind of not for the user.
So of course the probability is non-zero, right? But I mean, probably for research it's good, right? You always need some device, and probably you can train some toy model. I'm not sure, but for production level, I'm afraid that the probability is still non-zero, but probably not very big.
Okay.
For me, well, I kind of believe in zero-qubit applications. So you don't need to wait for a quantum computer to have effects, because people will come with problems we probably like formulated 20, 30 years ago, and we reformulate it, trying to solve the quantum computers. We maybe came up with new hints that we can already apply, or because sometimes we have to beat the best classical algorithm, we don't know. Maybe we can invent best classical algorithm by revisiting the problem. And actually we saw that, for example, DQI, decoded quantum interferometry, it's not really well studied, but people now start studying it. Probably some application there, right?
Great. So I think we conclude this panel with the final famous Ramana's question, that if you come next year here, and one ambitious that you want to have to announce it here, what would be for you? Because
well, what I said, we would like to, of course, announce the demonstration of classically verifiable quantum advantage.
Okay. Sonika?
For us, run an end-to-end model training on a real data set on 50 qubits on hardware.
That's very ambitious, yes.
So for us would be kind of the outline or the blueprint of our kind of quantum environment, so people can start using and appreciating the advantages of quantum computer.
Probably demonstrate some quantum self-learning framework, which at least can generalize to probably a couple of slightly different environments.
Okay, and
running quantum application for finance, actually, but some really like something, not really quantum advantage, and doesn't necessarily to be a quantum advantage, but something useful.
On the quantum
running on quantum computers.
Okay, yeah. Great. Thank you. With this, let's thank our panelists and speaker again. Thank you very much. Okay, this also concludes our workshop today. I thank the large number of the online audience. I think we stop here, and the recording of this session would be available, I think we in a week or so, in a Cisco website, YouTube channel, and Cisco TV channel, and we inform all the speakers about that as well. So I thanks again all our speakers for contributing to this summit. It was a great summit. We have, for the people that are in person, we have a small reception downstairs. We would like you to join us. We will be very happy. Thank you.